Now, as I said, this is a slight deviation from the book that, the order that is there in the book, and maybe in the document also. They said we'll first look at the phase diagram, and then in the phase diagram we'll say these are the pure substances. Okay, and the pure substances we said many chemically pure, and even chemically also it is nuanced, because whether it's number of electrons, number of protons, number of neutrons, or the distribution of electrons. So all kinds of variations are possible even when things are, let's say, chemical formula is the same. Okay. So, and also the phase also has to be the same, because things cannot be may not be pure if they are in different states. So we had this concept of a phase, and then how to handle phases, and then we looked at all the different kinds of ways in which material can be classified. So, and also what does it mean? You see, it could be a liquid, it could be a vapor, it could be a gas, it could be a supercritical fluid, and all Bose-Einstein condensates, complex fluid, so many things, plasma, and we discussed about what are the special features of those, and how is this state of matter related to the functionality of the phase, okay, or of the state. So at one level, if you want to look at any technology, then you can very quickly decide whether what kind of things do you need. And you will see lots of examples of this, okay, as you will do other courses in chemical engineering. Okay. And also we looked at how to use this information in some other situation also. Okay, so gas-like, liquid-like. So a state of matter is like a fundamental structure of the group that you have, or whatever you are handling, you look at this structure. And that can allow you to solve many difficult problems also, which otherwise you will not be so easy to solve, or you need lot of domain knowledge to solve them. Then we said, okay, pure is one end. Then we said, okay, pure is like a rarity, things may not be pure. You see, because even if they're not chemically reactive, you see, so you would say noble gases, there is that, very low reactivity, zero reactivity, will almost not combine with anything. Okay, that's okay. Chemically, they may not combine, okay? But within that material, it can be, you see, other kind of distributions, isotopes can be there. Okay, that is one. And also, physically, things can be together. See? So even though it's chemically inert, but doesn't mean that you will not have a mixture. You still can have a mixture. You see? And you can also have a solution based on the scale at which you are looking at it. Okay. So the difference between the solution and a mixture, we already know that there is an identity, the identity is lost. So even if at one level it is different, okay, heterogeneous, but at some other scale it can be homogeneous. Okay. So it depends on the scale at which you are looking at the whole thing. And then that idea of continuum and quasi-steady would also come into play. So even though something is impure, or something is a mixture, or something is in a solution form, the way you treat the system actually holds the key. Okay. So you can get rid of any heterogeneity, or you can think of a scale or a perspective so that everything looks homogeneous. Okay. So this is the key. While we look at pure and all kind of good things, bad things that have come out because of this perspective of pure, okay, or let's say looking at purity of things, there is always a perspective where things can be pure, things can be impure. Okay, and especially if you want to, even in materials, okay, or in other fields also. Okay, so you just need to have a perspective, okay, so that you can get rid of all the discontinuities or heterogeneities and others, okay, and see the whole thing as a homogeneous. Okay, so things can be heterogeneous, homogeneous, depending on the perspective in a very physical way, depending on the scale at which you are looking at things. Okay, do you understand this concept? In a very physical way, you look at the whole thing. This is good, but this whole is good. But if I look at a very small portion, it's not good. It's a lot of things. Okay? So in a very physical way, this can happen. But if you apply this in other places, quick, then there are things that have multi dimensions. So you need to focus on the dimensions that bring in the homogeneity. Okay. So because things may have many dimensions, and things can have many degrees of freedom. You see, because of the way that you will look at. And a good example is a complex fluid. Complex fluid has more degrees of freedom than we think. You see, it's simple liquids, So all the things that are based on no phase rule, this, that, all that, which is based, the whole foundation, you see, this PVT equation of state will not hold there. You see. So similarly, you can, so in a philosophical way, you will never know all the dimensions of everything. You see. But you can focus on some dimensions which bring in the homogeneity. Okay. And this is one challenge for your generation. You see, for my generation, it's already over, but your generation will face this challenge, where you'll look at things and you'll have to focus on the positives, or you'll have to look at what differentiates and what homogenizes, what unites and what differentiates. You'll have to look at things in that way. Okay, and you'll have to choose that perspective. You'll have to choose those dimensions. Okay. If you do not do that, you will have a very miserable life, I can guarantee you that. You see? If you will not be aware of this and don't adopt to this, all of you would be, anyone who doesn't do this will have a very difficult life. Miserable is probably a very strong word, but dramatic, you see. So you will really understand. Okay. So look at things where you can control whether you want to look at them as separate or whether you want to see some similarity. Okay, if this key is not there, you will face a lot of problems. Okay, because that is one of the keys of surviving and doing well in whatever future I can see for you. Okay, you and the world and the environment that you will go into. Okay, so pure and mixture, while in a physical sense it is okay, mixture, pure, we do all the things and everything. But when the rubber meets the road, as they say, when you are actually doing something, it is all the way you will look at it. You see, it can be a pure thing. You see, and the pure thing defined in a way, this is this, this is this, this is this, this is this, and this is what my pure substance is. Okay, so not pure in sense of, let's say, this is all electrons will have all the same quantum numbers. That's not possible. You see. It's not there. So that was one message, and it is mixing rules, and you need to look at the consistency, and the consistency means that you arrive at some state function, whether you arrive from here, there, whatever, it's the same. You see, so 3 components, 4 components, 5 components in a mixture, and you will have 5 dimensional space. Okay, and mathematically it's not difficult. You see, to visualize is difficult, but mathematically it is easy. You see, it's like a vector with 5 dimensions. So you have the state, and you say, okay, the composition is x1 is this, x2 is this, x3 is this, x4 is this, and x5 of course is 1 minus all of that, so not independent, but let's say 4. Okay, assuming that you're writing mole fractions. Okay. So 5 component mixture, you're writing it in terms of mole fractions, describing it in terms of mole fraction. You'll need 4 independent ones. Okay, and you can write properties based on those 4. Okay, and which means that for some value, whether you approach from here, there, everywhere, you should get the same. So the mathematical formulation for the mixing rule has to follow these kind of things. Okay, and we discussed for a binary system, we discussed infinite dilution, we discussed how these means are calculated, and how are why is there is a very solid mathematical foundation to the mixing rules. Okay, so it is not that you just think of something. Okay, there is a solid foundation to the mixing rules, and that lies in the different types of means that we study: arithmetic, geometric, and harmonic means. Okay, and it's And they have a very practical use also. Okay, and I kind of emailed, shared with you a paper, some R&D note by some professor, and I told you the story about that paper also. Yes. And all that, Tawqir, was done by me.
I saw the whole table.
it was going to the library, no AC, nothing, bringing out all these thick volumes, because for 1 year the journals are separate, so all the volumes are separate. It's easy to get them, but once 1 year is there, they'll put all of them, bound them together, and then store them somewhere else. So you have to lift them, sit down, and then add, and then you note it down on a sheet, and then you go and key in the computer. and this whole idea of कि sir -2 कर देते, it was my idea. He was very happy with whatever I got. So I said, "No, sir, ऐसे करते हैं इसको." And the trick was, if some of you have read that and have caught on to the trick was delta x. You see, so if the answer comes out to be 2.02, you say, okay, I'm looking at intervals of 0.05. So 0.05 means 2 is likely to, because you never reach 2.02, which is the absolute minimum, you see. So a little bit of, but it's okay, the machine gave it, you see, I didn't. You see? So if you put in the same number, you'll get you key in everything, the machine will give you that answer. You see, I didn't cheat. But intuitively I thought 2.02 is not so exciting. You see, 2 is exciting, and then you see, it's only a method. Optimization is only just giving you some values. So it was useful at that time, and it is very, very useful even now. So if you do these kind of things, you can still get them published. It's not a difficult thing, but not very exciting. So all of that, this is one part. So what kind of, and then we run into another issue, and I want to bring that here. Okay. We look at pure, and we bring in the concept of two things here. Okay, reversible and ideal. Okay. Ideally, I would have waited, or I would have used at least 1 full hour to explain what is ideal, okay, and what is reversible. But the issue is that you will not do any thermodynamics later. That is the main issue. So whatever has to be taught now in this semester. There is no backup or reinforcement. Okay. So ideal is what we decide is ideal, first of all. Okay. We have this concept. I think that's pretty easy to understand, that it's based on definition. Okay. So for pure substances, we are looking at ideal. Okay. That what is our ideal and ideal system, and then we kind of work with it. Okay. So typically, when you choose that ideal state, okay, how do you choose an ideal state? That this is the ideal state. So for a gas, you see the major problem is because of the potential energy. And it can be argued in many ways. Okay. One of the ways is that you are only worried about kinetic energy. Okay. And you say, okay, potential energy is anyway a big problem. Potential energy is actually a bigger problem than whatever happens with volume. It's a very, very tricky problem. Volume is still manageable in some sense. Okay. So we say, okay, what is the tricky part? Tricky part is the potential energy. So let's look at a system where there is no potential energy. Okay. And for those systems, those will be our ideal systems. Okay, easy to handle. Okay, and we'll get rid of a lot of complexity. So ideal gas is conceived in a way that there is no potential energy. You see, and why there is no potential energy? Because potential energy is a concept. Potential as a concept is a very tricky thing. So kinetic energy is okay, things are moving. At what speed they are moving, whether they are at rest, not, once you fix the reference frame. And actually it is a benefit because you can choose the reference frame. Okay? So it kind of gives us, lot of benefit. So lot of ease of handling. So we say get rid of potential energy, keep only kinetic energy, and what is that state of matter where only the kinetic energy matters? You see, anybody, what is that state of matter where only the kinetic energy is an issue? Hmm? Gases, ideal gases, far away, no? They're far away. They're very far away, no? So no KE, no PE. Okay. So if you are looking at no potential energy, which means no intermolecular forces, nothing, you're just looking at the movement. Movement, you see, vibration, rotation, translational, all those kind of movements. I mean, they are complex in themselves. Okay. So we say this is our ideal state. Okay, and this is ideal gas. Okay, and because we kind of just looking at the movement, we are looking at displacement as the work done from here to here, and the movement, pretty easy to see, and mathematically also pretty straightforward. So we are looking at ideal gases. But we can have ideal liquids, we can have ideal solids also. It's for us. So this is a degree of freedom that we have, or a design variable, let's say. We can choose. Okay. So what do you think an ideal liquid would be? If you have to choose an ideal liquid, what would be that ideal liquid? What characteristics?
Or incompressible. Not compressible.
Pretty much, all liquids will be. See, another aspect is that the deviations from that could be monitored. Okay, and most of it is in that phase, so that if you have worked hard to do things for the ideal state, you should be able to use it for majority of the situations. Okay, and if the deviations are there, then it is a special case, and those deviations you should be able to have a handle on, and those deviations also, to handle those deviations. Okay, so ideal liquid, what do you think?
Newtonian. Whose property doesn't change?
So I think you should.
Zero viscosity. Zero viscosity, I mean, it's defined like that. Okay, this is how it's, but maybe they have not done this course maybe. Huh? Fluid, have you done fluid mechanics?
Currently.
Going on, we'll check currently. Okay, so it's defined, it exists. What would be the definition exists, the way it has worked for most of us, it works, you see. So it's okay, you say incompressible, doesn't help much. Newtonian, kind of helps. So it is a very strong contender, you see. So for many liquid, like if you're behaving, looking at a liquid system, then Newtonian is a good choice, you see. It's not a bad choice. But inviscid is a even better choice, you see. Inviscid means, you're taking away the impact of the neighbors. See, what is the problem? You see, neighbors. What problem? Neighbors is the problem and all. What is the problem? देखो एक बैग रखा no neighbors. इसको ला So we say mu equal to 0 kind of systems. Okay, so very easy to handle. Doesn't help much though, you see. The Newtonian concept, is more useful because you're looking at flow and viscosity is there, you see. So very few, unless that you are able to, conceptually understand how is it different from a gas, let's say. Okay. Otherwise, you see, Newtonian is a much more practical way. Okay. To look at an ideal fluid. Okay, this is my ideal fluid. It's okay. जो कुछ भी है यहीं से शुरू करते हैं. This is my reference frame. This is what my ideal is. You see, why do I worry about something which is not, मन को आराम but काम तो कुछ नहीं हो रहा. mu equal to 0, how does it help? It doesn't help, you know, सिर्फ सोचने में. ठीक है, you know, that emotional thing is also, you know, very important. After all, you know, ultimately, whatever you do, आराम से होना चाहिए. Mu equal to 0 is okay, but engineer है यार, he has to get some work done. See, इतना science क्यों पढ़ रहे हैं? शांति चाहिए तो यार ऐसे ही मिलेगा. You have to get something done. So Newtonian is probably a better choice. Solids में what kind of thing do you think would be an ideal solid? Anybody? Which is the easiest one to solve for and very useful also, and also the deviations from there can be handled. You see? So I am able to handle this situation, and this situation is very useful, so I am able to handle it, which means that this situation, and it is very prevalent, okay, and if the deviations are there, at least I know how to handle them. Okay, so anybody? अरे डरते क्यों हैं? बस भी बोलो. Crystalline solid. Any particular kind of crystalline solid? FCC, GCC, HCP, पे पढ़ाया जा रहा होगा. लाजो पूछते हैं सर कि इतना सारा ये CP हम कर क्या रहे हैं सर? Cannot place बोल रहे हैं. At one time, you know, that was the only joy in Delhi. Cannot place. Then लोग आज Sunday आज CP जाएंगे. ऐसे करके लोग जाते थे. ये ऐसा नहीं कि Sunday मनाली जाएंगे. CP जाएंगे बड़ा शो. बड़े-बड़े लोग जाते थे. So, any preference? What do you think? What kind of close packing is the best?
FCC
Hmm?
FCC close packing because there is highest packing fraction, so minimum FCC.
FCC and SCP?
Both.
Both. Why?
Both have same packing fraction.
Where?
Both have same packing fraction.
Utility पे आ गए, which is one aspect. Okay, कि you know packing fraction है, pack कर दिया, maximum material pack कर दिया, solid का काम ही क्या है? ज़्यादा material, that is why we look at. If you look at the idea solid क्या है, कितना surface पे है, okay, कितना easy है, कितना इसमें what do you call, you know, same in all directions. Isotropy. So how much isotropy is there? Okay, and packing कितनी है? Okay, and surface पे कितना है? See, so those are the kind of things that will help you in designing it. Isotropy is a major thing because you don't want to be running into ये L है, B है. So what is the crystal structure where there is only one lattice parameter?
Simple cube.
And 90 degrees. One lattice parameter and 90 degrees. Best तो यही है ना. Simple cubic को छोड़ के तुमने कहा इसको छोड़ो, इसमें क्या रखा है? जहाँ ज़्यादा माल है वहीं चलते हैं, जहाँ ज़्यादा पैसा है. And ज़्यादा पैसा किसमें? जितना मटेरियल ज़्यादा पैक कर दिया. अभी तो आइडियल बना रहे समझा रहे थे. Anyway, water can be in that sense. Water can be the ideal fluid. If you forget about how complicated the water is, and nobody understands water. You know this. That is the state of art. Water is still very mysterious. Okay. And why can't water be an ideal fluid? You know, water सब कुछ है. उसके बाद देखेंगे क्या होता है. हाँ, water तो available है. We'll do all the experiments ये वो, and who wants to go inside the molecular structure and do all that. Water पता है, density पता है, ये पता है, वो पता है. And actually, lot of engineering is done based on density of water, viscosity of water. You see, lot of engineering as you will move ahead. You know, lot of useful things that are all based on water. You see, temperature scales क्या है? Water boil हो रहा है, water freeze हो रहा है. Specific gravity क्या है? Water है. Okay. Density is specific gravity, viscosity is water से, CP से, you know, once again there is another CP. Centi going. That's also CP. So this is okay because you want to make use of whatever else has been done. You will use this ideal gas, but with liquid you have a lot of utility. A lot of variety can be there. You see, depending on as I said, for most of the engineering calculations, water is most useful. Why can't water be the ideal fluid? Just deviation. Okay, knowing fully well that water we don't understand, but it's very useful. So the reference frame with respect to water is very useful. You see, and we already see that. You see, all kind of things. Just say air. You see, so a lot of things are with respect to air in engineering. And here, and then solids. We say simple cubic. Isotropic air, and lot of material is anyway there. Single lattice parameter, so we don't have to worry about this 90-degree angle. So those are rhombo and red, you're not worried about those. Okay, and surface पे enough material. Okay, but you're right. We are looking at a crystal structure. Okay, we are not looking at amorphous. Okay, so this is an idea. ये हो गया. Energy calculation से इसको करते हैं, but then we have an idea about air, we have water. इधर solid में क्या ले सकते हैं? What would be a good candidate for solid? Like air, like water. Solid क्या होगा?
Metal.
कौन सा metal? ऐसे ही जला रहा हूँ, मेरा काम ही जलाना है। जला रहा हूँ, हाँ, किताब तो बिल्कुल है। Any ideas? So I have seen कि even the chocolate, doesn't hold any, attraction. Even if I say one chocolate, एक बाकी है, एक बार सही आंसर दिया था SCF. So I'll give you one chocolate. I remember that. Can anybody answer like liquid? Like in liquid, I said water. In gases, I said air. Even though ideal ones are defined very differently. You see? But in engineering, it's more practical. Air is available. It's air. Okay. Liquid. Water is very tricky. You see, we don't understand what water is. You see? Really don't understand. A lot of work goes on. It's still going on in water. Structure of water. Okay, and it changes also. Okay, so many interesting things. Solid में क्या करते हैं? Anybody? अरे दिमाग चलाओ यार, ये किताब, कोर्स, ये दोस्ती, ये कंफर्ट, ये चला जाएगा कुछ दिनों में. फिर क्या करोगे? अभी इजिएस्ट होगा कोई जॉब कर लोगे. जॉब में भी दुनिया भर की पॉलिटिक्स है यार. 1 से 2 हुए, 2 से 3, उसके बाद तो पॉलिटिक्स ही पॉलिटिक्स. पॉली का मतलब ही ये. कुछ तो दिमाग खोलो. नया पूछ लिया कुछ थोड़ा कंफर्टेबल. यहाँ तो सब कंफर्टेबल है, वो तो सो रहता है इतना कंफर्टेबल. उसको जगाओ. कल क्या मेडल जीता क्या? इसको भी जगाओ. अरे बकस, इसको अच्छे से जगाओ. हाँ बताओ, सॉलिड में क्या आइडिया सॉलिड होगा? आजकल तो गोल्ड ही चल रहा है, बाकी बाद में देखेंगे. Just to tell you how far removed we are from what our world is, and systematically. किताब एग्जाम so many times, and her exam opens up something else, her exam opens something else. ये सब करके positive feedback, negative feedback सब तरह से करके इधर आ गए कि the defining feature of our ages, of our civilization, of our history is forgotten. हम तो हिंदुस्तान की बात कर रहे हैं, सिंधु घाटी सभ्यता की बात कर रहे हैं. तुम एजेस ही भूल गए जो पूरी ह्यूमैनिटीज को डिसाइड करते थे. वो सब भूल गए. कौन सी एजेस होती थी? स्टोन एज, आइस एज में तो मूवी देखी होगी। ये कहाँ से है? डर लग रहा है क्या? आइस एज एक मूवी आई, यू नो, आई वॉच्ड, आई मीन एक नहीं कई है। आइस एज, स्टोन और ब्रॉन्ज अब आया ना। आयरन सब भूल गए तुम लोग। यू नो मार्कर्स ऑफ आवर सिविलाइजेशन वो भूल गए तुम। हम तो यहाँ सोच रहे हैं तुम्हें हिंदुस्तान याद दिलाएं, वेदा याद दिलाएं, उपनिषद याद दिलाएं, 5000 साल की इंडस वैली सिविलाइजेशन याद दिलाएं, तुम यही भूल गए। क्या हो रहा है? We have succeeded very well. ये जो पूरा सिस्टम बनाया है ना, एग्जाम पढ़ाई एग्जाम पढ़ाई एग्जाम पढ़ाई एंड प्राइज, ये है। अभी क्या होगा? हो गया है, स्टील चलो मान लेते हैं, पहले था अभी इंफॉर्मेशन तो वेब वाली चीज होगी।
यूरेनियम है। ये बोला था।
ये तो तुम और भी धन्य हो। मतलब पकड़े गए तो उसने बोला तुम्हें लीडर बनाया है। लीडर ये नहीं कहता कि ये इसने बताया, लीडर कह रहा है यू आर रिस्पांसिबल फॉर व्हाट यू आर सेइंग, स्पेशली इफ यू आर द लीडर, you are responsible for whatever you are saying, especially the leader, but leader को एक immunity है। पता है क्या immunity है? कि leader बोल सकता है, leader can say something and always say कि this is a feedback that I've got। यहाँ पे बैठता है एक लड़का कौशिक मेरी क्लास में, उसको जरा सा भी पुश करो कहता है सर यही फीडबैक है। मैं नहीं कह रहा सर, ये क्लास कह रही है। ठीक है, सो डिपेंड करता है किस तरह के लीडर। उसने कहा भी है तो भी नहीं कहोगे ये क्लास मैंने डिसीजन, आई हैव डिसाइडेड आई विल नॉट गो बिहाइंड कि हमारे पीछे इतने लोग थे बिकॉज़ ऑफ माय पोजीशन। ये एक साइन है एंड इट्स अ वेरी वेरी इंटरेस्टिंग साइन। यदि 4 लोग गलती करते हैं, एक सामने आके खड़ा होता है कहता है ये मैंने किया, मैं ओन करता हूँ। ओके, ये बहुत जल्दी पता चलता है कि किस तरह का आदमी है। ओके, सबसे पहले अगर एक्सक्यूज देगा तो फिर कहीं गए तो। ओके, सो दिस इज अ टेस्ट। इफ एवर यू आर काइंड ऑफ डिवाइडेड बिटवीन एंटरप्रेन्योरशिप करना है, सीईओ बनना है या कंसल्टेंट बनना है या कोई जॉब करनी है, यू अप्लाई दिस टेस्ट। अगर सामने खड़े रहते हो सीईओ बन जाओ, और अगर आज समय आप ही की गलती थी, ये था तो फिर कंसल्टेंट इज द बेस्ट यू कैन डू, इससे ऊपर नहीं जा पाओगे। ओके, इट्स अ मेजर डिफरेंस। ओके, सो एनीवे यूरेनियम एज मतलब इतने बुरे दिन नहीं आए यार, अभी ग्लोबल है, इतना सन है, इतनी विंड है, अभी यूरेनियम तक जाना बट राइट।
कार्बन
This is one of the ways। अब शुरू हो गया ना, रास्ता खोल दिया हमने। अब तो सिलिकॉन, अब तो सेमीकंडक्टर सिलिकॉन भी आ जाएगा।
डायमंड
डायमंड्स आर फॉरएवर। डायमंड्स खत्म हो गया है, तुमको पता है? पांड्या कहाँ है इधर? पांड्या डायमंड्स खत्म हो गए, पता है तुम्हें? नहीं पता? अरे सूरत इज डिवास्टेटेड। इस बार तो शिवाजी भी नहीं गए, वैसे ही डिवास्टेट हो गए बिकॉज ऑफ लैब ग्रोन डायमंड्स। इट्स ओवर, खत्म, फिनिश्ड। यू नो, बिकॉज वो सेम ही है, इट्स लैब ग्रोन बट इट इज द सेम थिंग। तो उसमें फिर क्या करोगे? ओके, तो डायमंड्स का कुछ अब रहा नहीं। पहले तो बहुत बिजनेस करते थे डायमंड्स का। ओके, मैं भी मेरे घर में भी होता है. You see, but these lab grown diamonds are diamond itself, you know, कुछ है ही नहीं, difference ही नहीं है ना. You see, there are many things that are used जो natural नहीं होती हैं, but they are treated as natural only. So lab grown diamonds are like diamonds. So ये सब आगे देखो क्या क्या याद आ रहा है. We are learning all this. Carbon is a good way, so you need to look at the carbon का क्या कर रहे हैं. You see, so इतना कार्बन है, ऐसे कर रहे हैं. So but solid नहीं है. You see, थोड़ा मिस्टेक इसमें हुआ कि solid. It's the material that defines this. Silicon जैसे है, good example. Diamond भी ठीक है, but not so much. और कुछ? Anything else? Steel. Plastic, you know, because for a very long time, you know, that was the defining thing. Very much plastic on that. So yeah, so much for ideal. ये सब बना दिया, okay? But we know what in thermodynamics, what are the ideal states? Those are known, the standard states, the normal states, and the ideal states. That's already well defined. Those we are not going to change, but you have a freedom to understand, put a lot of effort in understanding something, and then using that result in variety of situations, and also look at the deviations. Okay. So ये हो गया. But there are many contenders. यहाँ नहीं थे. Stone, bronze, copper, iron, you know, already established. Okay. Then silicon also, carbon also, and polymer. ये एक major है. For solids, if you're looking at solids. Okay. This is kind of in between. Lithium can be one of the important things. Uranium भी आएगा, but uranium से ही bomb नहीं बनता है. Bomb तो बहुत जगह से बन जाता है. Okay. सारी uranium लेके क्या करोगे? You know, fissile तो होना चाहिए. सारा तो मसला ही है. Nuclear grade. वो कैसे बनाओगे? Isotope से enrich कैसे करोगे? That was the key. So you've got a centrifuge because everything else is the same. So how do you, I mean, you can separate only if there is some difference. If the difference is only in the isotope, you know, so कैसे करोगे? You know, and very small difference. You know, 250 में 2 का difference कोई difference है? नहीं, और उसको घुमाओगे, घुमा के magnified that difference. तो इसलिए centrifuge were critical. उसको बढ़ा देंगे, उसको घुमाते. The density difference was G की value बढ़ गई ना, 10,000 G. Okay. Reversible को how do we understand? So this is for the mostly used for the material, can be used for the process also. Reversible is for the process. Okay, where losses नहीं हुई कुछ. So there is a process where there are no losses. वापस आ जाएगा. So धीमे होगा, never far away from equilibrium. जहाँ गए बस वापस आते हैं. But critically उसमें speed and deviation is not the key things. You see, reversibility is the key thing. Okay, so that I do it and I take it back, and the system is the same, surrounding is the same. You see, that is the key. But we say in practical sense only if we do it slowly, so every step is reversible, but that is not the key thing. You see, reversibility is the key thing. If whatever we do and come back, so हमने बहुत कुछ कर लिया, वापस आ गए वही है. ऐसा होता नहीं. You see, कुछ तो रह ही जाता है. कुछ भी करो, you know, never be able to come back to the same. Okay. So, but we'll look at the ideal one. How does it play out with material, let's say? Also, so we'll look at separately. How does it play out with the material part? So there can be ideal solid, ideal liquid, ideal gas. You see? And the real, if one is ideal, the other would be real, and there will be a deviation. Okay? And there can be mixtures also. This is slightly tricky, and a lot of people make mistakes in that. So there are two things here. Okay? One is whether the component themselves are ideal and whether the mixture as we know is ideal, the way we have conceived. Okay. So if we are looking at, let's say, arithmetic mean type of mixing property, then we say it is an ideal mixture. So presence of one is not affecting the presence of other, or the result is only based on relative proportions. And those relative proportions can be, all kind of things, volume wise, material mole wise, if it is number wise, if it is material, how much material is there, how much units are there, all that, you see. So there can be an idea of an ideal mixture, and there can be an idea of an ideal component. Okay, so you can have an ideal mixture of non-real components, you see. So you can have a situation where you have an ideal mixture of real components, or a non-ideal mixture of, or a real mixture of ideal components. You see, both can happen. Okay, so that opens up many things, but many times we forget, we think ye ideal, and if we mix them, the result would also be ideal. It is expected, but not necessarily true. Okay, because ideal things when put together, they can have an emergent behavior. Okay, so that emergent behavior can be very different. As in complex fluid, we have seen that. See? So gas. Of course, with gas it's easy, but liquids, ideal. You mix them, something else can happen. See? There's no guarantee that things will not happen. Okay. So all kind of things are there. Okay, and we need to estimate those properties. So we'll look at property estimation for ideals. Okay. So the way things are done is they state we need to make a difference between this. We need to make a difference between ideal, and we need to make a difference between real. Okay, both for pure and mixtures. Okay, and real. I'll use real and reversible. Okay, and what we do is and there are other things also. Okay, where we do not use this, we use all of these. You see, so one way would be that we work very hard for the ideal ones. We work very hard for the reversible ones. Okay. And from there, we either use some kind of efficiency or some kind of deviation, okay, and we say that this is how the real would be calculated. So we choose an ideal state, we work, we have expressions for that, and we know how to work for the ideal, and then we look at the deviation and we look at the real one. Okay, this is one method. Okay, we look at reversible, okay, and then we look at the real, and we have an efficiency or something, or coefficient of performance or whatever, many different ways, okay, and you can have the results for the real one. So that for that heat, so much work is taken out, so much heat is transferred in a process. Those are the kind of things, and this is how the material has transformed. So the material properties change, the heat transfer takes place, and the work happens. Okay, three major things. You see, what happens to the material? How much heat is there? Transfer takes place, or how much work happens, we are worried about that, see. And then we say we know ideal and reversible, we work very hard on that, okay, and then we get some answer, okay, and then we look at the deviations, okay, so from reversible to real we get some deviation, and like efficiencies, okay, and limits on those efficiencies, and expected values. But in your generation, if you really want to know what is going to happen if we do this, or what should we do to achieve this, okay, both ways, front problem and the back problem. See, we want to achieve this, so what should we do? Okay, and if we do this, what will happen? Both problems can be solved by lot of data and this part. तुम्हारी generation में तो यही है, मैं तो already dinosaur बन गया. and this course भी dynamo बन गया in a way. लेकिन सोचो कितना limitation क्या है? Heat transfer is the limitation ultimately. You know, even if you have MI, you have, you know, ML and AI and everything, heat transfer. उसका क्या करेंगे? You just see, you know, just look at the beauty of whole thing. You know, who is putting a spanner in all of this? What is the ceiling? Who is going to finally say कि this and no more? Heat. हम नहीं रोक सकते, सिकंदर नहीं रोक सकता, अकबर नहीं रोक सकता, हीट ही रोके जो भी कर रहे हैं. The heat is so bad. Okay, अगर उसको हैंडल नहीं किया तो सब खत्म कर देंगे. ये सब chip manufacturers, they have started a division on heat transfer. Can you imagine? They are looking at all the calculations कि इस capillary में heat transfer हो रहा है, यहाँ हो रहा है, nano heat transfer हो रहा है, ये हो रहा है, how much heat is being dissipated. So they already realize कि semiconductor is okay, but we need to worry about heat transfer. Okay, so जितनी भी companies हैं, you know, big companies, all of that, they now have a division. You see, they already had a division, but now, you know, funding is there for that. So heat transfer in devices. You know, if somebody really doesn't want to, you know, कि यार अब बहुत पढ़ लिया, अब इतना और कौन दिमाग लगाएगा, अब कुछ करते हैं. You see, it is a very good field. If you are going to look at mass transfer, not so much about mass transfer, heat transfer. Mass में क्या है, उसमें तो logic gates हैं, semiconductor है, all kind of, you know, induction effects are there, material move नहीं कर रहा है, but the impact is there. ये हम तो conventionally सोच रहे हैं, all of this is moving from here to there and we can see that. See, but semiconductor में क्या हो रहा है, electrical charges, electricity में क्या हो रहा है, कुछ तो move नहीं हो रहा है, but सब कुछ हो रहा है. It's so difficult to handle. See, and ठीक है, Ohm's law लगा लिया, Kirchhoff's law लगा लिया, you know, all of that, we can do this, inductance लगा लिया, ये लगा लिया, circuit solve कर दिया, but वो सब भी fail हो जाता है semiconductor में. You know, partially जा रहा है, नहीं जा रहा है, कुछ जा रहा है, कुछ नहीं जा रहा है. You know, just imagine. You see, तो उधर तो जो ये सब B.Tech electrical वाले लोग हैं, physics वाले लोग हैं, let them do that. You see, if you can just focus on heat transfer in small dimensions, you know, very thin. And I'm looking at those chips, looking at those PCBs. You know, बहुत interesting है. कुछ ज़्यादा पढ़ना नहीं है, वो मोहन पढ़ा रहे हैं तुम्हें. Okay, that is enough. उससे ज़्यादा नहीं चाहिए. Okay, and you'll probably do some course in microfluidics also, do some course in, कुछ तो electrical में पढ़ाएंगे ही ना कि circuit क्या होता है, channels क्या होते हैं, नहीं तो पढ़ लेंगे. इतना ही है बस, और ज़्यादा नहीं है. And you can do a lot. Fluid mechanics चाहिए होगी थोड़ी. Okay, तो वो भी पढ़ेंगे. So that is one career option, good career option. If you really want to be in science, engineering, and want to do good, but वो सब तो ठीक है. ये, so all of you can have a career with only this much. मन नहीं लग रहा है, you know, यही चलेगा. This is good enough. अभी मतलब अगले 5-10 साल तो तुम्हें जॉब मिल जाएगी. उसके बाद क्या होगा, I don't know. Okay, but ये भी एक ऑप्शन है. फिर ये सब कोई यूज, इसका कोई यूज नहीं है. You know, पैटर्न देखा, कुछ आगे डिसाइड किया, पॉसिबिलिटीज देखी और कर दिया. This is what it is. पर उससे पहले बहुत होता था, correlations. This is poor man, you know, machine learning or statistics. वो करते थे, correlations करते थे, फिर semi-empirical होते थे, empirical होते थे, and all of that. And correlations में दो mistakes होते हैं. Okay, and you understand what correlations are? कुछ पता ही नहीं पता है correlations. अरे यार एक कुछ में expression दे देते हैं to compute something. Based on, you know, some experience. Have you not used any correlation?
It's a
अभी तक?
ideal का
correlation और property estimation.
हाँ, ideal का correlation वगैरह है ना.
बहुत सारे हैं, पर ये तो अभी 3rd 4th semester है ना. इन्होंने शायद ना पढ़ा. I don't know. Really नहीं or not? You tell me यार. Otherwise I tell you what correlation. वो correlation नहीं. there is a correlation, which means that if the density is this, if this is this, then some other property is like this. ऐसे करके नहीं कुछ प्रॉब्लम है.
ट्यूटोरियल में था.
ट्यूटोरियल में तो पढ़ा होगा इसी कोर्स में ट्यूटोरियल आगे चल रहा है. अदरवाइज यू हैव नो आइडिया कि कोरिलेशन क्या है. प्रॉपर्टी एस्टिमेशन में
स्केलिंग में पढ़ा था.
we'll have to teach correlation also. This is the property. इसको estimate कर रहे हैं. Some value here, some value here, some value here, some prefactor here, some this here, some index here. So this is where you are given an expression and you key in the values and you get the property value or whatever you are looking at. So this is the correlation. Okay. It is not the same as correlation coefficient. It is not the same as that this is correlated to this. Okay. Or this is caused by this. So we are not looking at that. We are looking at a simple expression where you key in whatever is required and you get the value. Okay. And there are many correlations in chemical engineering. Okay. So typically, the correlation की height इतनी, weight इतनी, ये इतनी, तो mass इतना होगा. I mean, I don't know. So I can't think of it. Sheet कहाँ है? Where is the sheet? तो बाद में देखना. Check कर जल्दी. ये चश्मा नहीं लाया ना? आर्यमन त्यागी, तुम बोलोगे? Thank you. दिल्ली बोलो.
आर्यन त्यागी,
Yes.
तौकीर, निशांत कुमार,
Nishant. Okay. Good.
दिव्यांशी नरेश, निशांत नंदन,
Good.
सनोज कुमार,
Sanoj. Okay.
तहसीन अहमद,
Okay. तहसीन कहाँ है? तहसीन अहमद. तहसीन अहमद कहाँ है? नहीं है. काटो उसको.
शायद किसी ने गलती से मेरे दिमाग में काट
काट दिया गया. तो कटे हुए को नहीं तुम्हें पढ़ना है. सही से जो काट दिया गया है नाम उसको क्यों पढ़ रहे हो?
दिया। मुनावत पवन,
मुनावत.
निनावत गणेश,
गणेश. Okay.
अश्विता राठौर,
राठौर. Okay.
हार्दिक कुमार,
Yes.
खुशबू यादव,
खुशबू. Yes.
लकी भुस्कुटे,
बिस्कुटे. Yes. Good.
शुभम चावला,
शुभम. Yes.
अभिषेक कुमार,
Yes. Okay.
प्रथम मनचंदा,
प्रथम. हाँ. Good.
प्रीतम कुमार,
प्रीतम. Yes.
आकृति हरित,
हरित. Yes.
स्नेहल सृष्टि,
सृष्टि. Yes.
सुमन माझी,
माझी. Yes.
पारस कंसल,
पारस. Good.
सुरभि,
सुरभि. Yes.
श्रियांशी गैरोडिया,
गरोडिया.
जागरण शाकल्य,
शाकल. Yes.
क्षितिज कुमार,
क्षितिज. Yes.
राहुल कुमार,
राहुल. Yes.
यश मोदी,
यश. Good.
प्रखर अग्रवाल,
प्रखर. Yes.
दिव्या,
दिव्या. Good.
पीयूष कंवत,
कंवर.
केशव,
केशव.
अर्णव रंजन,
अर्णव.
विकास कुमार,
विकास.
बसंता रंजन रॉय,
बसंता.
ईशा कुमारी,
ईशा कुमारी.
हर्षित भट्ट,
हर्षद.
तनुष सिंह परियार,
परियार.
आयुष भंडेरिया,
आयुष. Yes. Good. हो गया. कोई बचा है?
हार्दिक
चलो. Good.
हार्दिक कोटवार,
कोटवार.
आयुष कुमार, समर्थ गुप्ता, गर्व गुप्ता, अनिंदर रॉय,
Yes.
दृष्टि, उत्कर्ष गंगवार, निखिल कुमार जांगिड़, विकास यादव, स्तुति उपाध्याय, शशांक कुमार सिंह, निकिता जलवानिया, सार्थक मौर्य, अभिषेक सोनी, मान्या अग्रवाल,
Yes.
अमोल गुप्ता, हर्षिता अग्रवाल, आलोक यादव, पूर्वी जैन, हार्दिक बगौड़ा, निशान विश्वास, तरुण कुमार, केशव राज,
अभी
दीप्ति,
केशव एक हुआ. अभी एक और केशव भी है. ओके. ठीक है.
केशव राज, दीप्ति भारद्वाज, देन विशाल भगत, तुषार शर्मा, अंकित सुरेश भाई पड़ाया,
Yes.
सारंग मेंदे, अनिरुद्ध गोयल, इशिता सैनी, श्वेता चंद्रा, ऋषभ देवांगन, मीनाक्षी,
Yes.
शशि कुमार, पुलकित गर्ग, अनन्या यादव,
Okay.
अनन्या यादव, अनहद सिंह,
Yes.
निष्का मुरारका,
Deshka Murarka. Yes.
आदित्य सौमिल।
Soumil. Okay. Good.
ये बात कर लीजिए सिंगल कोर्स के लिए बात कर लीजिए आदमी नहीं जीवन सबसे मिलने का आता है डिपार्टमेंट वाले मतलब है ऑफिस में डिपार्टमेंट में भी तो ऑफिस है उनका अच्छा क्या संबल में वैसे नहीं होता या फिर मुझे लगता है कि ये BTT की ना BTT क्या बताता है
मेजर प्रोजेक्ट था।
हाँ मेजर प्रोजेक्ट हो सकता है
इसमें फर्क क्या है? प्रोजेक्ट से प्रोजेक्ट है जो 16 क्रेडिट से करा रहा है पूरा तो भी समर में
अरे वो बच्चे के ऊपर है यार उसको फ्लोट करवाना है कि नहीं करवाना है
तो असल में लोग प्रोफेसर इसलिए मना कर रहे हैं। लास्ट ईयर क्या हुआ था हमारी जो बैच थी वो लोग अच्छी हुई थी उस वजह से डी अपलोड करा दिया वो कोई रीज़न नहीं था। इस बार जो बैच है ना ज़्यादा कोविड डेली नहीं है थोड़ी बहुत ही एक सेमेस्टर आधा सेमेस्टर कोविड देखी है इसके बाद वो सीधा तो ऑफलाइन स्टार्ट हो गया तो ऐसे बच्चों को तो डिग्री एडमिशन चांसेस कम है ठीक है। अब प्रोफेसर को ये है कि अगर उनको बोला जाए समर कराओ वो मना कर देंगे समर में स्कूल आओ क्लास कराओ ऑफिस जाओ
सेल्फ स्टडी ले सकते हैं ना
सेल्फ स्टडी अलाउड नहीं है
क्यों अलाउड नहीं है भाई
उन्होंने ना बोला है जब लास्ट में जाकर एक आध थोड़ी नहीं
एक्सेल बना रहा
डेटा है मेरे पे
कायदे से वही होता है इस साल
ग्राफ
तो
कैसे जनरेट होगा ये बता
आपको पता करा दे रहा
साथ बड़ी बोलेंगे इवन इवन कोर्स में जो तो अगले साल इवन कोर्स में जा पाऊंगा और वो खाली पड़ा हो उसमें क्या करूँगा
अरे मतलब ऐसा है कि अगर तेरे को इस साल हमारे साथ ग्रेजुएट होना है और तेरा कुछ अटक रहा है ना तो ये लोग समर में सेल्फ स्टडी देंगे मतलब कहने का मतलब ये होता अगर तेरे पास मौका है मान ले कि भाई तेरे बहुत सारे कोचिंग बाकी है और तेरा अगले साल डिग्री खत्म होगा तो वो लोग शायद ना देंगे क्योंकि तेरा अटक नहीं रहा तेरा एक साल एनीवेज एक्सटेंड हो वो वाला वो लोग देख सकते हैं कि प्रेशर कम यहाँ पे कोई सिस्टम नहीं है कि भाई प्रेशर कम करना होता है
जितने क्रेडिट अभी उठाए ना सारे पास हो चुके हैं नियरली इस बार मेजर छुट्टी लेने को स्टार्ट किया जब बैठ सकता हूँ मैं सर्जरी होती है ग्रेड में होती है इसके बाद ये जितने सीरीज डाली हुई मैंने वहाँ पर बैठ लिमिट तक आ रही है और फिर जब सर्जरी तब जाके बैठ स्टार्ट किया विंटर में तो क्लास जा रहा था गर्मी आते आते प्रॉब्लम स्टार्ट हो गई फ्लूट निकलने स्टार्ट हो गया जमने स्टार्ट हो गया वो पिघलने स्टार्ट हो गया अंदर फ्लूट से अब वो चीज़ है नहीं तो बैठ सकता हूँ आराम से जो है बस उनको लग रहा है कि शायद इसमें भी कुछ क्रेडिट अटकना है। सर मैं एक बार बात करता हूँ, ये क्या होता है, एक काम करता हूँ, इसकी डेट तो बाद में निकलेगी ना,
इसकी भी
मतलब कोर्स मेजर खत्म होने के बाद रिजल्ट आने के बाद ही प्रोफेसर फ्लोट करेंगे ना अपने।
ये नहीं होगा।
हाँ तक याद है, ये था 16 तारीख का डेट है, पास तो मेजर खत्म है, फिर रिजल्ट आ गया ना मैं दिखा दूँगा, फिर मैं जब मैं पास हो गया अब आप भरोसा कर लो, मेरा प्रेशर कम कर दो, आपको बिल्कुल पीछे भी सुना था, इधर आप
बीटीपी करना मेरे से
अभी बीटीपी में पता है कि नहीं है कोर्स में क्या है, सर को वहाँ जाना पड़ेगा। बीटीपी में क्या होता है अपने उसमें रहेंगे ना, ऐसे थोड़ी प्रोफेसर कितने मिलते हैं,
हाँ
लेते हैं
जो वही समर में वो लोग घूमने जाते हैं ठीक करते हैं समर और विंटर में। ऐसा नहीं है मतलब कुछ प्रॉप्स जो एक्टिव रहते हैं समर में उनसे बात करिए।
अच्छा प्रोफेसर मुझे लगा प्रोफेसर भी
सारे प्रॉप्स तो नहीं घूमने जाते होंगे, कुछ कुछ जाते होंगे। मान लो जो नए शॉप से हैं थोड़ा ज़्यादा ही करवा दो
तो अगर वो रहेंगे ना यहाँ पे उनको बीटीपी कराने में कोई दिक्कत नहीं है, लेकिन उनको थोड़ी बाहर करना है, हमें आना है उनके लैब में, तो वो बीटीपी से मान जाएंगे, क्लासेस में भी मानते हैं, उनको पूरी क्लास जाना पड़ेगा गर्मियों में, बीटीपी मुझे लग रहा है घर मान जाएंगे, मैं क्लस्टर निकालने के बाद बात करूँगा।
एक डिजिटल बनाते हैं
step by step.
You may not realize, but that during the last 2 days in a classroom, like फिर कभी पढ़ना नहीं पड़ेगा. ये सिर्फ दिमाग में रखने वाली चीज़ है, you should qualify that. कोई होना चाहिए.
क्या पता तो ये सब कुछ है. तुम्हें कहाँ से है?
इस सिस्टम में कुछ कोर्स नहीं, नई एग्जाम देते कुछ करके क्लास तो करोगे, टोटल नंबर ऑफ क्लासेस
डीलिंग
कुछ नहीं होनी चाहिए. बड़े बड़े डिसीजंस हो रहे हैं, 100, 20, 30 each of the movements है, and we are fighting about these small numbers, which 10 का होगा, 20 का होगा. कितने का? 54%. Yes sir. 120%. अरे यार, we should learn from the elders and leaders. 10% basic. 10% basic. Okay. Then is okay. Chemical engineering, typically the margin of error or the kind of safety that you take is about 20%. Do you know that? Most of the operations, heat transfer, etc., heat mass actually it's a lot more. Okay. So heat transfer it would be about 20%. Momentum transfer also 20 to 30%. Mass transfer it can be as the over design or the efficiency should be, let's say, even double also. So you find out that this much time is required or this much area is required for mass transfer, but you design the equipment that has double the performance. So that factor of safety is double. Typically 20% for heat transfer. Momentum also likely 20. Heat transfer 3 times. ये जो जिसमें एनर्जी यूज करते हो, कोल वगैरह. So if the process itself is based on energy getting from the heat, so you're burning something, combustion, this, that, 3 times would be a good medium. Civil engineers, factor of safety would be 4, 5. Okay, so if they get something, that you should make this much thick, they'll make this much weathering वगैरह पे, and then you don't know क्या हो रहा है नीचे, जमीन के नीचे से seismic code. So there is a very strict code that kind of says that you have to have this much factor of safety. and you know, a whole lot of things that will come here and then be said.
फिर
Yes, quickly. You know, let's celebrate with new hairstyle. ऐसा करके घुमा करो जैसे कैसे फिर आउट करते हैं ना लोग एक पूरा ऐसा करो बाल भी घूमने से निकाल रहे हैं और तुम जोक समझ रहे हो I never joke I'm not allowed to yeah you're celebrating something you celebrate because मेरे को पूरा घूमना चाहिए थी अभी बाल भी घूमने से let's all the experts do it it's the brain for you moving to this you know very nice word there was a student you see we would color his hair with all kind of colors you know every week there is a new hairstyle and he was a boxer and he would actually go to Murika and other places and learn boxing and you know very and you all everything that people know who is a good person this that and everything so then you can celebrate you enjoy you can celebrate a very famous designer you know dress designer you know he was in this you know very celebrated school in the hills you know ये सब जो दून स्कूल टाइप्स होते हैं okay उधर था वो पढ़ रहा था and he was thrown out of the school for a while क्योंकि वो आज से 50 years ago he colored his hair green और ऐसे करके आया क्लास में और उसको भगा दिया स्कूल okay I think कुछ बड़े स्कूल में ही था I think green में चलो पूरा हरा भरा रंग के आया और गा रहा था and then he became a very famous you know dress designer वो बन रही था you know these kind of thoughts okay तो ये hairs gone part of the locks gone इसके तो बहुत और भी ज़्यादा चले गए you know all that shaving okay so you should enjoy them because you know some age you know they'll go away okay so you have to be kind of enjoy them while you have okay and take special care but don't be you know, nervous about anything you know, जो तुम्हारा मन करता है करो that's the idea okay after all किया ही है so you know why not take it further and show it to people okay and enjoy it celebrate it there is a message for all of you okay as young people young person as parents you know जो कुछ भी करोगे life में people under your charge you see if you are defensive about your decisions you know then the price that you pay for those decisions kind of doubles you see so don't be defensive about whatever you have done you know कोई बोले आप बात करें यार अच्छे तो हैं कितने अच्छे हैं you see somebody comes and comments कि आपका लड़का जो है बहुत पीट रहा है लोगों को you know when somebody neighbor comes and comments so parents क्या करेंगे पूछेंगे क्यों पीट रहे थे तुम्हें लग रहा है कोई बॉक्सर बन सकता है you know if the parent just asked him I could ठीक है बताओ कुछ डन था पंचायत में बॉक्सर बन सकता है मेडल okay and suddenly you know the whole idea is gone okay anyway you know very very fond memories of that student अभी भी है वो मुझे लिखता है कभी कभी crazy student so we were looking so yes I mean all these are the kind of things that we need to find values to because these will be used and then there will be these compressibility okay beta and kappa you know the volume compressibility and the temperature and the pressure so if temperature changes how volume changes and if temperature and pressure both how volume changes with those okay Then we were discussing about this xi, x1, x2, and we said that we are looking at this. Okay, the compressibility factor, and most of the property estimation, or rather thermodynamic calculations for real systems are based on this compressibility factor. How do you get this compressibility factor? And I said, you have an ideal gas or an idea of the ideal system, that is PV is equal to RT. So you say, I'll just multiply something here. Okay, when you just multiply something here, this is a good technique, because everything that you have, the answers that you have, the numerical methods that you have, or whatever techniques you have, you just have to multiply. Okay, so that's why this works very well. But then this may not be just this. How does this vary? You see, so you say everything is okay, I preserve this form. This would obviously vary with pressure, temperature and volume. Okay, but then I need to find that. But even in that, I do a bit of cheating so that I don't explicitly put all my pressure or temperature or volume variation here. I say I keep these out. The rest of the variation comes in here. You see? Otherwise, with the variation hai na. So whatever is the relation, I say okay, PV is equal to RT is taken out. The rest of the variations of pressure, volume, temperature in the compressibility factor, they go in here. Okay. So then we started looking at basis function and how do you find out unknowns. And if you remember, there is something called let the answer be x. And then you write down all what you know about x, and then you try to find something like this. On the left hand side of a equality sign, and you say, okay, if I can get this kind of structure, my job is done, because x equal to something. Okay, so all algebra and everything, second, third, fourth, fifth, jab se padha hai, algebra third se padha hoga, yahi hai. And there is no reason why it should not continue. Okay, when so much effort has been put into this, so thoda badh jate hain. Okay, so the higher education. So we say fx. So rather than just looking at x, we are looking at fx. Okay. So here for this thing it would be, what is z? Z is a function of PVT. We said how do you, in a general way, you see, and this is the key. You see, this is the key to most of the theoretical research. You see, the skill, the common skill to most of the theoretical research, most of the analysis. Okay, as let this be x was the clue to all algebra. Let's say application. You see, not the theorems, but the application. You see, so problem solving. So we say let the answer be fx. Okay, and then we say how do we find fx? So we write down all things about fx. Millisecond, because it's not so easy. Okay, so we need to be able to write things in the same way. You see, on left hand side, right hand side for equality and bring them to something. So we have this concept of basis functions. And basis functions could be complete set and linearly independent. So two reasons. Okay, it's something like this. Let's say two-dimensional vector. Just listen to this. A two-dimensional vector, if you have to represent, you say okay, a unit vector in one direction, a unit vector in another direction, and you can express them. Okay, so you can choose two vectors, and you can express them. You see, so x itna hai, y itna hai, this I, this is j, and all vectors in the two-dimensional space can be. So if your space of interest is two-dimensional, what you need is two vectors. Okay, and if they are orthogonal, it is very good. So orthogonal is like linearly independent. No, कोई contribution नहीं है ना. Okay, so one cannot be expressed in terms of the other. Linearly independent. Okay, so orthogonal it is better. Otherwise also you can take any two vectors. You see, and ऐसे ले लिए, उसमें भी तो express कर सकते हो. Okay, but then it will not be a unique representation. So if it is not a unique representation, huge problems you see. While the values may be correct, okay, but then how do you analyze? how do you key? You know, everywhere, so you need a unique representation, so linearly independent kind of works. Okay. And sometimes you say, okay, unit vectors, not only in these signs, but the length, the modulus should also be unit, so unit normal. Okay, so all those kind of things we use for a two-dimensional. Because we are looking at a two-dimensional space, the solution is also in two-dimensional space. So we say, okay, let fx is this. So many times that you have used this. You see, so if you have to find a vector, you say, okay, it is this times I and this times j. You have done that. For all imaginary things, complex analysis, you have done that. You see, a plus ib. This is the real part. This is I. This is another real part, and you try to find out a and b separately. Okay. So the same method, you see, of assuming that this is the solution and then trying to write whatever you know about the solution, all laws, all conservation laws, this, that, dissipation, everything has to be put there. Okay, and then the trick is again finding those. Okay. So many times have you seen in physics? Many times if you decompose around, let's say, an inclined plane, sometimes around the plane and perpendicular to it, the solution becomes easy. Sometimes in terms of gravity, horizontal and vertical, solution becomes easier. So it depends. You have that choice, you see, of the kind of functions that you choose. Okay, and you have those examples. You see, remember, motion down an inclined plane. You look at this and this. So the decomposition is in this and this direction along the plane and perpendicular to the plane. It's not in gravity and this. It's not like this. You see, so it depends. Okay, you can choose those. Why do you do that? Because sometimes it becomes easier to calculate. So this is using a basis function, okay, and a linearly independent one and a complete set. So that the complete solution, any solution, you see, any function that is in that dimension, you should be able to get it as a linear combination of those functions, okay, of whatever is in that box, okay, like a two-dimensional vector. Two-dimensional space, two-dimensional vector, a linear combination of I and j can give you that vector. So you are not precluding, or you are not saying that this is, we are only looking at some solutions, not all the solutions. So you are allowing it, whatever the answer may come out to be. Okay. So you okay. That is okay, straightforward. Linearly independence has two reasons, two major reasons. Okay. One of the reasons is, of course, it has to be a unique representation. What can be the second reason? And you have been taught all this. Whatever we discussed in the last 5 minutes has been taught to you. Am I correct? Do you remember, whatever we discussed? It has been taught to you. I didn't teach you anything new. It has been taught to you so many times. पढ़ाया गया ना? ऐसे करते हो, इग्नोर करते हो, I J करते हो. You do all those kind of things. Linearly independent में what other things do you get? Because this is a major trick, a slightly advanced trick, which is not there for, let's say, a 10th class student or a 3rd class or class 3 student, not 3rd class, no, class 3 student. Okay. Yeah. What is the benefit that you get if you have linearly independent?
Number of equation बढ़ता है. Number of equation बढ़ता है.
Minimum number of equations. So you are not looking at, let's say, extra number of equations. So you are only looking at whatever is an independent set. That's okay. X1. It has to. It's very similar to a unique representation also. So each type of unique representation. Fundamental, n equations in n variables. So it's over specified, under specified system. Repeated answers, these kind of unique solutions. You remember all those things that you made in algebra? Okay, matrix theory basically, system of equations, matrices. Okay. और क्या कर सकते हैं? लैपटॉप कहाँ है? पूछो लेट्स सी चैट जीपीटी क्या कहता है, लेट्स सी चेक करते हैं. तो फोन होगा, कहीं होगा, किसी का फोन नहीं है. फ़ोन नहीं यूज़ करते हो? No, it's a good sign. But like, I'm just trying to see what ChatGPT says about this. Linearly independent क्या होना चाहिए?
So first तो ये यूनिक सॉल्यूशंस,
देखो यूनिक सोल्यूशन आ गया. गुड.
सेकंड मैक्सिमल इंफॉर्मेशन कंटेंट,
यस, तो वो जो उसने अभिषेक ने बताया था.
फुल रैंक एंड इन्वर्टिबिलिटी ऑफ मैट्रिसेस.
ना फुल रैंक मतलब मिनिमम नंबर ऑफ इक्वेशन आ गए. ओके. इन्वर्टिबिलिटी थोड़ा सा डिफिकल्ट टॉपिक है. ओके. उसको समझना आसान नहीं है. ओके. So, do you really understand what it means to invert a matrix? But if matrix or inversion was a problem in itself, you said, okay, if this is not enough, let me add determinant also to that. Hey. Invert कैसे करते हैं? You know, not in terms of determinant or whatever. ठीक है, determinant का फिर you have to explain. Determinant is the rank of the matrix बताओ. ऐसे नहीं करना. अगर मैट्रिक्स इन्वर्ट कर सकते हैं तो सोल्यूशन एक स्टेप में मिल जाता है. ये मैट्रिक्स इन्वर्जन का ये मतलब. This is related to this, but इसको लेफ्ट हैंड साइड पे लाएंगे तो क्या होगा? जैसे चाहिए x, दुनिया भर की स्टोरी जान के हम क्या करेंगे? You know, if you need x, then a combination of x is not going to help me. So from a combination of x, if you want, you know, invert everything, तो एक स्टेप में आ जाता है. So you don't have to solve this kind of equations. So inversion से ये फायदा होता है. नहीं समझ में आया? ऐसे ही just an example पे कभी बोलोगे नहीं. Okay. Solution निकालना है एक ही स्टेप में आ जाएगा ना, इसको इन्वर्ट कर दो. दोनों तरफ both sides इन्वर्स से मल्टीप्लाई करते हैं. और आइडेंटिटी मैट्रिक्स चाहिए कहीं पे तो मैट्रिक्स एंड इट्स इन्वर्स दोनों को एक साथ ले जाते हैं. So, पर ये तो कहीं नहीं आया. You see, this ChatGPT doesn't tell you what I said is a higher order benefit of this, which you should know, because that is the key to lot of analysis. If you have that skill, okay. Or I won't say कि magical है, but bordering on magical तो है. Okay. So when you use this approach, you need to get the coefficients, क्योंकि linear combination of basis function है ना, तो दो coefficients क्या हैं? You know, the first function will have some coefficient, the second function will have some coefficient. Functions तो known है because I have chosen the basis. So the only way one solution is different from the other solution, or the solution is different from other vectors or other functions, is only in terms of those unique coefficients. So फिर तो coefficients ही पता करने पड़ते हैं ना. Let you know omega is a plus ib, a और b तो पता करना पड़ता है. These are coefficients of 1 and under root minus 1 और I. Okay. So coefficients पता कर देते हैं. इसकी ट्रिक ये है, जैसे ये लाते हैं ना x लेफ्ट हैंड साइड में, ओके. इधर एक फॉर्म ऐसा लाते हैं, और इधर तुम्हारे बेसिस फंक्शन. You try to get this form. You see, अगर ये फॉर्म आ गया तो सॉल्यूशन आ गया. Do you recognize this structure? मैथ्स जितनी पढ़ चुके, अब तो और नहीं पढ़ोगे. और and there is an instructor who says कि यार ये क्रिटिकल है एनालिसिस के लिए, और ये स्ट्रक्चर रिकॉग्नाइज नहीं कर रहे हो. in terms of finding the coefficients? Okay, who is able to do it? Who is able to yes? Not exactly. ठीक है, but that is another approach. That's not this approach. मतलब they are linked, but not this approach. और अभी थोड़ा और सोचोगे तो you'll find the answer. But if you have not seen this structure, then you have missed out on something. Okay? Because I'm sure this structure would have been taught to you. Okay? इसमें एक magic ये करते हैं, because this is a linearly independent and function तो infinite होगा. It is, function is like an infinite dimensional vector. ये मैं ऐसे ही passing में कह रहा हूँ, but this is a very good understanding of a function. Okay? The function is an infinite dimensional vector. Okay? तो इधर फंक्शन आ गया, linearly independent है, and a linear combination है. It is zero, and the only way it can be zero is when all things are zero, because here the zero हो नहीं सकता. Okay, so from one condition you get conditions on all the coefficients. Okay, from one condition for all the infinite terms you get the coefficient, you get the condition on all the coefficients. Okay, so you put n equal to 1. You say, okay, this is equal to 0, n equal to 2, this is equal to 0, and in general, this is equal to 0. इसमें coefficient होगा. Okay, so you'll get a condition for all the coefficients. So this is almost magical. You see, एक condition थी vectors, functions की, and you got conditions for all the coefficients. You see, ये magic है. You see, अगर linearly independent नहीं होगा तो नहीं होगी. Because linearly independent है, the only way it can be zero is coefficient is zero है. Trivial solution. Linearly independent का यही मतलब है ना. You see, अगर linearly independent, if this linear combination is non-zero, which means one of them can be represented in terms of the others. It's not linearly independent. ये कितनी बार use किया है? Okay. So, but do you now remember seeing this trick somewhere? हकीर यार, तुम तो ज्यादा पढ़ चुके हो, तुम बताओ.
देखा तो होगा, नाम याद नहीं आ
खैर तुम्हारा तो अभी टाइम बचा है. कितना टाइम बचा है? 1 साल,
रहा. हो गया सर,
3-4 months. ओके, जब डिफेंस होगा.
हाँ ये सर, जून.
चलो, इसका तो बहुत कम उम्मीद है. और कौन है? मोस्ट ऑफ द क्लास विल स्टडी फॉर अनदर 2 years. इसको पढ़ लेना. दिस इज अ मेजर थिंग. And this comes because of linearly independent. Okay, and this can be used. This technique is used so, whenever you are trying to find an answer, because the answer would be fx, the answer would be something that is multidimensional. Now I'm coming out of maths and I'm looking at finding a solution in any other problem. Multidimensional problem. Okay, the dimensions have to be chosen in a particular way, and you say, okay, this problem is dependent on these. Okay, and you write down all whatever you know about the problem. Okay, and then try to do algebra here, there, everywhere. इधर से खींचा, उधर खींचा, कुछ approximation दिया. Ultimately कुछ ऐसा ले आए. Okay, so the only way that can work is when all the coefficients are zero. Okay, and which means that you have a condition for all the coefficients. So एक physical reasoning से या simple math से you get a condition for all the infinite number of coefficients. ये match करें. Okay, और यही trick है. Okay. Can we say कि z में क्या कर सकते हैं? Okay, p के टर्म्स में लिख सकते हैं, b के टर्म्स में लिख सकते हैं, then p के टर्म्स में इधर रहता है, b के टर्म्स में 1/v के टर्म्स में होता है. You would have seen that, no? Virial equation of state. Okay, and 1 plus something करते हैं, because we are looking at the ideal one की deviation from 1 कितना है. You see, so if we know nothing, then we say okay, z is 1. Okay. You can do that. So दूसरा वेरिएशन है वो उसमें डाल देते हैं coefficients में, because there is a degree of freedom. So you see, you need to keep track of what is the degree of freedom. So that degree of freedom भी आ गई इधर. Degree of freedom उससे मिलेगी जो Gibbs phase rule. Okay, c minus p plus 2. n minus 5 plus 2. Okay, so you get the degree of freedom, pure substances, number of phases, all that has to be identified. Okay, and then you write down the whole thing and you say, okay, coefficients are not constants. I mean, the coefficients can be constants, or coefficients themselves can be functions. So ये कहते हैं कि whatever is the basis function, उसको लेना coefficient. So that is a mistake. You see, if you do that, then it's a mistake. Okay, a huge problem. You see, not that it can't be done, because you will still get the answer. Okay, a non-linear answer, but then it's not written in a proper way. So we say, okay, whatever is the volume dependence goes into 1 by V, 1 by V square, 1 by V cube, 1 by V4. The coefficients of all these 1 by V, 1 by V square, 1 by V cube, they are temperature dependent. Okay, let's say, or pressure dependent, depending, you know, the way you want to write. Okay, these coefficients should not be volume dependent. Otherwise, okay. Otherwise, you will have huge problems. You see, the major problem that you will face in mass transfer, let's say, something that you have done. I think you have done some mass transfer course, or you will do some mass transfer course. Usme there is a Fick's law. Something like this, and there is a diffusivity. So the worst case scenario is when the diffusivity itself is concentration dependent. You see, those problems are very difficult to understand. You see, so as long as whatever else is there, you know, goes into gradient of x plus gradient of x square plus gradient of x cube, all that is okay. That can be understood. You see. But if the diffusivity itself becomes composition dependent, then there is a huge problem. You see, those problems are not easy to see. Okay, because that effect is mixed, you see. So you don't know, you see, x idhar bhi hai, kahan se samjhoga? But if diffusivity is like this, like x dependent, if there is an x dependence which is not taken care of completely by, let's say, gradient of x, you say gradient of x square. That is a better representation in some sense. You see, somebody may say that you still preserve the equation and all that comes here, but anyway, that just in passing I said coefficients though nahi banana, because then the analysis is wrong and also physical understanding is also wrong, because you see something is here and you are worried about it and you only look at those things and say, okay, if temperature changes, this happens, if composition changes, this happens, if the composition gradient changes, this happens. Okay. And suddenly there is something else where also it changes. You see, the effect intuitively nahi samajh mein aata hai. You see, so then you run into trouble. Okay, so it is always good to keep these here. Okay, and then we also looked at how the power of 1. So if it is, you know, what this infinite series has to be evaluated first of all. If it cannot be evaluated, even if it can be evaluated, those expansion, you know, even though you have a rule to evaluate it, let's say, the ith term is given by this or the nth term is given by this, you're not going to sum the infinite terms. Even when you are going to evaluate it, you see, so analytically, it's a very interesting situation. Analytically, you know what the infinite series is, but numerically, when you are going to solve it, you know, you'll take finite number of terms, you see, and you will worry about the convergence. Okay, that so many terms are taken and we are very close to what the sum is. Okay, so all issues of convergence. Okay, so typically if this is the solution and I want to be close to this solution, and if that is specified, how many terms I need to take. You see, this is the problem. That this is the solution of this infinite series, I want this much accuracy, let's say 10%, 20%, 50% accuracy, then how many terms I need to take. So if that number of terms is 4, 5, 10, 20, you know, you should be able to find that, you see. And if those numbers of terms is infinite, then it's not a convergent series, you see. And then there is a convergence in Cauchy sense, where, you know, first 1, 2, 3 terms can give you the answer. Okay, so just to make sense of whatever, you know, how maths is involved in this. Okay, in a simple way. Okay, not in a very complicated kind of way. Now we come to another method for this. You know that another was talking about. Okay. Another way to handle these is, so what are those series? You see, x square, x cube, 1 by x, ln x, all those kind of things, you see. And then another kind of, so there are two very famous ones. You see, the one, there is a power series in terms of x, let's say. So you pretty much know what x is, what x square is, what x cube is, what x4 is. You know, some idea because we use it so many times. Okay, and straightforward also. But another would be that we take log of this and we do that, okay. Another is the Fourier series. You see, it's sine and cosine, or if you want to say exponential I kx plus omega t, you know, those kind of things. Okay. Why do you think, you know, I said this is a basis function. Power series is useful because the whole thing comes from expansion of functions in terms of a series basis functions. You see, all those power series things come from there. Okay, they can come from Taylor series expansion also, Maclaurin series also, but which is all, you know, the root is the same, but the way you study them. Okay, this is one. Why do you think, you know, what is so special about the Fourier series? Because you should know when you represent, you know, mathematically it is okay that it should be linearly independent, a complete set, and the trick of, you know, saying that, you know, ये जितना है उतने तो हैं, and this set, whatever is missing, we say it is also deemed to be inside this set. You know, so kind of, समझ रहे हो तो कि ये जो डीम वाली चीज है, you know, डीम से डूम बहुत दूर नहीं है. Okay. So all this, but it's a trick. जो नहीं होता उसको डीम कर देते हैं, इसी रुकते नहीं है ना, आगे बढ़ जाते हैं. If you want to execute something, एक स्टेप पे रुक गए, कंप्यूटर तो है नहीं, इंसान है, हमने कहा यार इसको छोड़ देते हैं यहीं पे, डीम टू बी दिस, इसको 3 ले लिया, खत्म करो, आगे बढ़ो. ओके, एक प्लेसेस ऑफ वर्शिप एक्ट बना दिया, ये तुम्हारा, ये तुम्हारा, ये तुम्हारा, ये तुम्हारा, खत्म करो, आगे चले. समझ रहे? ये सब डीम्ड ही है, अदरवाइज क्या था यहाँ? कुछ भी नहीं था. यू नो, कुछ सेल्स घूम रहे थे कॉस्मिक डस्ट में, उधर से कुछ केमिकल्स थे, कुछ थे, इधर बन गए, सब इवॉल्व हो रहे हैं, लड़ रहे हैं, अच्छे से लड़ रहे हैं, वेपन से, पैसे से, हर तरह से, साइकोलॉजिकल लड़ाई हुई है. बट very frequently, you know, just because, you know, we are moving towards, I may not teach you again, you see, maybe 4th year. Okay. Of course, yes, in 4th year. कोई भी वॉर होता है ना, लगता है कि ये प्राइज है, and we are fighting. War is for that prize. Okay. ऐसा मतलब राजपूतों के समय में होता था, 500 साल पहले होता था, ऐसा तब भी नहीं होता था. कोई भी लड़ाई जो है, जो सामने प्राइज होता है उसके लिए नहीं होती. ये थोड़ा सा तुम्हारी जनरेशन का गेम है. ओके, तो ये लड़ाई होती है फॉर सो मेनी रीजंस. ओके, और चाइनीज ने तो बुक्स भी लिखी हैं इसके ऊपर, आर्ट ऑफ वॉरफेयर एंड एवरीथिंग. बट ऐसे छोटे से समझा देते हैं, लाइक दीज मैथमेटिकल बुक्स भी बहुत सारी हैं. यू नो, पूरे मैथमेटिक्स डिपार्टमेंट ऑल ओवर द वर्ल्ड आर काइंड ऑफ डूइंग दिस. हमने तो एक छोटा सा अप्लाइड वे में समझाया. वॉर में भी जो सामने दिखता है ना, वो नहीं होता कि ये प्राइज है, प्राइज कुछ और ही होता है. और ज़्यादातर जो वॉर है वो इसलिए होते हैं कि पीट के तुम्हें यहाँ बैठाएं और फिर नेगोशिएट करें. You see, war is not to kill you. The war is to get you onto the table on our terms. Okay? So war is to weaken you, to force you to come to the table so that we can discuss on our terms of the things that is not even clear when the war was going on. You see? तुमको इसलिए अगर पीट रहे तो इसलिए थोड़ी ना पीट रहे हैं कि टेबल पे बैठा के और पीटेंगे. पहले तो पीट रहे हैं, टेबल पे आओगे फिर कुछ और मांगेंगे ना. तो लड़ाई उसकी थी, पीटने की थोड़ी ना थी. ये टैरिफ वॉर है, जस्ट टू गेट यू इनटू दिस. ये टैरिफ कोई इतनी बड़ी चीज़ नहीं है कि हमने इतने का दिया उतने का दिया. अरे टैरिफ क्या है? एक ट्रेड डेफिसिट है यार, किसी से सर्विस लोगे तो ट्रेड डेफिसिट बहुत हो जाएगा. यू नो, वो तो कुछ दे नहीं रहा है, आप ही पैसे दे रहे हैं उसे. बट इज इट बैड, इज इट गुड? ये सब कुछ नहीं है. ये सब और कुछ बड़ी कहानी है. ओके, सो ऑल ऑफ यू शुड ट्राई टू थिंक कि होगा क्या इससे. ओके, और हो क्या रहा है. Okay, so this is a problem for your generation which keeps on changing every 6 months. Because last time I was teaching some students, I said, this is the problem of your life. अभी इधर आया हूँ तो इस कोर्स में I see some other problem in your life. जी, ऐसा हो रहा है. Even the problems keep changing every 6 months. You see, I've been teaching for after a day. This is the third course. Every course the problem has been very different. तो कि क्या हो रहा है सोचो. Sometimes I feel so happy कि I've lived my life. Okay. So this will keep on changing, which means that all of you have to be fit, all of you have to be smart and kind of keep working. इसका क्या importance है? Fourier series. Anybody? अरे यार Fourier series पढ़ाई जाती है. Fourier heat transfer का लॉ है. ये पढ़ा रहे होंगे. मोहन ने पढ़ाया होगा. Fourier law of heat conduction, न्यूटन्स लॉ ऑफ कूलिंग, ये सब पढ़ाया होगा. डीटस बोल्टर इक्वेशन, ये सब पढ़ाई. कोरिलेशन भी पढ़ाए होंगे. इधर तो कहते हो नहीं पढ़ाए. ये सब इतना हीट ट्रांसफर होता रहता है कर्व चीज़ों में, इधर उधर फ्लो में. ये सब कोरिलेशन से ही सॉल्व होता है. किसी के इतनी दम नहीं है कि उसको सॉल्व करे पूरा कि इतनी हीट गई. कंडक्शन नहीं है, इधर हीट लेके वो भाग जाता है फ्लूइड. ओके, वो भाग जाता है, फिर पता नहीं चलता कितनी ले गया. कोरिलेशन से फिर भी पता चल जाता है. और सिर्फ भाग जाए तो भी ठीक है, वो लौट के फिर आ जाता है. जी, ये मेजर इश्यूज है हीट ट्रांसफर में. लेता भी जा रहा है और कितनी भी ले सकता है. मास ट्रांसफर तो इन दैट सेंस इज स्लाइटली बेटर, रुकेगा तो कहीं. हीट में तो कितनी भी लेता जाएगा. तो दैट्स व्हाई यू आर डूम्ड टू हैव कोरिलेशंस है. तो कौन सॉल्व करने जा रहा है इस तरह के उसमें फ्लो में. अभी ये फ्लूइड आगे जा रहा है, फिर ये फ्लूइड पीछे हो जाएगा, फिर ये फ्लूइड नियर द सरफेस है, फिर ये फ्लूइड उधर है. यार कौन इतना सब करेगा. सीधे सीधे कोरिलेशन देख लो. ओके, सो एनीवे, सो फोरियर तो इतना बड़ा फोरियर, इसका नाम इतना क्यों है. अभी भी फोरियर सीरीज यूज होती है वेरी वेरी एडवांस एनालिसिस. क्या रीजन है. कभी भी कोई चीज अगर लॉन्जेविटी है किसी चीज की, तो योर जनरेशन शुड लुक एट दैट. There has to be a reason why something has been there. That will give you a belief. ये एक अच्छा मेथड है लाइफ में. If something has survived so long, तो देखो कि क्यों, क्या था उसमें, क्या अच्छा था. Why has it survived? 5000 साल से हम हैं, समझे. कभी सोचो कुछ अच्छा होगा तभी हैं. समझ में आया. 500 साल में कुछ नहीं हो गया हमारे साथ. 1000 साल कह दो, 500 छोड़ दो, 1000 ज़्यादा ही नेशनलाइज हो जाओ. या 10 साल कह दो. जो तरह तरह के यू कैन चूज, कितना हिस्ट्री में तुम किधर जाते हो. 10 साल, 70 साल, 300 साल, 800 साल, 1000 साल, जितना कहना चाहो. डिपेंड्स ऑन यू. लेकिन ये तो देखो कि जो सर्वाइव कर रहे हैं उसमें क्या था. फोरियर सीरीज हैज इट नॉट अकर्ड टू यू कि क्यों सर्वाइव कर रहे हैं. क्या डिजाइन थी उसमें. एनीबॉडी. या इंटरेस्टिंग है. वुड यू बी इंटरेस्टेड इन नोइंग व्हाई इट हैज सर्वाइव्ड सो लॉन्ग. सर यूनिवर्सिटी है, सर इतना पढ़ाते हैं, सर इक्वेशन चाहिए, कुछ तो चलेगा ही, यही चल रहा है. और नाम भी अच्छा है सुनने में ना, फोरियर. ये इतना बड़ा नाम है कि हीट इज फोरियर. You know that in French. See, जो oven होता है ना, it's called a four. सही है ना. तो क्यों होता है ये. इसलिए होता है कि अगर n, what you do, you do any analysis, so one of the method is that you work till this point and you say okay, इसमें मजा नहीं आया, एक और टर्म ऐड कर लेते हैं. यही तो कर रहे हैं. इनफाइनाइट सीरीज में से पहले 100 टर्म्स लिए, 20 टर्म्स लिए, 50 टर्म्स लिए, 4 टर्म्स लिए, कितने ले लें. You see, so adding each term, you'll get some more accuracy. And when that incremental benefit is not beneficial in economics, वो कहते हैं नहीं अब इतना ही करेंगे और नहीं जाएंगे, ज़्यादा पैसा लग रहा है ना, करने में बेनिफिट कम मिल रहा है. Okay, कन्वर्जेंट सीरीज में यही तो होता है ना, we can keep on adding more terms but वो तो जाते जाएंगे, बेनिफिट मिल नहीं रहा है. So it is very very common in all numerical methods. जैसे numerical methods में भी if you get some solution, you should always change the grid size and run the scheme again and get a solution. And if both the solutions are not very different within acceptable limits, you say okay, whatever I have chosen is correct. It's called a graded invariance. Okay. इधर भी होता है कि if we take 8 terms or if we take 10 terms, अरे convergence में कितना कैसा प्रूफ था वो, Tn minus Tn plus 1 का डिफरेंस दिखाते थे कि कम होता जा रहा है within. You remember that? एक टेक्निक थी ना, Tn plus 1 minus Tn depends on n, और वो डिनोमिनेटर में n है तो कहते तो छोटा होता जा रहा था जितना लोगे, कन्वर्जी कर रहा है. वन ऑफ द मेथड्स. ओके, तो इसमें भी which means कि you will have to frequently, not frequently, almost always, if you are analyzing something, you'll have to look at the answer with n number of terms and probably 2n number of terms or n number of terms and more than n number of terms. ये तो करना पड़ेगा क्योंकि अप्रोक्सीमेशन है. अगर एनालिसिस कर रहे हो, if you are not computing, तो it is an approximation. How many terms you should take? Okay, this is, so you'll have to do it. If you are doing simulation, फिर तो imperative है कि कोई ग्रिड साइज लिया हो, ग्रिड साइज आधा करके फिर करना पड़ता है. You see, which means करना पड़ेगा. What is that in the representation or what is that in the coefficient that can help you a lot? That is the deal breaker when you choose the basic functions. What is the deal breaker? मैं उसकी उस पे जा रहा हूँ ना, फिलोसफी पे, कि हाउ टू चूज द बेसिस फंक्शन. क्योंकि z निकालना है. अब z तो बहुत तरह से निकलता है. विजुअल इक्वेशन ऑफ स्टेट है, एक टॉकीर इक्वेशन ऑफ स्टेट आएगी. ओके, आ सकती है डिपेंडिंग ऑन योर सिचुएशन. ओके, एनीबॉडी, क्या बेनिफिट दे दें तुम्हें if you want to evaluate something with n and also evaluate something with 2n, or let's say n plus 5 or n plus 10. So what is that which will be the deal breaker, or what is that benefit if you have will help you? मतलब एक पेन पॉइंट है ना यार, ये किया फिर से करो. कंप्यूटर करता है फिर भी तो कुछ तो कार्बन कहीं जलता है, टाइम जाता है. ये अगर टर्म्स कैंसिल करते हैं तो बहुत ट्रिकी सिचुएशन है. इट्स लाइक हैविंग अ वेरी सोफिस्टिकेटेड वेपन. सो टर्म्स कैन कैंसिल इज गुड बट इट्स अ वेरी डेलिकेट थिंग टू हैंडल. उसमें ये होगा कि ऑड में कितना है, इवन में कितना है, दोज काइंड ऑफ इश्यूज विल आल्सो कम. और टर्म्स कैंसिल कर जाएंगे तो इट इज अ गुड सिचुएशन बट वेरी ट्रिकी, नॉट इजीली मैनेजेबल. ओके, और एंड यू विल मेक मिस्टेक्स क्योंकि उसमें डिपेंड करेगा ना कि किससे कैंसिल कर रहा है. सो इसको इससे कैंसिल करना है पर तुमने कितने टर्म्स लिए, हाउ डू यू नो द पैटर्न. बट कैंसिल कर दिया, दैट्स अ गुड सिचुएशन, इट्स अ गुड थिंग. दूसरा,
इससे तो कोएफिशिएंट्स
सर कैंसिल हमें तो नहीं करते हैं. फोरियर सीरीज कभी ऐसे तो नहीं लेते कि सब में कैंसिल करें. इन जनरल ले लेते हैं, कोई भी फंक्शन होता है कहते हैं फोरियर सीरीज में डाल दो. फोरियर कोलोकेशन है, मेथड्स हैं, स्पेक्ट्रल कोलोकेशन मेथड्स हैं, और सिग्नल के एनालिसिस में फोरियर सीरीज यूज होता है. कितना यूज होता है, फोरियर ट्रांसफॉर्म होता है, फोरियर इंटीग्रल है. ये ओवन को भी फोर कहते हैं. कम्स फ्रॉम दिस फोरियर फेलो ओनली. ओके, कितने लॉज होंगे, ऐसे सोचो कितने लॉज होंगे कि न्यूटन्स लॉ ऑफ कूलिंग, उसके बाद भी एक फोरियर लॉ ऑफ हीट रिडक्शन है. ऐसे न्यूटन जैसा कोलॉसस जो भी किया सब कर दिया. जस्ट इमेजिन कि कुछ तो फोरियर में होगा. ऑफ कोर्स सभी में था कुछ कुछ. तो ये इतनी दिन चल गई. क्या बात है कि हस्ती मिटती नहीं हमारी। सुना है? नहीं सुना? तुम तो आजाद भारत में जवान हो रहे हो, तुम बड़े हो रहे हो, एडल्ट हो रहे हो, तुमने नहीं सुना, हमने नहीं सुना तो समझ में आता है। दबे रहते थे 90 तक तो मैं बड़ा हो गया, ऐसे सोचो ना, पढ़ाई हो गई पूरी जब लिबरलाइजेशन हुआ। उससे पहले तो मेरी सारी पढ़ाई पूरी हो गई। लिबरलाइजेशन तो उसके बाद है। क्या बेनिफिट मिलना चाहिए? आई एम नॉट इवन आस्किंग अ क्वेश्चन अबाउट कि फोरियर को क्या बेनिफिट मिला या फोरियर सीरीज में क्या बेनिफिट है। तुम्हें क्या बेनिफिट चाहिए कि तुम्हारा काम आसान हो जाए? एंड इफ यू हैव टू डू इट, यू नो द क्वेश्चन इज यू हैव टू डू इट फॉर ऑल फंक्शंस, एनी प्लेस, यू सी, तभी होगा ना। अगर इफ इट इज ओनली यूजफुल फॉर अ नीश, जैसे वो कह रहा है कैंसिलेशन हो जाए, देन इट विल हैव अ लिमिटेड यूज, यू सी। ये मास मार्केट में चलना चाहिए ना।
सर
क्या पेन पॉइंट है?
जो कोएफिशिएंट्स का ऑर्डर ऑफ मैग्नीट्यूड है वो आई थिंक अगर हर कोएफिशिएंट का ऑलमोस्ट सेम रहे सो आई थिंक वो कन्वर्जेंस में हेल्प करती है।
इन अ वे अगर सिमिलर हो,
यस
मतलब तरह तरह के मेथड्स, एटलीस्ट यू आर थिंकिंग, यू सी। तो इफ यू हैव एन हाइपोथेसिस, इफ यू आर थिंकिंग, you will think it through, you may converge on some result or you may not converge, but at least you have tried. Okay, फोरियर सीरीज में सबसे बड़ा बेनिफिट होता है कि अगर n तक कैलकुलेट कर लिया और अगर 2n तक कैलकुलेट करना है तो ये पहले वाले n नहीं करने पड़ते, इसी कोफिशिएंट्स, सिर्फ जो नए कोफिशिएंट्स होते हैं वो करने पड़ते हैं। ये बेनिफिट है उसमें। बाकी अब बहुत सारे, इफ यू लुक एट मेनी अदर काइंड ऑफ एक्सपेंशन बेसिस फंक्शन, अ फंक्शन इज रिप्रेजेंटेड एज 1 + x। तुम फिट करके देख लो किसी डेटा में, अ फंक्शन रिप्रेजेंटेड एज a + bx, okay, you will get some ab, okay, and a function represented as a + bx + cx square, you will not get the same ab. See that those a and b will be different, which means, and you have to definitely fit for a and b. ऐसा नहीं है कि a + b, a + bx + cx square करना है, ओके, एंड ab पहले से ही निकाल लिया a + bx से फिट करके, ओके, और सिर्फ c निकाला बाद में, यू नो, नहीं कर सकते। यू हैव टू गेट a, b and c अगेन, ऑल थ्री। मैं सही कह रहा हूँ? फोरियर सीरीज में नहीं करना पड़ता है। फोरियर सीरीज में अगर 8 टर्म्स तक कराए and now you want to do it for 16 terms, तो पहले वाले 8 प्रिजर्व हो गए। You have to do it only for 9, 10, 11, 12। कितना बड़ा बेनिफिट है? Do you see that benefit? Whenever you are estimating those coefficients in so many exercises that have been given to you while teaching, you know, Fourier analysis, did it occur to you कि ये जो हम निकाल रहे हैं ये independent है of the number of terms taken to represent? You see, ये major benefit है, and this is one of the benefits that because of this, you know, Fourier is so much used. It's still used. कितनी करनी है? Otherwise पूरे निकालने पड़ते फिर से, like in a power series, you see. So ये हुआ. I'll take 2-3 more minutes to complete this. What are the places where you should not use a Fourier series? ये भी तो होना चाहिए। फोरियर सीरीज यूजफुल है, इतना है, मासेस में है, सब फंक्शन में होता है, कुछ ऐसा होना चाहिए जो कि वेयर यू शुड नेवर यूज अ फोरियर सीरीज। एनीबॉडी? मतलब इज इट अ गुड नॉलेज टू हैव दैट आई वुड लाइक टू, यू नो, मॉडल दीज फ्लक्चुएशंस। ये फ्लक्चुएशन है, फोरियर सीरीज से मॉडल किए, साइक्लिक होंगे, ये होंगे, जो दुनिया भर की थ्योरीज है, यू नो, इकोनॉमिक्स में नोबेल तक पा गए लोग ये सब करके, ओके। हर जगह तो यूज नहीं हो सकती, कहाँ नहीं यूज होनी चाहिए? इफ यू हैव दिस इंफॉर्मेशन, विल इट हेल्प यू? ऑफ कोर्स कंप्रेसिबिलिटी फैक्टर के टर्म्स में पढ़ाया, बट दिस इज अ जनरल अंडरस्टैंडिंग। एंड मतलब गिब्स का एक वो है, जो अपने thermodynamics वाले Gibbs है ना, he has done lot of things in maths also. So there is a Gibbs approach, and that kind of tells us. Okay, इसको Gibbs phenomena कहते हैं. So there is a Gibbs phenomena in function analysis. If you encounter flat portions in any function, okay, flat portions in any function, then you should not use a Fourier series, because the number of terms that are required in a Fourier series to approximate a flat surface is very high, and you cannot take that. You see, वो oscillate ही करता रहेगा. So you see, so two situations. One is you should never, if you see flat portions, so you know, flat portions, so Fourier series is no good. You see, in fact, it will lead you to lot of trouble. It cannot approximate. So पहला problem तो ये हो गया. दूसरा है, in lot of places where there is a threshold, okay, because a Fourier series will always, you know, give you a wave. Wave means that you will be above the mean and you will be below the mean also. So you will have a positive deviation from the function as well as a negative deviation from the function. This is by nature, you know, in a wave. You know, ऊपर भी जाएगी, नीचे भी जाएगी. So any function has to be approximated. So it will kind of underestimate the function and it will overestimate the function. If the function represents a threshold and the behavior, a critical threshold, behavior on the top is different, behavior on the bottom is different. Okay, and which is very frequent, you know. Fourier series से approximate कर लिया, कभी ऊपर जा रहा है, कभी नीचे जा रहा है, ऐसा है तो नहीं. You see, so इससे directly you will not know what the behavior would be. So in two situations, a critical threshold, Fourier series doesn't have to be used. A flatter portion, Fourier series doesn't have to be used. Otherwise, very few number of terms can represent any kind of wavy behavior, cyclic behavior, any kind of wavy curve, this kind of behavior with Fourier series. You see? So, इसको खत्म करते हैं अभी. Where is the answer sheet?
So flat surface potential, flat surface.
Gibbs phenomena. Gibbs phenomena और क्या? Flat surface Gibbs phenomena. Okay. Sheet. फोटोग्राफ ले लें, क्या करें? सबका नाम लें तो लोग आगे करें से. मैम आ रही है नहीं? किसके पास है? सेल्फी का आ रहे होंगे. फोटो ले लेते हैं. इज इट ओके? चलो सब लोग साइन करो. इधर देखो सो मत. थैंक यू. एक इधर भी ले लेते हैं. And if the number is more than 70, 80, तब फिर नहीं करेंगे. Then वो कहाँ है शीट? मेरे पास है.
निशान भाई इस वक्त का
सर्दी वर्दी हो गई है मुझे.
अच्छी ले ना, कल तक भेज देना ना.
सर्दी मुझे भी
अरे मेरा क्या
मल्टीपल टाइम से होता है. सर्दी में तो नॉर्मल खांसी होता है, पेनफुल खांसी. आप अवॉइड कर लो, क्योंकि आप अभी हॉस्पिटल दिखाओगे वहीं पर चले जाओगे. लास्ट टाइम क्या होता है, मेरे पैर में फ्रैक्चर हो गया था. ट्रेन 3 में गया था, लेकिन नहीं करी थी कि जाने से पहले स्मोकिंग कर ली. उन्होंने जब पेन किलर दिया
तो काम नहीं किया उतना.
तो मैं हॉस्पिटल आई. तेज नहीं यहाँ पे, तो इसको बुलाना पड़ा था, क्योंकि बोले थे गार्डन लाएगा, इसके बाद मैं छुट्टी देंगे. उन्होंने CPR दिया था मेरे को. मेरा हार्ट फेल हो गया था रात में. उन्होंने बिना BP चेक करे पेन किलर दे दिया. उनको लगा कि मैं फिट हूँ.
नॉर्मल सुट्टा मार के तुझे वो हो गया.
अरे हुआ क्या था कि उनको लगा कि पेशेंट है, स्मोकिंग करके थोड़ी एम जाएगा.
गांजा फूक
नहीं,
चल चल आजा नीचे. ऑन द वे. तू तो डरा रहा मैंने ऐसे लापरवाही करी मैंने कुछ किया नहीं हाँ यार अब तो वही करना पड़ेगा बहुत ज़्यादा अजीब हो गया यार सर और दर्द हो रहा है बहुत ज़्यादा फीवर आ रही है हाँ फीवर और क्या सेंटर चलते आज 5 बजे के बाद अबे 6 बजे से मेरा रिमाइंडर है MTL का यार ठीक है जाना इस संडे चलेगा 8 बजे सैटरडे भी फ्री है हाँ क्लास के बाद आओ ठीक है ठीक है
चेंज कर दिया आज पकड़ेंगे लास्ट टाइम ये किया था ना तो भी कहा था किसी को पकड़ेंगे लास्ट टाइम पकड़ा भी था वो बंदा लेट आया उसने सुना नहीं कि पकड़ेंगे इसलिए तो पकड़ा ये होगा अगर वो सुन लेता ना तो पकड़ा नहीं जाता आज भी किसी को पकड़ेंगे What date is today? For elections.
Okay, quiet please. So we have a quiz today, and that's for 30 marks, and there's a sheet that will be kind of circulating, and you have to enter it, one after the other. Okay, so don't have to skip. Okay, so that if I find someone has skipped, that person can be marked absent or whatever. Depends on how things unfold. We don't know. Okay, so please be careful when you mark your attendance. Okay. So we were looking at pure, and we said T, 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 U, H, C, P, C, V, Q, and W, and composition, and number, phases. Come in quickly. Abhishek Bachchan. Okay, so do we have everyone here? Mic. Please pay attention. Quiet. Keep saying this all the time. The exam paper should look like, how many meanings can you give to quiet? That can be one of the questions. How many times, I have said quiet in this class? So you have to, very fair question. So please, listen to this. This is the most critical one because we will do a lot of things in 2 lectures. Okay? And there is no, you will not visit them again. Okay? So because there is no other course where you do it. So looking at pure, we're looking at, let's say, ideal, non-ideal, real, processes, reversible, rest of the process. We have had that discussion. Okay? Now we look at pure, and we need to maybe look at all of these. And we kind of figure out, how pressure changes with temperature, how temperature changes with pressure, how volume changes with this, that, and everything. Quiet. क्या बात है? क्या लिखा है? Can you read whatever is written here? सीधा पहना है उल्टा पहना है? Yeah, there's a bully, trapped inside. Just kind of held together because of so many years of education. तुम लोग सब सुनते ही नहीं हो. मनोज क्या तुम्हें क्या हो गया? तुम सामने सामने सुन ही नहीं रहे हो। ये तुम यहाँ बैठे थे वहाँ चले गए। हाँ? Focus on this, when you miss out on several things that I say, and that kind of shows up in your exam also. Simple things that you miss. So, आयुष तुम तो फोन पे बात कर रहे हो, मतलब लिमिट हो गई। तुम गेटकीपर हो इधर। तो आगे ठीक है यार, he needs some help, he needs friends, he has friends। ये सुनो तो क्या हो रहा है? मैं जोक कर रहा हूँ क्या इधर? I'm trying to teach something that is kind of the trickiest part. अब वो देखो, ये देखो, शशि कुमार बात करते जा रहे। I mean, क्या creature of habits? ये कितना सही है? बस हो गया। अब will not let enter, तुम देखना। Okay? कोई भी आएगा, we just अब नहीं आएंगे। कहाँ? मुझे दिखता नहीं। Just Owens। एक गलती हो गई, बंदा को इतना पकड़ लिया यहाँ से। अब come back to this. There's a trick. There are lots of tricks here. Otherwise, you'll kind of see what will happen is, and I've gone through it many times, and I've seen other people also go through it. What will happen is that there will be all kind of calculus and computations and things, and you can do them. They're not very difficult mathematically. Okay, but you'll never be comfortable with them because whenever in, let's say 2 years from now, something will come, and then you'll have to study the whole thing again. So you'll never be comfortable with all those thermodynamic calculations. You see, that is the problem with thermodynamics and the way it's understood and taught and learned. ये तुम नहीं आओगे? अब हो गया क्या? आप जैसे भी क्लियर हो गया क्या? टाइम नहीं वेस्ट हो गया। सच में हो गया यार, डोंट टेक मी। और ये प्लीज क्या नाम है? आपका क्या नाम है? पूर्वी। तो निशांत एंड पूर्वी will be allowed to sit, but they'll not be allowed to mark that image. तो तुम लिखना शुरू करो। फकीर, निशांत, पूर्वी, एंड आपका क्या नाम है? अनन्या नाम है इसका? पक्का? Can somebody vouch? No, अच्छा, you go. Okay. So Ananya, Purvi, and आप क्लास नहीं करेंगे? देखो मनुष्य, ये सब पढ़ाई का मंदिर। 30 marks। अटेंडेंस नहीं है, आएंगे नहीं। आगे चले जाएंगे, एक एग्जेप्शन दिया गया। फिर भी Right. So 3 लोग हैं, फकीर 3 लोग हैं। कौन 3 लिखे? Okay. निशांत, पूर्वी एंड अनन्या। कोई और भी है? गुप्ता, इसका क्या नाम है? आगे वाला नाम भूल गया। अमोल। यस, अमोल। तुम अंदर बैठ सकते हो, बट अटेंडेंस नहीं मिलेगी। देखो ये पूर्वी, लुक एट दिस। आप तो फोन देख रहे हैं। Hundreds of hours of hard work have gotten you here, and thousands of hours of hard work has gotten me here. You see, ये आके जो है, we are just kind of not happy with each other. ऐसा मतलब इतना inefficient process है ये पढ़ाई। Focus on this. So we just say what do we need, because there are thousands of things that we can have here. Okay, so we are worried about how each of them changes. What is Q, what is W, okay, and X and all of this. Okay, so how V changes, how other things change. So there is a trick to that. So first you identify, what you need. So let's say we want to, and one of the things would be how volume changes. Because इसका नाम भी लिखो ताकि क्या नाम है इसका?
गणेश
गणेश. यस गणेश. जैन. आरव जैन. अभी सवाल नहीं पूछेंगे क्योंकि दैट लीड्स टू हार्ट ब्रेक एंड फिर मूड नहीं रहता पढ़ाई का. सो आई मे विन बट आई हैव नॉट एक्चुअली वन. किसी को पनिश कर दिया इधर क्या सीखेगा, इससे अच्छा तो बाहर ही चला जाए. ओके. सो इसलिए ये जो अब लोग आएंगे उनके नाम नहीं पूछेंगे, उनको जैसे नाम पूछेंगे, ये बताएंगे नहीं क्या होगा. So good. So we say, okay, we first figure out what variation is what are the things that we are interested in. So let's say volume is one of the things. For example, let's say entropy can be one, enthalpy can be one, internal energy can be one. Okay. So how V changes with T and say all other things. Okay. So which means we need something like this. Okay, we all understand this, we need to know this, and maybe many things are kept constant. So what is that?
The first word.
B changes.
V changes.
B is the volume. So we generate this first. Okay, or we can generate a lot of other things also. So we can say this U by T and lots many other things. Okay. But we first say this, we remove this so that we don't confuse. Okay. We look at the degrees of freedom, which means that this has to be accompanied by another partial derivative, because these partial derivatives will come as on the right hand side of a total derivative. Okay. And total derivative we can then work. Okay. So let's say the easiest one, as I said, it's given in the book also, but maybe not like this. So we have this. Okay, so we choose two, and this is also related to how you generate lot of other equations. So this trick will be useful. So you generate this pair. It's a kind of pair. So once you have this, then this partial derivative would get t here, and this would get t here. Okay, this will come for consistency. And this is, देखो ये दो दाढ़ी वाले बात कर रहे हैं, चश्मे वाले, और ऐसे मुल्ला की तरह दाढ़ी ये चूरे और बात कर रहे हैं. क्या हैबिट्स हैं, मतलब सुधर ही नहीं रहे. सुधर जाओ. जैसे फोकस ऑन दिस, कुछ ट्रिक सिखा रहे हैं यार, अगर नहीं सीखनी है तो भी सुन लो. डोंट डिस्टर्ब. वो देखो उधर भी बात होती है, वो देखो आराम से बातें हो रही है. और अब 3 लोग हो गए, एंड और लोग बढ़ते जाएंगे उधर. अब इधर भी जगह नहीं है ना, काम भेजेंगे उनको. Quiet, we are looking at, let's say, first of all, we say how volume changes. Okay, so volume changes with temperature. We got a partial derivative, and we say, okay, एक और partial derivative चाहिए. So the easiest one in this case is, let's say, pressure. Okay, but they can be anything. You see, any other potential, G, H, entropy, whatever you want to put in, that can be there. Okay, and in thermodynamics, just like this, but in any other system, what we want to analyze, this can be some other things also. So, but you have to be very clear about how many degrees of freedom are there. Okay, so let's say in this case, we have this, and these two have been put in, and this is the major change. You see, otherwise, when you say that there is a partial derivative, means everything else is kept constant. In this case, also everything else is kept constant, even in the sense that you say P is constant. So this derivative when P is kept constant, specifically, okay, this partial derivative when T is kept constant. It is not the same as this and S is kept constant. It's not the same. Okay, when you want to, so this with T kept constant, this with S kept constant is not the same. You see, that also TVS is also one combination. Okay, so you have to be very careful about what is kept constant, and this kind of thing, you will revisit this many times. You see, that whenever you are analyzing a system, you need to, and you have chosen, that I am going to represent my system by this, and you have lot of options of of representing your system in many different sets. So you need to be very careful because you have chosen, you have made a decision that this system is defined by this, this, this. And once you have done this, just a plain partial derivative is not going to help you. You need to specify what else is there. It has to carry that information, otherwise that information is lost. So once you do that, it is there, and now the trick would be that we say, okay, this is there, but all of us have done enough of those things where we have done with where we have looked at errors, and we say errors in absolute sense may not do not make that much sense. So you need to look at relative errors. You need to look at percentage changes. You need to look at relative changes. So this is fine, but you see something like this. Okay, and you need something like this. Okay, so this is what you are looking for. Okay, so you see, we construct this first, that this is what will help you, because this itself, this will give us how volume changes when temperature, fine, when pressure is kept constant. How volume changes with pressure when temperature is kept constant. But we divide by V because that gives us a better control. Okay, even though V itself is the molar volume. You see, it's a specific volume. It's not just some total volume. It's a specific volume. Let's say in this case molar volume. Okay. So are you going out? You're not allowed to go. इसका क्या नाम है? नाम बताओ? Kshitij. So if Kshitij doesn't come back, then Kshitij will lose all attendances. So we construct this first, and now we need to find these in some equation. Okay, some way. We need to convert this to some delta. Why some delta? Because we know we can get values here, we can get values here, because that's the only thing that we have. In real sense, you see, we can measure things. We can measure things at this state. We can measure things at this state. So we need to, if we can relate all of this to some difference or some measurement somewhere, you see, and then only it makes sense. Otherwise, even if we get them in a form of an equation, ये अभी आए हो कि पहले आए थे? इसका क्या नाम है? अक्षय. अक्षय भी लिखो. बैठ जाओ. ये गेम चल रहा है. क्या होता रहता है? But it's not over yet. There is something else also that you need. Okay? We try to keep things. This is a bias. Okay? That we say, okay, we'll keep them in a way that is positive. Okay? कितनी बातें होंगी? तुमने इसीलिए एंडोर्स किया था कि इनका नाम अनन्या है, so that यहाँ बातें हों. Okay? तो मत करो ना, please. Okay. So we kind of keep things positive. You see, that's also one of the. It's a bias. It doesn't. It's neither here nor there. You see. It could have worked both ways. Lekin positive kind of helps. सोच ऐसी है, positive रख रहे हैं. So इसमें what do you think? Is this by itself positive? Again, positive. Temperature बढ़ाया, volume बढ़ी, महंगाई बढ़ी, क्रिस्टल के अंदर बंद है. फिर क्या करोगे? Negative तो नहीं होगी. हो सकती है. Can this be negative? अरे हो सकती है, फेस चेंज वगैरह में हो जाती है, आइस में हो जाती है, but this is by itself positive. Okay, क्षितिज आ गया, उसका नाम काट दो. इसमें what do you say here? This by itself is likely to be negative. Okay, so we say this is not the best representation. We should put a minus, unary minus. Okay, not as in subtraction, but a unary minus, which means whatever it is, it comes a minus. So these are the things that we need to estimate, and unless we are able to estimate these things, we will not know how volume changes. Okay, and if we don't know how volume changes, What is the biggest problem that will come? Can anybody tell me? If we don't know, if we do not have control over volume changes, what is the biggest problem that can come? वर्क नहीं पता चलेगा, द वर्क डन नहीं पता चलेगा. वर्क डन नहीं पता चला तो फिर कुछ भी नहीं पता ना. अरे यार ऐसे फिजिकल तरीके से मत देखो. देयर आर अदर रीजंस आल्सो, बट अभी इस स्टेज पे क्या व्हाट कैन बी अंडरस्टूड बाय दिस क्लास. बाय दिस क्लास इट कैन बी वेरी इजीली अंडरस्टूड कि वर्क नहीं पता चलेगा, वॉल्यूम चेंज नहीं पता है. देयर आर अदर थिंग्स आल्सो. अगर वॉल्यूम चेंज नहीं पता है तो रखोगे कहाँ? यू हैव टू अकाउंट फॉर दैट वॉल्यूम, यू हैव टू डू सो मेनी थिंग्स. यू सी, लेकिन मेजॉरिटी ये है कि इफ यू डोंट नो हाउ इट चेंजेस, वर्क ही नहीं पता चलेगा. तो वर्क नहीं पता चलेगा, देन फर्स्ट लॉ नहीं लगेगा, कुछ भी नहीं पता लगेगा. यू हैव नो कंट्रोल. एंड मोस्ट ऑफ द टाइम इट इज द वर्क दैट यू आर आफ्टर. यार ये मिल जाए, even though we need to give it heat or whatever, but we need to control the work because that is what makes sense. Okay, so idhar ek minus hai. You need to calculate these.
So what is the negative out there?
Huh?
Minus 1 by v. Negative here.
Can somebody answer why is it negative?
सर प्रेशर बढ़ाने पे वॉल्यूम कम होगा, गैस और
इसलिए negative है because we want to keep things with a positive value. क्योंकि ये एक बायर है, ऐसा नहीं है. एंड ये हमारे पेस बॉलर ईशा कुमारी, क्या नाम है, आप भी बातें नहीं करते जाने कहते रहे. आप पेस बॉलिंग कहाँ करते हैं? ग्राउंड में? हाँ, ग्राउंड पे नहीं, नॉर्मल. और नॉर्मल क्या होता है? ग्राउंड ही नॉर्मल है पेस बॉलिंग. मतलब ऐसे ही विंग में. अरे तो फोकस करिए कम से कम. इसको उधर चैटिंग करें. ये सब स्लिप वाले लोग करते हैं, पेस बॉलर नहीं करते. मंदिरा देख लीजिए क्या मतलब द काइंड ऑफ टेंशन आई हैव टू गो थ्रू एक क्लास पढ़ाने के लिए. तो रिमेंबर कौन क्या करता है, सो दैट वो दैट पर्सन डजंट फील हर्ट. अदरवाइज तो बहुत सिंपल है. क्यों बात कर रहे हो, क्यों, क्या समझ में नहीं आता, बाहर निकाल दें. समझा के समझ ले तो वो अभी भी नहीं समझ रहे. देखो, the problem with generosity is that people think कि कुछ होगा ही नहीं. अरे सब कुछ होगा. लोग फेल भी होते हैं कोर्स में, you know that. कोर्स तक तो ठीक है, लाइफ में फेल हो गए क्या होगा? You have to thought about that, which is a result of what your little habits are. Correct? I can give you a lecture on that. ये little habits जो है ना, यही डिफाइन करती हैं कि मतलब लाइफ में क्या होगा. Okay? So बहुत सारे लोगों ने बहुत कुछ कहा. See how habits decide this. Get into this. ये class है, learn all this. So ये बनाना है. कैसे बनाया जाए? So simple है, इसमें कोई बड़ा issue नहीं है. We just say this is the major decision जो लेते हैं. So we say okay, V इधर है, EP इधर है. V is VP. The moment we say this, all the calculus will come to our head. And all state functions and all that, in the beginning I said, you kind of revisit your calculus. So ये आ गया. फिर एक derivative लिख देते हैं. Okay? कोई भी काम कैसे होता है? अगर कुछ भी नहीं हो रहा तो तोड़ो उसको. कुछ तो होगा. ऐसे काम चल नहीं रहा है. कुछ पिटाई करें, इधर से ठोको, उधर से ठोको, क्या करती है? कैट क्या करती है? हिलाती क्यूरियोसिटी कितनी है कैट की? जैसे वी हैव टू बी लाइक कैट. फिर समझ में नहीं आ रहा है, हिलाओ, इधर करो, देखो किधर जाता है. कुछ खोलो, तोड़ो. तो ये हमने इसको तोड़ दिया. हमने कहा इसको तो फाइंड आउट कि क्या होता है. फिर तो रेस्ट विल फॉलो. रेस्ट ये मेरा क्लास नहीं है. इट्स वेरी इजी. And DT कर देते हैं, डेल्टा नहीं लिखते हैं. इससे पहले कि ये बोले भी तो क्या बोलेगा गलत है. DT लिख देते हैं. दिख नहीं रहा है बट इट्स DT. फोटो में भी गलत है. और फिर B भी चाहिए. Okay, तो इधर b कर दिया, okay, इधर भी 1/b कर दिया, इधर भी 1/b कर दिया, okay, इसको बीटा कर दिया, इसको कापा कर दिया. It's okay? Is this okay? कोई दिक्कत नहीं? So minus comes in because we want beta to be positive. Okay. Negative, there's lot of trouble that comes in when you, as it is, there's no problem. But because rest of the system is based on things being positive, we kind of have to work with that. You see. Otherwise, there's no problem. We could have, we could have done away with that minus sign. Okay. But it's bias. Okay. And the only place where you find a real bias is in thermodynamics. You see, कहीं और नहीं, no other field of inquiry has that bias. क्योंकि इधर time का concept है, उधर भागता है आगे. This is the only field of science. जिसमें एक time है, आगे जाता है. So there is a directionality. Nowhere else you will have that. Everywhere इधर से range आ रही है, उधर से वापस आ रही है. Same. Okay. इसमें this is the only place that tells you forward movement एक है. Okay. So honoring that, ये बन गया. Okay. Now the question is कि we can integrate this. पहले थोड़ा arrange कर लिया अपनी तरह से, और फिर बना रहे हैं. And typically this is what happens in the world in all processes. ये तो एक analysis है, but in all processes also this happens. कुछ खाना खाया, तोड़ा, फिर बनाया. Okay. All those components, ये protein, वो protein, ये थोड़ा carbohydrate, थोड़ा कुछ बनाया. Okay. कोई मिला उसको तोड़ा फिर बनाया. Okay. This model of education में तोड़ना allowed नहीं है. 10 साल पहले था, 20 साल पहले था, अब allowed नहीं है. देखो क्या होता है. कितनी मेहनत करनी पड़ती है. अभी तोड़ना allowed होता है तो अब तक ये नौबत ही नहीं आती. सब अच्छे से बने हुए आते हैं. प्राइमरी स्कूल से ही सब बने हुए आते हैं. अभी तोड़ना अलाउड ही नहीं है. क्या करें? But that's okay. ये भी रूल है. So this has a name. This is kind of some compressibility. This is some compressibility. Okay. And this is there, and you need to integrate this to convert this to data. See, dt say it's good for analysis, but ultimately you need to convert that to some data. Okay, which means that you need to integrate this. So this will become T2 minus T1. This will become T2 minus T1. This will become you'll have some log of this and log of this. Okay, but this is okay. There is nothing else here. This as a function, you see, of, because we are integrating with respect to t, we are integrating with respect to t. So those functions of
T and P.
you need to know, or they are zero. You see, they can be zero also, you see, because maybe the volume doesn't change. Whatever the volume is there, if the volume stays that way in the process, the volume is not changing. It's something like an incompressible. Okay, so you can choose any fluid. This is like tangent here. So you can choose any fluid and you say it is incompressible. Okay, but you know that it is not completely incompressible. With some limit, small changes can come for liquids. So one set of assumption would be incompressible, but you want to say, okay, it has some small value here. So this is in cases where you are looking at liquids and special kind of liquids, and also a movement towards polymers, moving towards complex fluid. Okay, you can say beta and kappa, they have small values, but they are not zero. Okay, which means that the volume is changing, but a little bit, and we know how it changes. Okay, so you put them as constant values. Okay, so this is one trick, and have you understood this trick? Okay, the trick is that you need to look at some variation. Okay, and you need to convert that variation to either to some measurements. You see, to measure it. finally, to estimate that variation. And to estimate that variation, you can only make measurements. That's the only thing that you have in your hand, you see. And those measurements can be of anything, depends on what kind of instrumentation you use. But typically, pressure can be measured easily, temperature can be measured easily, volume difficult, composition can be measured easily, okay, because composition kind of shows up, can be magnified. The effect of composition can be magnified in many ways, you see. So all these new kind of sensors, okay, and this is something that you will find very fruitful, is to how to detect, how to find out about something, very early, something that is happening, how can we know it early, in health care, in let's say in safety, okay. So a little bit of something that has come in, how do we detect it, okay, and what kind of measure there, purity of things, okay, contamination, all those kind of things. So the composition sometimes has a very, very, prominent signature, okay. Let's say your nose, you see, I mean, you can detect so many things, you see, very quickly, you see. So composition, even though it is, let's say, very, very small, but you can have a huge signature, okay, and can make, you just need to find how to measure it, you see. So you don't necessarily have to count that these many molecules are there, and you flag all of them, or maybe there is some radioactive tracer or something, you can do all, but you can look at what this composition does, okay. So some kind of titration, some kind of color that appears, some kind of smell is difficult, you see, very subjective, but color, let's say, because you can measure it through sensing, okay. So this is the key, and you have to convert it to some data in that, okay, or some measurement. So this is the key. There will be other tricks also, okay, and we'll see. Now for all of this to work, okay, we need to find some relations, okay. So because of many things, okay. One of them is, let's say, P dV is the work done, okay. Force dot F dot D, you see, is the work done. Work done, we need that work done. If we know what the work done is, we'll put it into the first law and we'll find out what the heat is, okay. And of course, we need to know how U varies. So we need to track the internal energy also. We need to track what the work is, and we need to track what the heat is. So if we know two of those, the third can be found, okay. U, we have good control over, okay. See, the worst thing to have control over is the heat, you see. Work also is difficult because it involves, change in volume. Volume itself is difficult to measure, but it's still better than the heat, you see, because it's directly, some movement, some changes. So you can figure out this displacement has happened. You can say, that the work there is this, but then there is some other work that is lost here and there, shaft work, this and that. But let's say, at least the work that is useful, you can measure directly. See, that's not the case with heat, okay? Because the heat, you'll have to look at something that changes in temperature, you give heat to it, and then it changes in temperature, you measure the temperatures, you know what the specific heat is, okay? So very indirect measurement. Okay, so the direct measurement would be this position, and this is the force. Okay, so maybe we can use the other one, or this also. Maybe this part. Because the processes would be something like this. So we just need to find out how P and V are related, because P dV is the integral of that would be the work done. Okay. So we say, okay, if we don't know about the process, we say PV gamma is constant. Okay. It is during the process. It doesn't tell you that it's an equilibrium value. You see, it's not equilibrium. Okay? It is during the process. Okay. So this is the difference, which you'll make mistakes here and there in one sum or the other sum, but then you'll get it right later on. So equation of state, because we need to know the relation between PV, P and V, and how U changes with T and all of that. Because that ideal system we should be able to control completely. See, we should know everything about the ideal system, and we should know everything about the reversible process. If we falter in that, then we are in trouble. Then it's all data only. Okay, I'm telling that. So we look at this. So what is the first thing that we get? Is PV is RT. Okay. This is for ideal gas. Okay, so P is there, V is there, R, we know the universal gas constant, the units have to be right. Okay, it will not be the Boltzmann constant, so people do make that mistake. Okay, so it is R, the universal gas constant, and then absolute temperature. Okay. So let's say if you want to use this well, but it will work only for some cases. You see, for most of the cases of interest, let's say complex fluids, solids, plasma, dense gases, real gases, liquids, this will not work. Okay, but this can be your starting point, at least for gases. Okay, so we have some variations of these. So what do you think should be the first variation? If this is the starting point, and knowing fully well that you need to know about the real liquids, real states, all other liquids, and also reversible work in the process. Okay, work and heat in those processes. So what should be the first one? Okay, variation from this. So we say we have something like okay. So this is the first. This is the compressibility factor. Basically compressibility factor. We call it Z. And this is one of the starting point for looking into all kind of other systems. Okay. While PV is equal to RT is the starting point for ideal systems, PV is equal to ZRT is the starting point for all other real systems. So depending on the requirement, okay, you can go as deep as you want. Okay. In this, because the thing here is Z. What is Z? How do you find Z? Okay. So if you can find an expression for Z, okay, and depending on what the requirement is, so Z can be the starting point. So because if there is no other complexity and you're happy with the ideal gas law, Z is 1. Okay. But let's say you want to have some more effects, you want to be, maybe things are very non-ideal, okay, or you're worried even for very small changes. Both cases, you see. The thing itself might be changing very fast, or you're worried about even small changes, okay, which in the sense, the thing is actually varying fast because the measurement unit is very fine. Okay. So what do we do? What do we work towards? Okay. So two methods here, two, let's say, different kind of streams. Okay. So one stream is to get the equation of state from physical considerations. Okay. That will get this equation of state from looking at the physics. You see, so what kind of changes can come in the equation of state? Okay. So what was the first instance of that? Where we looked at the system, argued about the physics of the system, and we got an equation of state. Okay. And that was the starting point for even though it was done for gases, but it was the starting point for understanding liquids also. So that is and all other things. Okay. So can anybody tell me? See, there are two ways. One is that we kind of look at variations from this, and of course this is the best form that you want, okay, because it's only the Z. One is that we do it in a theoretical way. We argue about, we look at the physics and we say, okay, this is probably the kind of expression that we should have. Okay, one way. The other would be that we look at data. You see, we just assume that Z is some function of temperature, pressure, volume, and we kind of look at what those coefficients are. Okay, so two very different approaches. Okay, so one is through some physics, and the other is through experiments, data, because you can make lots of measurements. So the first one would be, do you recognize this? With a small v.
Van der Waals.
How many of you recognize this as van der Waals? अरे V छोटे से होता है इसमें, लाइक बैंक, बहुत सारे बैंक है ना, बैंक V छोटे से, बैंक पर से, ये सब जो फुटबॉल के बैंक मास्टर, छोटे से V, नाम जो होता है छोटे V, ओके। सो वैंडर वॉल फोर्सेस, ये इक्वेशन ऑफ स्टेट पढ़ी है? किसी ने पढ़ी है? किसी ने नहीं पढ़ी? पढ़ी होगी, इतनी सिंपल है। कुछ वॉल्यूम ले लेते हैं मॉलिक्यूल्स, और कुछ इंटरमॉलिक्यूलर अट्रैक्शन है, ओके। दिस इज रिलेटेड टू have you done this kind of exercise? Yes, all of this is so some attractive force, some repulsive force, and where is the attractive component, where is the repulsive component. You see, volume can be seen as a repulsion. You see, so this in your mindset, there is a perspective of looking at a repulsion in saying that this belongs to me. So as soon as you say that this belongs to me, there is a repulsion that is implicit in it. That doesn't, so there is an exclusion, you see, that it doesn't belong to you. You see, for space. So that is a different perspective, you know, very subtle change, but it's a different perspective. So as soon as you say, this is what I have, okay, this is the repulsion, because that's how you exclude others, because of the repulsion, okay. So this is the volume, but this is the repulsive term, this is the attractive term, okay, and both of them will then give you this. Now lots and lots of questions can be framed, okay. From this to this is not the subject matter, you know, we'll not do this, but can be done, okay. And from this to this, you see, so this is somewhere, this is at macroscopic level, because we can measure volume, pressure and temperature, and then with lots of experiments we can figure out what is A and what is B and this. So if you want to do a lot of measurements where you know what the temperature is, you know what the volume is, okay, and you do experiments, okay, and or maybe you know what the volume is, you know what the pressure is, and then you figure out what the temperature is, you measure that also and you fit it, okay, and you get A and B, because once you get A and B, you have control over. If you want to use the virial equation of state, why we want to use the virial equation of state? Because the thermodynamics package in your simulation or results that are available for working, you see, all those are in terms of the compressibility factor, because that's the unit that we have decided to work with, the compressibility factor. So we say, okay, this particular equation of state which has A and B in it, they have to be related to the compressibility factor. How do we get A and B? We get A and B by doing experiments, okay, or we get A and B through knowing A and B, capital A and B here, and then working from here to get this, okay. So this is also a very valid form of inquiry. You see, a lot of people spend their lifetime working in this domain. You see, from microscopic, and listen to this carefully, a lot of faculty members, lot of researchers have their career based on this, and this is one of the important question to answer. If you know the microscopic, can you then estimate the macroscopic to compute the macroscopic from the components, okay. So you start with these and you generate this, okay. So a lot of research is done in this. Polymers also, the structure and all of this, and then you figure out what the rheology would be, how the reactions would, what the diffusion coefficients would be, do all that, what the viscosity would be. So one field of inquiry is this. Another field of inquiry, which is probably more useful for industry, directly useful. How do you get A and B, and then how do you convert it to Z? Why do we convert it to Z? Because Z is the kind of structure that we have all agreed to. You see, it is straightforward. Ideal में इतना होना था, इसमें इतना है. Z is more than 1, तो ये कम है. You see, volume ज़्यादा हो गया. जितना आना था उससे ज़्यादा हो गया ना. Because Z is B over BIG. Okay. So इधर लगा सकते हैं ideal gas. Okay. Is this is ideal gas, and this is the volume. Okay. So EV ideal gas is RT. This is the ideal gas law. This is for anyone. Okay. And Z. So because we have chosen to work like this, so the whole idea and structure and things that are available, design methods that are available, rules of thumb that are available, values of compressibility factors that are available with respect to, let's say, pressure, temperature, species. So a lot of work has been done here, which means that if you convert whatever your analysis of the system is to this form, okay, so knowing the equation of state, you convert it to Z. Okay, this is another research. Lots of questions, in your tutorials would come from here. Okay, that given this, how is Z related to A and B? Can you do that? If PV is equal to ZRT is this, and this is this, how do you get A and B related to Z? सर एक ही इक्वेशन है, उधर तो दो वेरिएबल हैं, मैं कहाँ से लाऊंगा? You understand? और ये तो Z आपने एक ही लिया है. Let's say if you're looking at a complex form of Z, complicated form of Z, which is Z has 1 term, 2 terms, 3 terms, 4 terms, वो सब कहाँ से लाऊंगा? Okay? तो major question जो analysis का है इधर. Okay? It is not a straightforward thing where you have one expression and another expression and you say, okay, I kind of do some algebra and one expression comes out to be, I can compute what Z is in terms of A, B, or compute A, B in terms of Z. Okay? It's not straightforward. You will get lot of other derivatives, okay, and that's what makes it very complicated. Lots of questions based on those. Okay, so two major kind of questions. Okay, AB to this, and from there to Z. Okay, and Z itself is a form which can be. These are virial equation of states. Okay, so वो कौन सी है? I'll have to read because it's in terms of P and it's in terms of V. Have you done those virial equation of states? कुछ तो किया होगा.
थोड़ा याद आ रहा है.
यार ऐसे कुछ नहीं देखा. मैं देखता हूँ इसमें लिख के दिखाता हूँ क्या एक्सप्रेशन है. ऐसे करके और ये भी है जब तुमने पढ़ाई छोड़ दी 12th के बाद हम क्या करें? 12th से पहले मैं तुम सबसे आगे, कोई डाउट नहीं है मुझे. Okay, so as I said, if you need more than what just one value of Z, okay, this is how you get it. So the question now becomes here B dash क्या? How do you get B dash? How do you get C dash? So in both ways, if the equation of state is given, which is not a visual equation of state, so how different equation of states convert to visual equation of state? Okay, with just one term, with two terms, with three terms. So this general method. So this is one kind of calculations. Another kind of calculations would be how to get those equation of states. Okay, and one of the method there is that from physics, another is from data. So you will see B dash, how is it related to PVT? Okay, so you can assume that P variation is in this, and this is only a function of T. इतनी गलती नहीं करेंगे ना कि P और T इसमें डाल दिया तो फिर T कायदे से नहीं लिखा है. You see, then it's not the right expansion. You see, and this is intimately related to the power series expansion. Okay. So there is nothing wrong in writing those virial equation of state. They will stand on their own because the maths tell us, the calculus tells us this. So Z is some function of pressure and temperature. You कर सकते हैं. Okay. And if we know Z is a function of pressure and temperature, we can say, okay, the coefficients will have the T variation and we'll write a power series for P. Okay, and the way we'll write the power series for P is, because linear, 1, 2, 3, 4, 5, 6. If you maybe it has been taught to you in maths or not, but it exists, this kind of things exist, where you write a function in terms of power series expansions. Okay, so Fourier series is, let's say, a very special example of that, okay, in terms of functions. Okay, so not just in power series, but in terms of functions. Okay, so yeah, and those of you who would like to do some very high order analysis, okay, and do a lot of good maths, okay, one of the things would be to study this. This function written in terms of a series of some basis function. Okay. So the special case would be a power series. So you must have done some examples, कोई function दिया उसको 1 plus x square plus x cube करना, and then the coefficients have to be found. And how do you find those coefficients? You take derivatives, and you get those coefficients. ये सब exercise की है. But power series is not the only expansion. You can expand or have an estimate of a function based on the basis functions. Okay. And there are several restrictions on that the basis functions themselves should be a complete set. All kind of mathematical jargon would come in. That this function can be written in terms of other functions, but the other functions have to be a complete set. Complete set means that this unknown function, they should be able to represent any given function, which means that they should have that special quality. Because ऐसा नहीं होना चाहिए कि we choose a function पर ये सारे मिलके उसको बना ही नहीं पा रहे, like Humpty Dumpty, बना ही नहीं पाए. So then this doesn't work. Okay, but अगर पढ़ोगे इसको, तो you will catch on to some kind of, I'll not say cheating, but some play. वो क्या करते हैं? So which means that there is a concept called a complete set. If you study, function analysis or linear algebra, there is a complete set. इसमें does anybody even remember a little bit complete set? कभी सुना है? ये पावर सीरीज तो पढ़ा ही है ना. एक्स स्क्वायर की जगह कोई फंक्शन हो सकता है ना. फोरियर सीरीज तो पढ़ा है ना. साइन वो भी तो फंक्शंस ही हैं. You see, going from 1 to infinity. तो ये functions जो हैं ये they should form a complete set, which means that they should be able to represent all functions in that space. मतलब मेरे स्पेस में जितने भी फंक्शंस हैं, I should be able to represent all those functions by a linear combination of these functions. यही तो है. Okay. Cheating क्या है इसमें? So whenever you will do this course, you should look for that cheating. Not cheating is a strong word, but थोड़ा बहुत ऐसे. क्या करते हैं? वो कहते हैं this is my complete set. I use this set to represent any function because आंसर पता नहीं है, तो हम ये कोफिशिएंट के टर्म्स में आंसर लिख लेते हैं और बाद में वो अननोन्स को पता करते हैं. लेट सबसे पहले क्या पढ़ा था अलजेब्रा में? लेट द आंसर बी एक्स. फिर एक्स की कंडीशन लिखते हैं, तो इधर भी लिखते हैं कि लेट द आंसर बी दिस, और फिर ये कोफिशिएंट्स पता करते हैं. ओके, तो इधर भी यही करते हैं. बट कोफिशिएंट्स पता करने के लिए द क्वेश्चन इज कि इट शुड बी अ कंप्लीट सेट. अब कंप्लीट सेट कौन बताएगा? क्योंकि इतना तो आसान नहीं है. इस पूरे इंस्टीट्यूट में कोई नहीं है जो गिवन एक सेट दे दे जो तुम्हें बता दे. अगर इस इंस्टीट्यूट में नहीं है तो दुनिया में भी कोई नहीं है. 1-2 लोग होंगे जो बता सकते हैं. ओके, वेरी डिफिकल्ट टास्क. तो क्या करते हैं? कहते हैं कि ये जो सेट है, इट इज सेट ऑफ these functions प्लस I'll add whichever is required to make it complete. तो ये कौन सी डेफिनेशन है? पर है. So ये तो है, I'll work with these and I'll add whatever else is required to make it complete. ऐसे करके वर्क अराउंड कर लेते हैं. बट अटेंडेंस शीट कहाँ है? अभी पकड़ते हैं. 30 मार्क्स के लिए कोई शहीद होगा पक्का? अभिषेक, पता है इसका क्या मतलब है? कि जब शहीद होता है इसको बता के होता है. अरे यार पढ़ो, मुझे पढ़ने में नहीं आता. जल्दी पढ़ो.
लाल वाला तौकीर
इज हियर.
आर्यन त्यागी
त्यागी इज हियर.
ऐश्वरी प्रसाद
यस, प्रसाद इज हियर.
हर्षित भट्ट
Bhatt is here.
विशाल भगत,
Bhagat is here.
पुलकित गर्ग,
Garg is here.
शशांक कुमार,
Yes.
अनिंदर रॉय,
Yes.
उत्कर्ष गंगवार,
Yes.
अर्नव रंजन,
Yes.
विकास यादव,
Yes.
मनोज्ञ,
Yes.
जगदीश,
Yes.
मयंक कलाल,
Yes.
अंश अरोड़ा,
Yes.
सार्थक मौर्य,
Yes.
अभिषेक सोनी,
Yes.
प्रीतम कुमार,
Yes.
आकाश,
Yes.
केशव,
Yes.
शशि,
Yes.
स्तुति,
Yes.
मान्या अग्रवाल,
Yes.
निकिता,
Yes.
दिव्या,
Yes.
इशिता,
Yes.
दिव्यांशु,
Yes.
आलोक,
Yes.
खुशबू यादव,
Yes. Khushbu Yadav. Yes.
अश्विता
Yes.
राठौर,
Rathod is there.
मोहम्मद तसीम,
Yes.
हार्दिक कुमार,
Yes.
लक्की बुस्कुटे,
Yes.
निखिल जहांगीर,
Yes.
केशव राज,
Yes.
अंकित एस पाध्याय,
Yes.
हिमांशु मीना,
Yes.
सनत गुप्ता,
Yes.
ऋषभ जोशी,
Yes.
सारंग मेदे,
Yes.
पारस कंसल,
Yes.
तनुष सिंह,
Yes.
प्रथम,
Yes.
संजय कुमार,
Yes.
नेनामत गणेश,
संजय कुमार कहाँ है? Yes. 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 ठीक है चलो.
नेनामत गणेश,
Yes.
अन्ना यादव,
Yes.
अमोल गुप्ता,
Yes.
मुनावत पवन,
Yes.
अनंत सिंह,
Yes.
बसंता रंजन,
Yes.
वेदांश अग्रवाल,
Yes.
क्षितिज कुमार,
क्षितिज कुमार कहाँ है? Yes.
शुभम चावला,
Yes.
अभिषेक कुमार,
Yes.
विकास कुमार,
Yes.
प्रखर अग्रवाल,
Yes.
राहुल कुमार,
Yes.
निशांत कुमार,
Yes.
अंकित कुमार,
Yes.
नितिन यादव,
Yes.
आकृति हरित,
Yes.
दीप्ति भारद्वाज,
Yes.
उदय प्रताप,
Yes.
ईशा कुमारी,
Yes.
हार्दिक भगोड़ा,
Yes.
ऋषभदेव अंगन,
Yes.
पीयूष कामत,
Yes.
निशान विश्वास,
Yes.
रोहित कुमार,
Yes.
आयुष,
Yes.
तरुण कुमार,
Yes.
जागरव,
Yes.
सचिन,
Yes.
अनिरुद्ध,
Yes.
निष्का,
Yes.
स्नेहल,
Yes.
आरन बंसल,
Yes.
हर्षित अग्रवाल,
Yes.
सुधा चंद्रा,
Yes.
सुमन मांझी,
Yes.
सुरभि,
Yes.
दृष्टि,
Yes.
श्रेयांशी करोड़िया,
Yes.
साक्षी पटेल,
Yes.
दिव्यांशी नरेश,
Yes.
मंदिरा दास,
Yes.
मीनाक्षी धिंगड़,
Yes. Meenakshi is here. Yes.
हार्दिक कोतवार,
Yes.
यश मोदी,
यश मोदी है. फोटो पे खींच रहा है.
मनु कतियार,
Yes.
गर्ग गुप्ता,
Yes.
मनन कतियार।
Yes. और कुछ लोगों ने नहीं लिखा? चलो.
रेट ऑफ 10 है ना?
क्या चाहते हो? रिक्वेस्ट टू रेज की होगी. ऐसे दोनों का सकते हैं.
सर शीट दे दो सर, शीट फाइल दे दो, हाँ फाइल दे दो।
Let's see around. जो तुम्हारे साथ गया था उसको कहाँ छोड़ दिया? Okay, what date is today? नहीं है ऐसे ही आइडिया से Okay, so quiet please. So looking at the properties of substances, we said we look for an equation of state, okay, and we kind of break into the real ones and the ideal ones. And the ideal ones you should be able to handle easily, and they should be able to find the deviation also, so that most of the real ones can also be used. So this division between ideal and real is also one of the tricks, and has to be used well, because the way you choose ideal is kind of is in your hands. Okay. Shh, quiet. So the way you choose ideal, one of the messages is that the way you choose ideal is in your hands, and it should do the job properly, which means that you should have good control over ideal, and also it should be able to take care of most of the real situations by just a small deviation here and there. Okay, so two opposing things. It should be simple but not simple enough. Should be useful. Okay, so simple as useful. So this will give you a chance of defining your own ideal state. Okay, and see, one ideal state is no different from any other. The one of the ways to choose the ideal state is that you get rid of the potential terms, or all the hidden terms, or all the latent terms. You see, so something that is not visible directly, you see, is the first thing you should get rid of. Okay, जो सामने दिख रहा है वही देखेंगे. So that's why your grades, you see, they become the shortlisting criteria. You know, company क्या करती है? Company कहती है देखना है, you know, what do I look at which I have the greatest faith in, which is known, you see, which is in front. The grades are in front, you see. Your appearance is in front. You see, the way you dress, the way you speak, the way you talk to people, you see, that's in front. What you write is in front, you see. So there's nothing philosophical about, you know, feeling bad about that nobody looks at what is inside. But why would anybody look at what's inside? It's so difficult to look. You see, there's no check. So most of the time when you have to choose the ideal, and that does the job most of the time, is to look at what is directly in front of you. Okay? And in terms of nature and materials and thermodynamics and matter, it is mostly, and even men and people, women, is mostly the hidden things, the latent things. Okay? So you get rid of the potential energy component very quickly. Yeah, who is bothered about the potential energy? Andar छिपा है कुछ है, you know, how do we even know? Yeah. Come in quickly. So that's why the ideal gas is no potential energy component. Okay. So we have the pressure, we have the temperature, and we have the ideal gas volume. So you have a superscript Ig, like ideal gas. Okay. So just see, there is no P ideal gas here directly. There is no T ideal gas here. See? Normally we speak in terms of, you know, what is the volume. So now you can relate it to the difficulties that we always have had with volume. You see? So we say, okay, we'll know what P is, what P is. This is the volume. This is the ideal gas. Okay. So this is fine. I mean, there's so many ways to look at it, but then, you know, we waste a lot of time. Not waste, but kind of not directly relevant to this case. Okay. So how do we look at the deviations now? Okay. And then there is a trick. The trick is that you always have the ideal one here, and the easiest way to look at the deviation. Okay, and the easiest way to look at the deviation would be to write the same equation here and then just say PV is equal to ZRT. Okay. So there are many reasons for this particular form to be very useful. Okay, and one of the reasons why this form is very, very useful is because thermodynamics, the most of the contribution is through property estimation. So whatever simulations you do, whatever process analysis you do, is the thermodynamics package that comes in, gives you the properties, and in properties you need to know the volume typically most of the time. I mean temperature, pressure also, we are looking at saturation temperature and pressure, means the boiling point, the dew point, all those things. So if you look at the thermodynamic properties, there is this PV is equal to RT, the ideal gas one is straightforward, and you just kind of add a compressibility factor to it. Okay, and so the coding wise it's very easy. You see, physically to appreciate knowing the value of Z, what will happen to the system is straightforward, because Z equal to 1 is like the difference. So below it a different behavior, above it is a different behavior. Okay, that makes sense. So if you want to have a threshold, see there is a little bit of trick also involved in this. If you want to have a threshold so that the behavior here is different from behavior here, you see, it's just like a threshold. Okay, and if that threshold is mapped to 1, you see, by some numerical method or non-dimensionalization or scaling, then it makes a lot of sense. Okay, so you should try to map all your thresholds, so bring all your thresholds to unity by manipulation. Okay, by dividing them by something or whatever. Okay. So that kind of helps. Okay, so it's a good practice, because that threshold would be a part of some calculation, some program, somewhere, some analysis, some theoretical analysis also, and things being greater than 1 and less than 1 is a huge impact. Okay, huge impact. You see, the 1 has that power. Okay, so 1 has many interesting things, but 1 typically has that. Things keep on increasing, things keep on decreasing. See? So if you look at subsequent powers also, so the 1 you relate it to 1. Okay, so compressibility being 1 is the straightforward case, is like a threshold. Less than 1, it has a different meaning. More than 1, it has a different meaning. Okay, coding wise, software wise, you just have to include some term there. Okay, or you multiply your answer by something. Okay, so that's why it's very, very interesting. Okay, so most of the time it is to find what the compressibility factor is. Okay, and now the compressibility factor is, you see, another trick. If you, so maybe I'll write down the tricks here, otherwise you'll forget. So 1, power of 1. You see, you understand the power of 1. Your generation would understand, you see. Whatever is happening is power of 1. So the 1% decides. Just 1%. Okay. In your history, whatever, 20 years, you have not seen that. You see, 1% deciding. Not our Prime Minister, somebody's president. So 1 is actually very powerful. Okay. 1 is anyway, there are so many things about 1. So 1 ho gaya ye, ek humne idhar likh diya. The second thing is that the moment we say unknown, then we say Z is unknown, we have to find out Z. So there are many methods to find out Z. One of the approaches is, why is this deviation? This deviation is because of we can be clever and say non-ideality, this, that, but let's say potential energy, typically. Kinetic energy also, but mostly potential energy, because kinetic energy also, not all the terms could have been there, you see. While translation is much easier to see, rotation, vibration are not so easy to see, you see. Rotation is difficult to see because rotation kind of moves, you see. So while we think, you see, that all three modes are straightforward, they are not, you see. Translation is much easier to see, measure also. Rotation is so difficult to measure that, once you are seeing something, observing something, it has taken 5 rounds, 6 rounds, 10 rounds, 20 rounds, 100 rounds, it's not easy. We will come back, we'll show you the same face. Okay, so just think of this. RPM measurements How do you measure the RPM? RPM of a stirrer in a mixing tank, you see. And then there is this RPM, it is moving, and how do you even measure it? What is the way to measure it? And you know fully well by this time that RPM kind of relates to power factor and then how much power is being transferred to the solution and the mixing. And that is chemical engineering. Mixing हो रही है नहीं हो रही है, non-ideal mixing है तभी हम हैं. If everything was ideal, then chemists would have solved the issue. Mechanical engineers would have solved everything. You know, because things are not mixing properly, you know, हमारा discipline है chemical engineering. So mixing के लिए the stirrer is there, and the stirrer में the major thing is of course the blades and everything, the design. But the RPM is the major thing because that's under control. Once you bought the agitator, once you bought the stirrer, RPM is ignorant. RPM measure नहीं होता. How do you measure the RPM? Because जैसे ही measure करोगे एक बार घूम गया, you know, नहीं measure होता है. So rotation is not that accessible. You see, तुम्हारी जिंदगी में कितनी बार घूम गए? You know, मून घूम गया, धरती घूम गई, सूरज घूम गया. You know, कुछ minutes बता रहा है, कोई hours बता रहा है, कोई months बता रहा है, कोई seasons बता रहा है. You know, all kind of rotations. फिर वही है. You see, तो कैसे पता चलेगा? You know, अभी पता चलता है, ये बाद में क्या पता चलेगा? 10 साल में, 20 साल में, 25 साल में नहीं पता. You see, so all kind of rotations because they come back to the same place. You see, and it is still an unsolved problem. How to measure this the RPM of a stirrer easily? Okay, ये अभी भी it is not solved because there are many issues. Okay, and the major issue is of that harmonics. Because whatever you measure, the major problem is because of harmonics, because it comes back to the same location. And if you use anything known signal to match it with this and see that, you see, you miss out on harmonics. Okay, so ये life में all kind of rotation, harmonics, you know, is an issue. Okay, vibration उससे भी बड़ा issue है. You see, vibration तो बिल्कुल ही नहीं पता चलता क्या है. You know, वो एक experiment किया होगा ना कभी गए थे साइंस लैब में, ऐसे करके पीटते हैं उसको, कुछ दिखता है उसमें? कुछ नहीं दिखता. क्या हो रहा है? वाइब्रेशन है. You know, come here, I get these vibrations, all kind of vibrations. You see, seismic vibrations, ये vibrations, वो vibrations. You know, not so easy. से घूम रहा है, फिर the kind of damage they do because it's kind of cyclic. इधर जा रहा है, इधर जा रहा है, इधर जा रहा है, इधर जा रहा है. There can be a feedback that is positive or feedback that is negative. You see, तुमको धक्का दे रहे हैं, जब तुम उधर मूव कर रहे हो तो और धक्का दे रहे हैं, फिर और उधर मूव कर रहे हो और धक्का दे रहे हैं. So even with a small force you can generate a huge acceleration. Not acceleration but huge impact. Okay, because वो तुम phase में तुम constructively you are kind of pushing. You see, तो जब वो vulnerable है, जब घूम रहा है उधर तो और धक्का दे दिया, फिर अगली बार घूम रहा है फिर और धक्का दे दिया. See, तो measurement कैसे करोगे? If the measurement में तो impact ही measure करते हैं, and the impact itself is kind of dicey, कुछ भी हो सकता है. You're never sure vibration. Okay, फिर all kind of resonances come. So not so easy to measure. क्या हो रहा है? And very damaging. Bridges टूट चुके हैं. I mean this is reality. You see, ऐसा नहीं है कि हमसे joke कर रहे हैं resonance. So even kinetic energy is not there. उसमें भी components of kinetic energy they are not so existent. Rotate कर रहा है, rotation में half I omega square है. You know, major component omega ही नहीं पता. घूम रहे हैं. I तो जोड़ो, because that would mean the mass distribution को तो और भी difficult है, अंदर जाना पड़ेगा. So all kind of things are there. So इसमें what to control Z, the simplest case we need to look at what the potential energy component would be. Okay. So there's one way is that you work from inside, because for this codes and thermodynamics we are saying that we'll only look at the macroscopic. We are not go inside. But problem solution में तो it is multidisciplinary. We can make use of many things and we are ready to go inside also and get the value of Z. अगर प्योर thermodynamics ही कर रहे होते, and if you are true to what we are doing, then all the values of Z would have been fitted values, you see, from some experiments. Okay, so we'll come to that. So Z में experiments कर लिए, I'll say so let's just discuss about these experiments also. कि you have experiments or you have a data set, जो maybe not at your level now, but सबसे पहले what are you searching? Data set कहाँ है? कहाँ से मिल रहा है? कौन दे देगा? So that I can run my algorithm on it. और my algorithm छोड़ो, कोई और software run कर दे. So the quest is for the data set. Okay, कि कहाँ है? And so you can get a data set from some here and here, you know, all kind of things that you can use and get the value of Z. Okay, and क्या चाहिए होगा Z straightforward mean you should, if you have this data, this and this data, PVNT data, PVT data है तो ये मिल जाएगा Z because will fit. Okay, so this is one way you can get it from a data set because कहीं ना कहीं available होगा. Journal of Chemical Engineering data, journal बहुत, there are lots of journals for data also. Okay, so वो सब लेके आते हैं. जो mixing rule में I searched all those viscosities of mixtures. फिर you can do experiments also. So experiments में what is the biggest problem that you foresee? One is of course the infrastructure, the time and everything that is required because you do a physical experiment, so that cost. Okay, that cost is there. But what is the biggest mistake that you can make in this kind of measurement where you have to get Z, because Z is important. Z is what will give us a handle on the real values, you know, real substance values. Okay, so what can you see? The biggest problem. Infrastructure तो है, you will set up everything and all that. ऐसे भी है, and who will do it also? You have to find somebody. The major problem ये भी हो रही है, you have to find somebody to get the work done. You see, वो भी नहीं मिलता. You see, the moment you will step out, एक नौकर भी रखना है तो नहीं मिलेगा, कोई वर्कर रखना है नहीं मिलेगा, नहीं करेगा काम. Major issue, you see, how to get people. तुम्हारी लाइफ में अभी नहीं आया ये, but आएगा. So क्या लगता है? ये even if you account for all of these, the biggest problem and the biggest mistake that happens is because you need to look for the equilibrium. Okay, so equilibrium नहीं मिलता. This is an equilibrium relation. Otherwise, so any relation can happen. Anything can happen. If it's not an equilibrium, anything can happen. You know, ये क्या है? PV gamma is constant. What is this? You know, it kind of defines the process, not at equilibrium. See? So to find the equilibrium is the bigger problem. See, and people miss that. Which means कि if you have a 3-hour lab and you have to find the equilibrium and you have to, let's say, look at some kind of law, ideal gas law or your compressibility factor, the equilibrium कहाँ जाएगा? Which means it has to be split. एक बार की अगले दिन सुबह जाकर रीडिंग दो, फिर वो then it is unattended, the experiment is unattended, कहाँ से पता चलेगा? और if you cannot do something at an undergraduate level, if there is an experiment that cannot be done in schools, an experiment that cannot be done at an undergraduate level, you know, popular skill sets तो गायब ही हो गए. And it becomes a specialized thing, you know, heavily specialized. कौन करेगा? Okay. School में कर रहे हैं, you're not doing it in the schools, you're not doing it in undergraduate level because the time is so much. Okay. So there are schools still in this country where the lab session is a lab day. You see, so there is not a 3-hour lab session. The lab starts in the morning and goes on till evening. You know, there are places in this country where undergraduate curriculum, you see, a lab day is there, not a lab session. So they'll start in the morning and they'll continue till evening because that's how the lab has to be done. 3 घंटे में कैसे? वो कुछ होगा ही नहीं. But even 4 hours, you see, so that's an extra constraint. Okay, so equilibrium. So in equilibrium, as the driving force diminishes, the rate diminishes, so you reach the equilibrium slowly and slowly, you see. And Z by default is 1. You're only looking at some variations from Z. So you're not just happy, stopping at 95% of the equilibrium. You see, you're asymptotically reaching the equilibrium value. So you're not happy with, let's say, just 90% of that. Because 90% of that is anyway, one, if you take 1, you'll not be very off, you see, for most of the gases, you see. Only for very dense gases, which means low temperature and very high pressure. If they're not operating there, then Z equal to 1 is a good answer, you see. And even by experiments, if you're cutting, the measurement far away from equilibrium, or even 10% away from equilibrium, you see, it's far away. Okay. So equilibrium, to attain that is very difficult. Okay. In physical terms, in numerical terms, it's much easier. You see. Why it is much easier? Because in numerical methods, you have done a course, and in numerical methods, there is a step size. And the step size, the stability of the step size, and the resolution of the answer based on the step size, you see, depends on how fast the function is changing and on the derivatives. See, if the derivatives are smaller, then the step size can be taken to be much larger. So it's a very interesting. Physically, attaining equilibrium is so difficult because it becomes slower as it reaches the equilibrium. Numerically, attaining equilibrium is much, much easier because the derivatives become smaller and bigger steps and sizes can be taken. Because the function is not changing much. The derivatives are less. So you can afford to take a bigger step. Okay, and of course there is a stopping criteria also. So this is typically a difference between how do we attain equilibrium in physical experiments and how do we attain it in numerical simulations. Okay. So much faster in numerical simulations. In fact, if you are closer to the equilibrium, then it's just 1 or 2 steps. You see? And then of course you look at data sets. So they don't exist so much on the net, but if you search, maybe you can find somebody who has done it. You see. So those can be used. Another approach is, so this is one which is based on experiments. We do experiments, we do our own experiments, or we borrow data from other people. Okay, and we fit, and all kind of fitting expertise, whatever happens with fitting, all that will come into that. See how to get the best fit. What do you fit for? You see. So what is that function that you fit for? Okay. So any unknown, and listen to this carefully, because anything that you want to have an handle over and it is varying. So it is not a constant. So it is, let's say, it varies with things. Okay, so it's like a function. Not necessarily a function, but it just changes. Okay, because function would mean something special also. But it kind of changes. So something that is changing, and if you have to have control over, then the trait is for so express it in terms of, do you get something? You borrowing something? No? He has nothing to give? क्या हो रहा है? Got something? No? But classic, if you have a Labrador, or if you a small child maybe, and the small child will not look at you directly. Will not allow you to even address you directly as a बात करेगा. You see, और पूरा नहीं भागेगा because that's rude. थोड़ा भागेगा. You see. So when I look at you, you need to tell me what has happened. You see, you can't just be slightly 5 degrees away and not seeing me, not addressing me. How can this happen? I'm talking to you. You see? You need to answer. Both of you, you tell me what was happening. Pen. You lost a pen. I have a pen. This desk has lots of pens. Anyway, it's very, very, interesting, to observe 100 students coming from a different era. I'll just take 1 minute. We went to this marriage and there was these young people, bride and the groom, very interesting names. Okay? And everybody had problems with those names because they have not heard those names. And I didn't have any problems. You see? It was very normal for me. You see? I said, ये तो नाम होता है. I used very casual कि हाँ ये नाम तो होता है. Not because I'm a professor or an intellectual or somebody. It is just because I come across so many names. You see, so then one of them said कि प्रोफेसर साहब आप हर साल जो है वो नए नाम देखते हैं. So आपको दिख जाते हैं नए नाम, हमको नहीं दिखते हैं. Just imagine, I never thought this, you see, that I would come across, 100 different names, all kind of names. If I'm a school teacher, even younger ones. Okay, very interesting. Okay, so all kind of behaviors also, you see, different behaviors. How we will behave. I can write a book. Okay. So anyway, so we express things in terms of a basis function. This is a trick where you want to explore something and you say, okay, I don't know this. Okay, or I want to find out this function. Okay. So if you remember in algebra in class 3, class 4, class 5, you were told let the answer be x. ऐसे करके पढ़ाते थे ना. I think the शुरुआती वाली सभी ना let the answer be x and then you write down all conditions on x. Okay, and find out what x is. Okay. So इधर भी यही करते हैं. You see, advanced तरीके में. Let the function be this. Okay. So function को express करते हैं basis functions. Okay. So all kind of series that you have, power series that you have. अगर कुछ नहीं मिलता है तो you can have that power series. Okay, which is let's say x square, x cube, x4, something like that. You see, अगर एक ही variable है, multi-variable, then it becomes difficult. Okay. So वो basis functions हैं. Now the issue is that linear combination of basis functions, you see that those basis functions have to be linearly independent, otherwise you'll have a problem, you see. Okay. So you'll have to generate that basis, and this is how many functions, infinite number of functions have to be there. Okay. And then linearly independent. Then the biggest question is that the unknown answer, you should be able to express it uniquely in terms of those. Which means that this basis function, and this is where I said, a little bit of, I won't say cheating, but kind of cheating only has been done. What they say is that I have this box of functions, this is the basis function, and all the required functions I should be able to generate from this box. Okay. So which will mean that it is a good box. You see, it has almost everything in it. You see, so that all the functions that are possible, because the answer can be anything. And if the answer cannot be written in terms of these, which means that you're precluding some things to be an answer. And you're saying that I'll only look at those answers which can be written in terms of these, I'll not look at other answers. Okay, unless that is the case, you see, so this is the fundamental problem, you see, that the box should contain those functions which, combined, a combination of those functions should be able to give you all possible functions in that space. Okay, so you must have heard terms like ये Hilbert space होती है, कुछ Banach space होती है, all kind of algebraic terms, वो तुमको डरा देंगे. Okay, फिर तुम कहोगे नहीं यार ये छोड़ो ये पढ़ देते हैं. Okay, ऐसे करके तुम ये करेंगे, but इसमें कुछ difficulty नहीं है. Okay, बहुत सारे proofs हैं, lots of proofs and great mathematicians. The issue is कि whenever we define that, क्योंकि वो box हमें define करना पड़ता है. Box is in our hand. You see, we define that box. Which functions do we choose? So do we choose x, 1, a naught, x, or x dot 0, x square, x cube, is that this? Or ln x, or sin x, sin 2x, sin 4x, something like a Fourier series. Okay, so we do all these kind of things. Okay, we can choose that box. Okay, but अगर कोई भी box नहीं मिलता है तो this power series is good enough. You see? So you say my function fx is a naught plus a1x plus a2x square plus a3x cube and ऐसे करके चलता रहेगा. Okay, and if you are very clever, then you say okay, my x is lying between 0 and 1. Because the problem is that you'll have an infinite series, you see? and which means that you will not be able to, unless by some method you are able to get that sum. इनफाइनाइट टर्म्स तो यूज नहीं करोगे, कंप्यूटर भी यूज करेंगे, which means that you use only some of those, okay, and which means that the neglected one should not have a greater impact on the ones that you have selected. तो power of one वहाँ use होती है, because power of one in a power series would very easily tell you कि if x is less than 1, then x ले लिया, x square ले लिया, x cube ले लिया, बाकी सबको छोड़ दिया, क्योंकि बाकी सब इससे तो कम ही है ना. Of course the coefficients you may say कि coefficients ज़्यादा हैं तो हो जाएगा, but in general you see there will be less, okay. So इसके तो power series becomes very special, okay. Sin 2x, sin 4x, Fourier series is also very special. इतने लोग पढ़ा रहे हैं, तो क्यों पढ़ा रहे हैं? इतने सालों से पढ़ रहे हैं, क्यों पढ़ रहे हैं? Power series, Fourier series क्यों पढ़ रहे हैं? Because power series is very easy, you see. इतने polynomial के बाद छोड़ दिया, okay. फिर polynomial भी है. Then there is a fundamental theorem of algebra. Do you know this? There is a fundamental theorem of algebra. Anybody? Yes. वहाँ तक नहीं, पर उससे पहले भी है. That a polynomial would have n roots. You see, nth degree polynomial would have n roots. You see, and it kind of works. It is so important कि उसको fundamental कहते हैं. Okay, so power series is a polynomial in x. Easily दिख जाता है. It will have so many roots. And all this is also relevant to thermodynamics, because we will see why it is relevant. So you get the basis functions, okay, दो तरह की series, power series and ये sine वाला ले लिया, but there are other series also. Power series है, x, ln x भी लेते हैं, कई बार exponential x भी लेते हैं, exponential इतना नहीं but ln x we take many times, okay. So x is very interesting. Power series is very interesting because simplest है and polynomial है and control है of truncation. You see, otherwise if you truncate you don't know. You see, sine में कैसे, you know, sine तो घूमता रहेगा. We just now talked about the RPM and the problems. You see, sine है, sine 5 degree, अब जरा sine 365 भी वही है. क्या है, मतलब एक राउंड घूम लिया वही. तो छोड़ दिया उसको, कब छोड़ेंगे? 5 को छोड़ दिया, 365 ले लिया, पर 725 लेना पड़ेगा, वो भी सेम है, छोड़ोगे क्या? प्रॉब्लम है ना. सो एनीवे पावर सीरीज में भी लो, अगर लेस देन 1 है छोड़ सकते हैं, तो इवैल्यूएट हो जाएगा. ओके, सो इफ z इज रिटन एज we can find out the coefficients, okay, but z 1 से ज़्यादा भी हो सकता है. You understand? अगर 1 से ज़्यादा हो तो क्या करेंगे? If something is more than 1 तब क्या करते हैं? And we still want to be sure कि इसको छोड़ें, इसको ले लें, because वो एक tricky चीज़ है. Because you see, ये fundamental, this is fundamentally true कि the solution which is, let's say, because z by itself is not enough, z naught is enough, we want to have more, you know, express it, find the other changes also. यही issue है मेरे. So we said करते क्या, maths में क्या करते हैं? We say okay, we'll express it as something and we'll find the coefficients. We'll express it because if we express it as an infinite series, then we are not making any mistake. That's not an assumption. That's entirely true. The moment we say we'll truncate after 2 terms, we'll truncate after 3 terms, we'll truncate after 4 terms, then it's an assumption. Okay, and we want our assumptions to be good. Okay, and which means that if you are neglecting, that should not be, you know, more than what we have kept. Okay, अरे यार penny wise pound foolish सुना है, pound छोड़ दिया penny रटी, ये तो बेवकूफ़ी है ना. You know, वही चीज़ है यार, ये term छोड़ दिया, ये ज़्यादा है, ये रख लिया जो कम है. You know, and the idea is how to get z, and z equal to z naught or z equal to 1 is not enough. तो हमने कहा z is something like z square, z ऐसे करके, as long as z is less than 1, you see, z squared, z cube kind of works. And fitting में will not choose all of them. You see, there are many reasons. One is that will not go to infinite, so there is an upper bound, we can take lots of terms. But we would still like only 1, 2, 3, 4 terms, not many. Okay? Which means that the first 2, 3 terms should have the most weight. Okay? How do we ensure that? Okay? See, there are two things. One is at the other end. कि infinite नहीं जा सकते तो कहीं ना कहीं finite करना है. But maybe 100 terms, maybe 200 terms. Okay? But 100, 200 fitting for all that, even with all the computers and everything, it's not so easy. And especially if the power is also increasing. Okay? So, बहुत जल्दी बढ़ जाता है ना, power 2, 3, 4, 5, 6, 7. So let's say we want only first 2, 3, 4 terms. But 3, 4 terms should give me a good estimate of Z, or give me a good estimate of the answer. This problem is different from the imposition of कि we will not be able to go till infinity. You see, there are two issues. Okay, two different issues. So for these kind of series, there is a special term. Okay, and most of the time you are working with those. Okay, so while one is worried about the convergence, कि converge तो करना चाहिए ना, अगर converge नहीं करेगा तो आंसर ही नहीं है ना. But there is a very fast convergence. So first 2, 3 terms are good enough. So वो expression basis function has to be chosen in a way कि first 2, 3 terms can give us answer. You see, so पूरी creativity in analysis, in research is to find that basis. कि express किस terms में करें. So the first 2, 3 terms give us the best representation. Okay, because we don't want to be looking at 100 ones. You see. तो क्या करती कंपनी कहती है स्कॉलिस्टिक एबिलिटी क्या है, लीडरशिप पोजीशंस क्या करी, ये क्या करते हो, 4-5 चीज़ें देख लेती है, rather than looking at everything that you have done. ये 3-4 चीज़ें हमने देख ली, you have a good idea तुम क्या है. Okay, so practical use है, we have to define, design a system कि 3 terms में ही मुझे पता चल जाए बेस्ट क्या है. Okay, या 4 terms में ही पता चल जाए. Okay. So all of this what we do here is kind of related to designing a kind of measurement method, evaluation method, and so many things. See? So कहते हैं Cauchy convergence. Okay. So if a series is convergent in a Cauchy sense, ये सब बड़े-बड़े mathematicians हैं. अगर इनको mathematician की तरह से जाओगे तो almost half of you would be turned away. मतलब तुमको बहुत repulsion होगा. Okay, वो उसकी the language is very different. The terminology is very different. वो symbols बनाएगा, ये बनाएगा, बोलेगा कुछ. Just to say something, 1000 proof देगा पहले. Because they don't want to just say something. So completeness बताएगा क्योंकि set अगर box complete नहीं हुआ तो फिर you are excluding some samples. Okay, you are excluding some answers. अगर box ही नहीं complete हुआ तो. Okay, उसमें ही पूरी दुनिया, पूरी जिंदगी चली जाएगी. Just to prove that this set of boxes is a good box. ओके तो एक कर देते हैं, वो कहते हैं कि बॉक्स मेरा ऐसा है, आई रिविजिट द चीटिंग, वो कहते हैं बॉक्स मेरा ऐसा है कि उसमें ये तो है, एंड वी एज्यूम कि जो कुछ और चाहिए इसको कंप्लीट होने के लिए वॉट एवर एल्स इज रिक्वायर्ड टू मेक इट कंप्लीट इज ऑल्सो देयर. समझ रहे किस लेवल की चीटिंग है ये सब मैथ्स वालों से आ रही है. जो कहते हैं we are very exact, we are this and we are that, and equality होनी चाहिए, inequality होनी चाहिए, इतना सब गेम खेलते हैं लैंग्वेज के साथ में. ठीक है, सो we say कि ये तो फंक्शंस हैं and whatever is missing we deem it to be there. So एक और कॉन्सेप्ट आया डीम का. डीम्ड बहुत पावरफुल कॉन्सेप्ट है. So if nothing else is kind of giving you the solution, you see, try to think यार deemed को use करते हैं, इससे मिल जाएगा solution. Okay, so it's not only in analysis, everywhere it is being used. Okay, wherever we run into a process where we have to make a decision and the information is not there, we say deemed. Okay, ये wing में cricket खेला कभी? ऐसे टेनिस बॉल से इधर उधर छोटी जगह पे डिक्लेयर्ड 4 रन्स, इधर चला गया डिक्लेयर. हम जब डिक्लेयर करते हैं, हम डिक्लेयर समझ नहीं पाते, सोचते डिक्लेयर इसलिए कहते हैं बड़ा है, हम राजा बन गए, हमने डिक्लेयर कर दिया, 4 रन्स डिक्लेयर, ऐसा नहीं है। वो डीम्ड वाला कॉन्सेप्ट है कि इधर किया देन इट इज डीम्ड टू बी 4 रन्स। ओके जी, अगर एग्जाम में सर हिल रहा है इधर उधर, डीम्ड टू बी चीटिंग, क्योंकि इनपुट है ही नहीं। क्या करेंगे? डीम्ड इज अ वेरी पावरफुल कॉन्सेप्ट। जब कभी डिसीजन लेना हो, एग्जीक्यूटिव पावर यूज करनी हो एंड अलाइनमेंट फ्रॉम द वर्ल्ड इज देयर, मतलब ये जरूरी है। यू सी द वर्ल्ड हैज टू अलाइन। अगर सब अलाइन नहीं हुए तब तो प्रॉब्लम है, फिर तो वन मैन शो हो जाएगा। ओके, वन मैन डिसाइड्स। कांग्रेस ने भी नहीं डिसाइड किया, पता है तुम्हें? उसके साथ वाले जो लोग हैं उन्होंने भी नहीं डिसाइड किया। जस्ट 1% डिसाइड्स, यू सी। एंड हाउ कुड 1% डिसाइड? बिकॉज 1% हैड एक्सेस टू चैट जीपीटी। कभी सोचो, of all the theories of causation, if this kind of artificial intelligence was not there, a duffer could not have used that artificial intelligence to be so powerful or to take a decision. उसको necessarily consult करना पड़ा, और consult करते तो कोई एक तो समझाता कि क्या कर रहे हो भैया। Are you getting on to this? कि क्या हुआ? वो पार्टिया कहाँ है हमारा, वो स्टॉक मार्केट वाला? वो नहीं है इधर। कहाँ गया मेरा गुजराती फ्रेंड? है इज नॉट देयर टुडे। So just imagine, because 1% had access to all the data, could do all the calculations, उसने कर दिए। अगर नहीं होती एक्सेस तो जाता ना, पूछता लोगों से, किसी इकोनॉमिस्ट को तो बुलाता, किसी तो फॉरेन रिलेशंस वाले, किसी से तो बात करता, 1 से 2 तो भले ही ना। ओके, तो सी क्या क्या होता है दुनिया में, ये सब एक्सेसिबल था। सो नाउ कमिंग बैक टू दिस, ये डीम कर दिया, तो डीम इज ऑल्सो अ ट्रिक, वेरी पावरफुल ट्रिक। इफ यू कैन नॉट प्रूव समथिंग, यू कैन डीम टू बी यूनिवर्सिटी। वो चेक नहीं कर पाए कि यूनिवर्सिटी की ऑल कंसिडरेशंस हैं, सब कुछ है, ये नहीं है, वो कहता है डीम टू बी यूनिवर्सिटी, यू आर डीम टू बी दिस। और हम बचपन में खेलने लगते हैं, डिक्लेयर्ड 4 रन्स, डिक्लेयर्ड आउट, रूल नहीं है, भी डिक्लेयर्ड आउट, डिक्लेयर्ड 6 रन्स, डिक्लेयर्ड 4 रन्स, डिक्लेयर्ड 1, कैसे करते हैं बचपन से सिखा। कहते हैं कि when this generation will grow up and will have some wisdom, बच्चे को भी होता है, बट बच्चा एक्सप्रेस नहीं कर पाता, हाथ छोटे छोटे होते हैं, उसको भी बहुत विजडम होता है, पर इधर आते आते तक वो फुल्ली कंडीशनड है ऑफ दिस कॉन्सेप्ट ऑफ डीम्ड, कि ये डीम हो गया। ओके, तो इधर भी डीम कर दिया, तो यू अंडरस्टैंड दिस ट्रिक। And I can tell you, whenever in your life if you are not able to take a decision, ये एक scapegoat है। You cannot scapegoat, but this is a method to be used. Okay? Management school में नहीं पढ़ाते हैं, क्योंकि management school में management पढ़ाएगा, ये सब कहानी से सुना नहीं सकता। Okay? पर मैं तो सुना सकता हूँ, मैं इसलिए सुना सकता हूँ because my responsibility is to tell you things that you can use all your life maybe. Okay? So this basis, we choose this box properly, we express it, z equal to z square, z cube, ये तो virial equation, ये virial है ना, ये तो पता है ना, this virial equation of state। तो z वाली तो चल गई, z कम है, अगर z ज़्यादा होगा फिर तो z cube से काम नहीं चलेगा ना, you have to then go till infinity। फिर क्या करेंगे? नहीं, कुछ आंसर तो यार मैं ही बोलता रहता हूँ, नॉट गुड, यू सी। गेट नियरिंग द एंड ऑफ द कोर्स, यू शुड ऑल्सो स्पीक। ऐसे करते थे, अगर x 1 से ज्यादा है, 1/x तो 1 से कम होगा, ये कब सिखाएगा या नहीं सिखाएगा? सिखाया, किसने सिखाया? मैथ्स में सिखाया किसी ने, इधर नंबर आ गए, खत्म, एंड, वो आगे नहीं किया। ओके, अब समझ में आया तुम्हें कि वेरिएबल इक्वेशन 2 फॉर्म के क्यों होते हैं? ऐसे एंड विच वन शुड बी यूज्ड? पूरी किताब पढ़ दोगे ये नहीं समझ में आएगा, जो कि इंट्यूटिव है, स्ट्रेट फॉरवर्ड है, एंड यू ऑलरेडी हैड ऑल द नॉलेज. ओके, सब पढ़ाया गया है. When which form of the virial equation has to be used, and of course वो कॉशी वाला जो पढ़ाया था वो भी बड़ा इंटरेस्टिंग है. You see, so you in designing systems, okay, so in designing systems में क्या करते हैं कि if you are worried about the major impact पहले दूसरे तीसरे में, तो you think in terms of a Cauchy series, not Cauchy series, Cauchy convergent series, कि इस तरह का काम करेंगे. अगर टेल पे परेशान है, you see, ये कहते हैं ना गरीबों से भी गरीब, उसका ध्यान देना है, तो फिर दूसरी तरह से सोचना पड़ता है. तो दुनिया पलटनी चाहिए, दुनिया पलट देते हो तो ये आगे आ जाता है. ओके, सब जो रिवोल्यूशन होती है, ये सब होता है, अरब स्प्रिंग हुआ, ये हुआ, इतने सब जो होते हैं इसीलिए होते हैं, तो क्योंकि कोई तरीका नहीं है उसको फोर फ्रंट करने का, अनलेस यू रिवर्ट द सिस्टम. वो ब्लड बाथ होता है, साइलेंट होता है, जो भी होता है, बट दैट इज द ओनली वे, और कोई तरीका ही नहीं है. वॉट एवर फिल्टर यू विल यूज, कि उधर जा रहा है, इधर जा रहा है, अल्टीमेटली ये शुरू के टर्म्स में ही यूज हो जाएगा. अगर उसको 10 होगा तो इनको 100 मिलेगा. तो तभी हो सकता है जब लाइन ही पलट दो, तभी सोल्यूशन है. देयर इज नो सोल्यूशन. ओके, अदरवाइज ये धीमे धीमे करो तो यूज से कि सभी को ऊपर ले जाते हो, तो वो भी कर सकते हैं. ऑल ऑफ अस कैन बी इन एक्साल्टेड स्टेट. एक आश्रम है, उधर जाओ, सब लोग ही ऊपर चले जाएंगे धीमे धीमे. Okay, सबका विकास हो जाएगा. नहीं, ये कुछ समझ में आया? आई एम जस्ट गिविंग यू एनालॉजीज. ओके, सो विरियल इक्वेशन ऑफ स्टेट बनाई, ये एक मेथड है. कंप्लीट बॉक्स का सेट बनाते हैं, कंप्लीट सेट बनाते हैं तो कंप्लीट स्पेस हो जाती है. देन दिस बॉक्स हैज टू वर्क, एंड दिस इज वन ऑफ द इश्यूज दैट यू विल फेस इन योर लाइफ. तुम्हारी जनरेशन विल फेस दिस, इज ऑलरेडी फेसिंग दिस, बट इट विल फेस दिस इवन मोर. ओके, you are getting a solution. Let me see how many of you can relate to it. You are getting a solution, okay? वो solution का जो box है, उसके बाहर का solution नहीं आएगा. ये जो method है ना, this method will give you the solution that is only possible with whatever is there in the box. ये out of the box solution नहीं आने वाला. और आउट ऑफ द बॉक्स नॉट ओनली इन टर्म्स ऑफ इनोवेशन, और नया सोल्यूशन. इनोवेशन छोड़ो, इनोवेशन इज अ वेरी डीप कॉन्सेप्ट. ओके, कोई स्पेशल सोल्यूशन, ओके, क्रिएटिव सोल्यूशन, उसकी बात नहीं कर रहे. आई एम टॉकिंग अबाउट द बायसेस. कैन एनीबडी एक्सप्लेन एंड टेल मी हाउ इट इज इंपॉर्टेंट एट दिस स्टेज एंड इज गोइंग टू बी इवन मोर इंपॉर्टेंट इन योर लाइफ, परहैप्स द मोस्ट इंपॉर्टेंट थिंग इन योर लाइफ. अभी तुम देख चुके हो चैट जीपीटी से क्या हो सकता है. 1% became so powerful. जी, उसको आदमी नहीं चाहिए थे, मशीन नहीं सब कर दिया उसके लिए. अगर आदमी चाहे होते तो आदमी से डेटा लेके नहीं आता, आदमी आता पूरा. जी, मैन और वुमन वुड हैव कम एज ए होल, नॉट जस्ट एज ए डेटा सप्लायर. कुछ बताता कि क्या कर रहे थे. मशीन नहीं बताती, उसका बताएगी, बट मशीन तो नहीं सुना. आदमी तो हर तरह से बताता है ना, ऐसे मुंह टेढ़ा करके बताएगा, गुस्सा करके बताएगा, इधर देख के बताएगा. सब कुछ कम्युनिकेशन और होगा ना. मशीन तो बेचारी एक लाइन लिख देगी, बी केयरफुल. सुना नहीं सुना? ताकि ये हो रहा है टेक्नोलॉजी के जब ऐसे. अब तो आएगा नहीं टाइम, पहले आता था स्कूल में, टेक्नोलॉजी इज अ बून और अ बेयर, जो हम लोगों ने भी लिखी ना, आता थे. तुम्हें भी आए? सुधरेंगे नहीं लोग, मैंने भी लिखे. सो एनीवे, सो क्या है, कोई कैन एनीबडी टेल मी ऑफ द इम्पेंडिंग थिंग दैट इज गोइंग टू बी इवन मोर इंपॉर्टेंट एंड इज रिलेटेड टू दिस? Completeness of the box and the box being good and you getting a solution of the box. तुम बताओ यार.
मशीन लर्निंग
इतनी बायसेस आएंगी. मेजर इशू तो यही है, और कौन सा इशू है? यही तो इशू है.
only data available will be fitted, extra data will not be there. So
नहीं, उसके मेथड्स हैं. You see, that is there. डेटा में इतना इशू नहीं है. You see, because fitting में we have faced this problem earlier also, so we know a way to generate, you know, जैसे म्यूटेशन कहते हैं ना, all these genetic algorithms हैं of control, उसमें म्यूटेशन कर लेते हैं. इवोल्यूशन कर लेते हैं. ओके, सो दोज मेथड्स आर देयर टू गेट इन द न्यू सोल्यूशन. वो हम कर लेते हैं. ओके, ये मेथड्स नहीं है ट्रेनिंग में. ओके, सो इफ यू आर लुकिंग एट इट, डू ऑल ऑफ यू अंडरस्टैंड कि यू विल बी इंक्रीजिंगली reliant on a machine to give you an answer? You already are, you see. You'll be even more reliant, you see. And that machine would give you not only terms results for data, but all other kind of decisions also. Will help you in making all the other decisions also. And all those decisions would be based on some history, some training, and that intelligence would come out of that experience. Okay? And how will it give you something that is not there? तो biases कहाँ से? You see? तो पढ़े लिखे लोग ही रूल बना रहे हैं. हमने रूल बनाया, अपने लिए फायदा कर दिया. हम उसको accessible नहीं कर पाए टेल को, because the tail had no representation, tail had no voice, tail was not used in the learning. अगर टेल की किस्मत तो हमें पता ही नहीं. ओके, तो टेक्नोलॉजी से और मैग्नीफाई हो गई प्रॉब्लम. तो दिस इज गोइंग टू बी अ मेजर इशू विद. ओके, और वो यही कह देगा डीम्ड वाला एल्गोरिथम लगा के. एक्सक्यूज क्या होगा डीम्ड वाला कि 10,000 डिफरेंट सिचुएशंस में 10,000 डिफरेंट इंस्टेंसेस पे हमने ट्रेन किया था एंड इट इज डीम्ड दैट इट इज ऑल एनकम्पासिंग सैंपल स्पेस, और हमने सब जगह एक्सपेरिमेंट कर लिया. ऐसे करके डीम्ड वाला आर्गूमेंट लगा के चला देगा. डीम्ड वाला आर्गूमेंट क्या है? 280 इन फेवर, 213 इन अगेंस्ट. ये डीम्ड का आर्गूमेंट है. ये हम सबसे नहीं कर सकते, रेफरेंडम नहीं कर सकते, हम डीम्ड कर लेते हैं. समझ में आया कि डीम्ड इज सो डीप. समझ में आ रहा है? अब अच्छे से समझ में आ डीम्ड का इशू कि कैसे कैसे रिप्रेजेंटेशन होता है. So all this is a variant of the. Okay. Anyway, अगर फ्री विल भी देखेंगे, एक एक लोगों से भी पूछेंगे तो अभी चेक किया जब वो गुस्सा है, अभी चेक किया जब उसकी सैलरी आ गई, अभी चेक किया जब उसको नोटिस आया. आदमी ही डिफरेंट है हर बिहेवियर में. सो इवन लोग कहेगा कि यार क्या अंतर पड़ता है. आदमी ही डिफरेंट है, तुम अभी इधर वोट करो, अभी उधर वोट करो. ऐसे अच्छा हम डीम्ड मेथड से ही कर लेते हैं, लाइक अ रिप्रेजेंटेटिव मेथड. ओके, सो what is the solution for this? क्योंकि ये एज्यूम करते हैं कि दिस क्लास हैज नॉट ऑप्टेड फॉर COL, तो दिस क्लास वांटेड टू मे बी, हम फ्लैटर कर लेते हैं कि केमिकल इंजीनियरिंग पसंद थी या उधर नहीं जा पाए या जो भी रीजन है, यू आर हियर, यू हैव स्पेंड दिस टाइम. ओके, कैसे कर सकते हैं इसको? हाउ कैन यू गिव एन इनपुट सो दैट दीज थिंग्स जो डिसीजन मेकिंग के लिए ट्रेनिंग है, those training methods can be improved. Well, we started out trying to explore what Z is. Z को ऐसे तो बहुत आसान था लिखना कि Z is this, Z is this, Z is this, ये relation है. But then what actually Z is and how can you use this approach to kind of solve for any other Y somewhere else. Okay, वो I hope you have been able to understand. But because we have an opportunity कि हम यहाँ तक आ गए हैं, we can now discuss a little bit about कि ये जो training methods हैं, how can we improve those training methods. कैसे कर सकते हैं? So that we get rid of these biases. Okay, just think of this. There's a lot of scope in this. You see, कि how can we data में कैसे करते हैं? We generate that data. You see, optimization में you'll study that. Genetic optimization techniques. ये आदमी भी क्या करता है? हम क्या कर रहे हैं ह्यूमंस में? कोई जीन इधर उधर घूम जाता है, जम कर जाता है, ये कर जाता है, नई चीज़ आ जाती है. We do all that. You see, नेचर में ये होता है. You see, all kind of diversity comes in because of this. Okay, inbreeding नहीं होती. You see, so data में भी हम कर लेते हैं. We generate all kind of data. पर ये तो language models हैं. You see, these are not data models. You see, तो language model में क्या करना होगा? We have done it in the past. We have solved these issues in other places. You see, how do we handle it in data? ये issue, where is the attendance sheet? तो ये while I take the attendance sheet, ये थोड़ा सोच कहना कि the major exam, what kind of major exam would you like? Why, how, what, कौन सा? Mixed.
Same as minor.
Somebody comes in late. But there's no way you can go on the road. It's not in, I can drive. You can drive. Right? No, really. Next time you're driving, you can call me. Come and see how you do. Where's the car?
At home, but I can call it wherever.
So wherever it is here, you should. But how did you get a license?
It was complex. I had to get to the office. But
It was possible.
yes, it was possible.
I can help you with that if you want to write it. Or you can write it yourself. Because you have done that, see? So write us.
She's looking at how biophilic elements can happen. So like when we go in front of nature, it makes us feel relaxed and calm. So that was what we used to about. Okay. She's part of Reiki Mind Lab, and there are all wonderful things I can talk about her, but I think she's not going to like it. So maybe I'll just invite her, and she'll be there for about an hour or so. Let it go.
Thank you so much, Professor Jyoti, for this grounding exercise. I hope we all are awake from our afternoon nap after this wonderful experience. This while I kind of fix my slides here and also fix this mic, I want all of you to scan this QR code. And there is a very short reflective exercise. And request there are
What date is today? 3rd.
3rd April.
So I think we are celebrating politics today. So we have a quiz for today. Tomorrow we will have a quiz for ethics. As we get closer to the election.
Sir. Sheet है.
अच्छा आपको हो गया?
नहीं.
Okay, quiet please. Fine. So, shh, quiet. So we'll give a quiz for 20 marks. This is to kind of acknowledge that there is politics in the air. So we said, okay, we'll have a quiz for 20 marks. Tomorrow we'll have a quiz for 30 marks. Okay. ठीक है होना चाहिए. So we're looking at ideal and real, and also two concepts between ideal and real, and also reversible and any other. You know, it's not really right to call something as irreversible as a class. It's just that, you know, all processes, some of them would be, or rather very few of them would be reversible. Okay. So we discussed this ideal thing. Okay. And the major issues in thermodynamics would be, just to recap, would be properties of these, how do they change? Okay. So we have to find a way. Right. So the strategy is that we have to find a way to compute property change for ideal. Okay, which means that the ideal has to be chosen in a way that we should be able to compute the property changes, okay, or understand the system. And of course, many other things that, you know, for practicality, for utility, all those things would govern your choice of the ideal. Okay, but if you kind of use the choices that are already there in literature, lot of history is there, lot of work that has already been done on them, then you can make use of all the past work if you conform. Okay, so that is the price for conformity. That things that are already available, you can make use of them. That should not stop you from devising your own idea. You see, that freedom stays with you. Okay, and there may be many systems, many situations where you would like to analyze a system or situation, but you know, there is no history. So there, you know, it will make a lot of sense to choose something that is ideal. You see, so ideal is absolutely your choice. You see, Of course, there is a terminology people have accepted. So ideal gas means something, that's already accepted. But you can have your own definitions. Okay. So the trick is find relations of these. Then how do you kind of convert from there? Okay. So what are the tricks? So because you have already done some examples or some tutorial sheets, so there are concepts like fugacity. Have you heard of this word? Fugacity? Tutorial mein aaya na? Yeah, this is something between, for gases. Okay. So there is let's say pressure, okay, and then there is something called fugacity. Some property of gases, and so this is a bridge between real and ideal gas. This is one way to find out. You see, typically you would like to have some coefficient. So that is the best way. Rather than having a very complicated expression, if you can just have a coefficient, that the real things are so many times of the ideal things. You see, so once you have the ideal, you can very easily compute the real ones. And in many cases of, let's say, technological importance, and in many other cases also, just this idea that whether the real property is less in value than that of the ideal, or the real property or property of the real system is more in the value. You see, even this is enough. You see, at times. So you should know the trend that this is more, this is less. Okay? Or this is 10% off. So you, at times, if you are not able to compute the property of the real system, okay, sometimes these directions, these bands, they help. Because in computation, see, listen to this carefully because we mostly discuss. You see, I'm not writing everything that I'm saying. So you miss out on many things. See, and this becomes very, very important because when you do some very large computation and you need to use the thermodynamic property, and there is a cost associated with those computations. Okay. And you have to then see whether that cost is justified or not. So to what accuracy do you need these? Okay. So that decision, of course, in any process you need to make, that whether so much resource is going into this computation and whether you need it that precisely or with this much accuracy. So that decision anyway has to be made, and in this property estimation also, that decision has to be made. Okay. And there is a cost associated with this. So we should have a way to compute things for ideal systems, and that is how the ideal systems have been designed in thermodynamics. The way we study it, classical thermodynamics, that already exists. Okay, so things like activity. You remember for liquids, activity coefficients. Have you heard of this term? Similarly, you have fugacity coefficients. Okay, and if you remember, some of you may remember, when you were looking at reaction rates. Okay, so reaction rates, if you remember, you don't use the mole fraction. What do you use?
Concentration.
That is mole fraction. In a way, mole fraction only. You take out the denominator. What do you actually use? Does any one of you remember this? That you write a rate equation, K is C1 square, C2 square, or X1 square, X2 square. But you're not actually, if you look at what the equation is and how it was originally developed, there's something else. Not the mole fractions, not the thing that you measured. What was that? Active mass. Remember? And there is a difference between the two. Okay, so everywhere, you see. So while mole fraction is something, you compute, so there is a value that you can figure out by measuring. Okay. But active mass is something that is hidden. You don't know. The mole fraction may be this. Active mole fraction may be something else. You remember this? You see? Which means that the moles are there, but maybe all of them are not participating in the collisions, you see. Which means, reaction, how would it happen, if you need two reactants, at least two molecules, you see. Then if they have to collide, you see, that's the collision rate theory. That's how you get K C1 square, C2 square. Okay, that so many they collide, there is an energy barrier, and some of them collide, and then some of them stay there, some of them get converted to reactant, some of them just come back. You know, all those kind of mechanistic way of looking at a reaction. Okay, so you remember there are always, you know, these concepts of active mass. Okay, then there is fugacity, then there is activity, and all of these you would get by some method. See, there will be some methods to compute that. Okay, which means there will be a method for ideal material, and there will be a method for how to convert that ideal to real. Okay, so this is one step, which means this transformation. Okay, and similarly for processes. Okay, so what is the work that will come out, or what is the work that has to be done, or how much heat will come out, or how much heat has to be given, what will be the changes in the internal energy, what will be the changes in the enthalpy, you know, those kind of things. You look at processes. Okay, and then in these processes you say, okay, things can be done for a reversible process. So if you can figure out what can be done for a reversible process, okay, so two concepts. When you analyze a process, there are two things that you need to worry about. You see, the nature of the process and what are the milestones. You know, what are the anchors? What can you specify during a process? You see, so any process, you see, it may be, you know, the questions may be spread across, let's say 6-7 chapters. You know, different processes. There is that closed system, open system, flow system. You know, same pressure, same volume, all those kind of things. You see, but the key is, if you have a process, you should, you know, be able to know the kind of process. You see, so the how do you describe that process? You see, so that is very, very critical. At times you don't know. You see, so what is happening during the process. Okay, so there is no handle on the process. You see, in that sense. So for gases, typically the handle is, if you have heard of this word, or maybe gamma is a technical word. So you say, okay, the process is defined by PV, gamma is constant. So the pressure and volume and something gamma over there, you see, is constant. So this is the description of the process. That while the process is happening, this is true. Okay. Otherwise, you follow the process, you break it into small steps. Okay. And then you say that this is my process. Okay, so you can chart it on a pressure, volume, pressure, temperature, volume, temperature graph, and you can say that this is how the thing is happening. Okay, at this point we don't have the temperature, entropy, and enthalpy, of course, yes. So you can chart it out in an enthalpy, temperature, enthalpy concentration diagram also. Okay, so you can figure out what is happening, you know, in the process, but it's not easy. You see, people may say that, you know, this is the process that is happening, but what is the actual process? That's never easy to find out. Okay, so you say, okay, so things like these, they describe the process. So you know the description. And you also look at what are the anchors, what are the milestones, and those would be the state functions, state properties. So you say, while this process is happening, and you measure what the pressure and temperature is, because this is something that you would measure. What are the properties? So pressure, temperature, mole fraction, flow rates, all those can be known. Okay, how much amount of material is there? What is the pressure of the material? What is the temperature? What is the volume? You know, those kind of things you would know. What is the flow rate? Okay, but then you say these are the state functions. So if I know this, I know this. I know the value of these things. Okay. So the process has come from this state to this state, doesn't matter how it came, but at least at this point it is here. Okay, so there are ways to say that, okay, these are some of the, I would say milestones, but these are some of the anchors, you see. So the process will pass through these. Okay, and the process can be defined by something as vague as this. PV gamma is constant. Okay, this is how the process happens. So the trick is, you design a reversible process which goes through those milestones, okay, and or those anchors, you know, true to those anchors, and you say, okay, this is my reversible path. You should be able to compute what is happening in that reversible path. See, that is the key. Like you should be able to compute what the properties for ideal systems, you should be able to compute what is happening in the reversible path. You see? So that is the key. If you are not able to compute what is happening in the reversible path, then you are in a soup. You see? Even then you are not in a soup because you would have a lot of help, you see, otherwise also. But then things are not very easy. You see? Then some things are not under control. Okay? So reversible and ideal, you should be able to make use of these state functions, okay, state points on that diagram, okay, and the process has to be represented somewhere, okay, but doesn't matter what people say, process is not understood. You see, somebody say that this is going like this is going, it's not understood, you see, because what is happening we don't know, anything can be happening, okay. All kind of friction is there, all kind of irreversibility is there, all kind of heat losses are there. How do you know that this is the process? Okay, you say that this is a reaction that is happening, or maybe the reaction is not happening, and in a heat transfer, you see, that's some course that you are doing. You know, how would you know that that this is the heat loss at this point? You see, look at a double pipe heat exchanger or a heat exchanger. You say, okay, how do you know that? You see, you'll say, I'll compute for no heat loss. Okay. So this stream comes in, this stream comes in, this much heat transfer takes place, this is the outlet temperature, this is the inlet temperature, these are the flow rates, these are the specific heats, okay? And the losses are, let's say, 10%, 20%. But do you really know at which point what losses are happening? Is it 10% in the beginning or 10% in the end or in the middle? You have no idea. Maybe it's not required. You just want to know that if it has to be, if I have to recover this much heat, this is the likely temperature that I'm going to get. Okay, so, but at least if you are not able to solve for the reversible one, then there is a problem. This is path. And if you are not able to solve for ideal ones, then there is a problem. You see, estimating the real ones from ideal is a method. You see, you may say some kind of, fugacity or activity. Many models for these. Okay, many models for these. Not just one, many models. Okay, and then there will be fugacity coefficient, there will be kind of activity coefficients. Then reversible. This is, you need to describe this. Okay, which means that you need a diagram. Okay, so if you need a diagram, and the diagram would be V diagram, HT diagram, whatever, kind of helps you. Okay, so you can have an enthalpy diagram.
Kept a pen, marker or pen he kept.
Kept a pen there. Bomb over there. You look like a student. Oh, with a special pen, a stylus pen. Student.
नहीं forget वो staff.
Staff, sure. सोचा कोई स्टूडेंट को कुछ अंतरात्मा की आवाज आई, गलती से चला गया, लेके आया. Staff का तो काम है. Anyway, but unusual है that you should find out. क्या पेन रख रहा है, why? all of us. So we need a diagram for it. Okay, and that diagram can be as and when those Chinese coordinates, those coordinates will be there. And in that diagram, you need to be able to figure out what is happening. Okay, which means that all the thermodynamic relations. Okay, jitne bhi ye sab, all confusing things that are there in thermodynamics. The worst part of thermodynamics, all those Maxwell relations, all that is confusing. All that is used here. Typically here, not so much here. ये तो फिर भी easy. Sir, difficult चीजें, all of them are used here. Okay. So, and what are the coordinates? How is one coordinate related to the other one? Once you do this, you have some efficiency, or you have some kind of coefficient of performance. like in, okay, efficiency also, you will find out that there are two places where things are more than what you would expect. So it's very counterintuitive. So let's say in mass transfer, you can have efficiencies that are more than 100%. Have you come across that already? Anybody? Okay. Efficiency more than 100%? Chaudhary? Efficiency more than 100%? Anybody else? Efficiency more than 100%? Can it be there?
No, sir.
क्यों नहीं हो सकती भाई?
Conservation of mass will not
एफिशिएंसी की बात करें तो मास ले आए.
but
Chemical engineering is a field where at least at two different places you have very counterintuitive things in one place, and it's very widely used. The efficiency comes out to be more than 100%. Okay? और ये मास ट्रांसफर कोर्स नहीं किया? जब करोगे तब पढ़ना उसको अच्छे से. Okay, because it's a very defining feature, किसी को बुद्धू बना सकते हो. कुछ नहीं तो लाइफ में 5 minutes of happiness in discussion कि ऐसा हो सकता है. So there is a tray efficiency, the distillation trays होते हैं, and there is a particular kind of tray. तुमने पढ़ा होगा यार. Murphy tray efficiency नहीं पढ़ी, हम more than 100% हो जाती है because the way it is defined. You see, efficiency means that everything will be defined in a proper way. ऐसा कौन सा rule है भाई? You see, so they define it in a way that the efficiency can be more than 100%. Okay, because the way it is defined. Okay, so ये बड़ा interesting है. And then you figure out कि ऐसा है क्यों. And why it is interesting? Because if you write a code, if you write a program, and when you write a code and a program and you solve, and listen to this carefully because I speak and then तुम लोग miss कर जाते हो बहुत चीजें. Because when you write a code and you've done numerical methods, you always do a check on what results do you get. And at times when you solve nonlinear equations, there are some particular solutions that you accept, some particular solutions that you reject. And there is a consistency check on them, and there is some kind of bound check on those values also. Okay, so for something like efficiency, a nice programmer would always put this check, that if the efficiency is by solving this equation for efficiency, if the answer is coming out by some iteration, by some numerical method, if the answer is coming out to be more than 100%, then I will not accept this, or at least I'll report it but with a flag. Okay, this is how codes are written, you see, that the error will be, that the answer will be there, but it will come with some flag, warning or with some error code. Okay, so coding ऐसे ही हो जाएगी. अच्छा कोडर ऐसे ही करेगा, जो अच्छा कोडर नहीं है वो तो ऐसे ही लिख देगा, जो आंसर आया रिपोर्ट कर दिया. अच्छा कोडर कहेगा नहीं, I have to reconcile, I have to check, I have to reject some, I have to, if it's unusual then I have to give a warning flag. देखो ना अच्छे कोड्स में ये होता है. You see, good codes will give you an answer like this. This is my answer, but this statement, some qualifying statement is also there. Okay, वो flag होता है typically error code or some warning flag. Okay. उसमें आइडिया ही नहीं है. मर्फी ट्रे एफिशिएंसी निकाल रहे हैं, इट कैन बी मोर देन 100%, बट इट्स नॉट नोन टू द कोडर, क्योंकि कोडर ने तो जॉब करने के लिए COL और ये सब कोर्सेज ले लिए. थर्मल तो पढ़ी नहीं अच्छे से. कोडिंग तो मैं कर ही लूँगा, क्या रखा है इसमें, और कोडिंग कर दी उसने, 100% आया, वो उसने बना दिया उसको. So ये एक बहुत realistic scenarios है, and people do make these mistakes, and good coders make these mistakes. You see, bad coders will not make these mistakes, but they'll make lot of other mistakes, because they have not made this mistake. See, so non-linear equations, any solution that you get out of non-linear equations, you have to make a decision whether to accept it or not, especially with non-linear equations. Okay, so there is a whole method that tells you how to reject, accept solutions of nonlinear equations. Okay, there is a method. I don't think it has been taught to you, but that kind of method exists. Okay, if someday I'll not be teaching you numerical methods, but in some presentation someday I can teach you that. So So this is one part where the efficiency, because you are looking at efficiency and coefficient of performance. Coefficient of performance typically in refrigerations, air conditioning, you have coefficient of performance, and I can tell you that when this chilling system for our supercomputing facility was to be installed, then the manufacturer came, his engineers came, drawing very high salaries, and everybody came and they said it is not possible to do it with this value. Okay, and where do you put it? You see, and do all that, and they said, it cannot be done under these specs. But it was done under these specs. Okay. You see, so a faculty member from IIT Delhi said, I'll do it, don't worry. You see, so he designed the whole system and everything, and within the specs. But these kind of success stories are not told. You see, but this happened, and then those people with the whole, the data center. Yeah, it was for data center. So data center, you see, all the big minds are going there. You see, and the engineers were there, and the data center would need something to cool. And cooling के लिए कहाँ बनेगा नहीं बनेगा, the size would be this would be this, where is the place? And so it was designed by an IIT Delhi faculty member. Okay, and faculty member has taken VRS at a very young age. It's a kind of just भगवान भजन में चले गए, कुछ some charity or something कर रहे, not really interested in teaching. तो ऐसे होता है. Okay, I told you some other stories about. Okay, so it is your job to find out who that faculty member was. Okay, कि कौन था ऐसा जो उसने ये किया. Everybody has given up कि नहीं होगा, but he said हो जाएगा. तो coefficient of performance, it's kind of simple. So one place is this, and of course it is counterintuitive, so it has some value, and of course it has a real value because when you are coding, you see, it would have a value there. There is another thing where, in chemical engineering, where you are counterintuitive more than 100%. Anybody? Plants running over capacity. You see, plants running at, let's say, 10% over capacity. Okay? Manufacturing happening, there is a chemical plant, its capacity which hai, it is producing more than 10% more than what it is supposed to produce. Okay, so this is fairly common. Okay, why does this happen? It happens because the denominator is defined in that way. You see, so it is not the best definition; it's a practical definition. Works most of the time, but the way it is defined. You see. So the capacity of the plant is defined in a particular way, but then it is possible to kind of push it harder, okay, so that they are running over capacity. Okay, but this is fairly common, you pack things over capacity, designed for this, but then you're putting in more. Okay, so ये तो करते हैं. It's common in other places also. You see, you pack करते हैं, especially. You're packing in more than what the design is, not actual volume, but जो design उसकी होती है, जो वो claim कर रहा है कि इतना pack करो. Not that. Actual volume कौन है? इतना pack कर दिया वही volume है. You see, logic से अगर लगाओगे तो जितना pack कर दिया, how do you measure volume? कुछ pack करते हो, ज़्यादा pack कर दिया तो ज़्यादा volume है. That's how it's defined. इसीलिए volume is a tricky thing. But so much for efficiency, and this to very strange cases, which also means that the ideal, it is your definition. The denominator that is there, or the design capacity, that is your definition. You see, you say that it's designed for this. Okay, right. So whenever somebody says give more than 100%, you see, the games होते हैं ना, sports वगैरह, 200% दे रहे हैं, या effort कर रहे हैं 110%, that's possible. I am designed for this, but I am over exerting. Okay, so ऐसा कोई, there's nothing inconsistent about the whole thing. Okay? So ये सब हो गया. Then I said property estimation में correlations होते हैं. So did anyone study about correlations? ये क्या होते हैं? Correlation is typically some value here or let's say y is some function to नहीं कहना चाहिए, but there is a relation here. So x1, x2, x3, lots of things, okay, and then they'll give you some value here. Okay, y is related to x1, x2, xn in some way. Okay, and that some way is typically found by experiments. So it is an experimentally fitted thing. It is not something that will come from first principles and using those conservation laws and everything. It comes from experiments. Okay, and they kind of make these correlations. Okay, so we'll spend 5 minutes or maybe less than 5 minutes on correlations because ye bread and butter hai. This is the bread and butter. So what we do in correlations is, so what is the typical thing in correlations? First of all, you say, okay, this has to be estimated. Okay, and this is likely to depend on these. Okay, so you say, okay, I'll vary these, and I'll measure what is this, and I'll have lot of data, and I'll fit. Okay, and this is how I'll get the correlation. Okay, now what are these? Some physics should tell you. Okay, some other previous experience should tell you. Okay, or there can be other methods also, you know, principal component analysis or all kind of things. You see that these are important components. While it depends on many, but these are the more important ones. Okay, so we do like this. So all physics, all history, everything goes there, and you say, okay, we'll work on these. Okay, then so there is a principal component analysis, and there is a design of experiment also, which means that given these, you need to vary them like this. So what is the minimum number of experiments that you need to do so that you have enough data to find out what y is. Okay, so there is a design of experiment, and what else was there? ECA. Okay, and all physics is used. Okay, to help. Okay, so these are the things that will go into this. Okay, and once you try to get a correlation. Okay, and another thing that comes into there is that use of non-dimensional numbers. Okay, so rather than using some simple parameter values, you use a group of them.
Sir, what is PCA?
ECA. ECA is principal component analysis. एक term है जब next time कहने का मतलब the idea is that next time when you come across this term थोड़ा ध्यान से पढ़ लेना. Okay. ये मैं भी पढ़ा सकता हूँ. ये DOE तो पढ़ा होगा. Design of experiments. पढ़ लेना जब आएगा. कोई कोर्स तो पढ़ाएगा. I don't know. नहीं पढ़ाएगा तो कोई फिजिक्स आती है, all other things are there. फिर experiments करते हैं. We do lot of experiments. Okay. So the idea is that we do experiments that contribute to this. So we reach this quickly, economically, you see, and more reliably. So that is the whole idea. And how do we reach this? Okay, and what should be the form of this? So we use non-dimensionalization also. So non-dimensional groups, there are many methods to do this, and I said there was a Buckingham Pi theorem that you should read. Non-dimensionalization you can get by dimensional analysis also, okay, and by physics also. There is something called a similitude. You look at similitude, do those kind of analysis, and you'll get these non-dimensional things. Okay, but this is only for beginners. This is a very, very intelligent technique. Okay, and people who do analysis or do very, what should I say, very advanced research in terms of maths. Okay, they engineering, very advanced engineering research and theory and everything. They are very good at it. You see, and what they do is you will write some Navier-Stokes equation, let's say, okay, or some equation, non-linear equation or very lots of parameters in that equation. And what you do is you kind of look at variation of those in terms of something. You see? So there will be a linear analysis, there will be a first order analysis, there will be a second order analysis, and depending on the order of analysis, you'll get more and more refined answer. Okay? And you keep on increasing the order of analysis till you are able to include the effect. I'll give you an example. Let's say intuitively and by arguing also through physics, I know that in this phenomena surface tension is important. Let's assume, or I have some experience where I've changed surface tension and something changed in the answer. Okay? And surface tension is fairly easy to change. Okay? Then you put in some surfactant, so it can change. You put in anything, the surfactant in a liquid, surface tension would change. Okay? Now, you start from the basic equation, then you say, okay, this depends on this, and you kind of combine all the terms. Okay? So the terms that have surface tension in it, they'll also have some coefficients. Okay? And in some, let's say in a linear analysis, the coefficient of the surface tension term is 0. You see, it's neglected in the linear analysis, because what is a linear analysis? Higher order terms are neglected. So let's say the coefficient of, if you write down the whole equation, the coefficient of the surface tension term, which is, let's say, gamma, like surface tension or sigma, whatever you want to call it, comes out to be, let's say, a cubic term. Okay? Now, for first order analysis, that cubic term has to be neglected, which means that if you analyze this process through these equations in a linear way, the surface tension will not have any effect. Because you have to neglect that term, the coefficient of the surface tension term is a cubic term. You see, even first order equation will not give you the surface tension effect, which means that if you solve this equation which you have got, there is no surface tension in that equation, so how will you get that effect? Okay? So you keep on increasing the order. Okay? And you say, okay, now at least with third order, so I'm taking everything that is, let's say, cubic, but I'm not looking at fourth order. Okay? And how do you get these cubic and fourth order? Because you choose a small value, something like epsilon. Okay, so you say, okay, this is something like this. I'm seeing some gap here, Or P minus T, or this is also okay. Something like this, You can write, epsilon cube, epsilon, something like this. See? So, this is not there. Or there is something else here. Okay. So you say this is some deviation, you write it in terms of some deviation. So then it's easy to see. So this is a small number and you say this is a linear analysis, so I'll take only, what are the constant terms without epsilon, I'll take only those terms. First order, epsilon would be used, but terms with epsilon square and others will be neglected. Okay, this is how you work, you see. Taylor series expansion also, you do the same thing. Okay. So in that sense, you'll have to go till the third order at least. You see, if the surface tension terms come with epsilon cube, which means that epsilon cube cannot be neglected. You see? So if epsilon cube cannot be neglected and epsilon is a small number, okay, epsilon square also cannot be neglected. Epsilon cannot be neglected, and unity is, of course, is already very high number because epsilon is a small number. So epsilon 4 is less than epsilon 3, epsilon 5 is less than epsilon 4. It's a small number, much less than 1. Okay, so you will get some equation, okay, in the end. And this is typically how, those brainy looking professors, they do a lot of equations, they work like this. This is their bread and butter, you see. I don't know if in the department anybody does that. Paresh does that. You see, maybe Sankalp also does it. I don't know. Sankalp I have not seen enough, so I don't know. But Paresh definitely does this a lot. Okay. So ultimately you will end up with some equation. And now you rearrange. And now you rearrange to get the minimum number of parameters in that equation. And that is how you are able to get those non-dimensional numbers. So you try to non-dimensionalize that equation. So it is art and science combined. A lot of creativity also is required. But this is something that is absolutely essential if you want to look at complicated equations, or if you want to solve a phenomena from complicated equations to get some approximation of it. Okay, so this is in the heart of that approximation. Okay. So we do all of this, then we get correlations. So now do you understand this? How do you develop correlations? You develop correlations by, of course, by data, fitting a lot of data. That data is generated either by physical experiments or numerical experiments, simulations, okay, or some other method also, I don't know, but typically through experiments or physical experiments or numerical experiments, and then you fit it. What goes in there is back and forth. You start out with something, but then you may not be happy with it, it may not do the job, you may not get the right correlation. So you kind of work again, take another choice, work again, try to fit. But the statistical methods that you now have, will anyway, this process is very quick now. It used to be a very tough process earlier, but with a lot of statistics now available as packages, it's okay. It can be done very quickly. Okay, I mean that's not a botheration anymore. Now, what are the problems here, and what are the common mistakes that people make? Because property estimation in industry is through correlations. You see, most of the property estimation. So wherever, even if we tell you that this is the CP expression for CP is this, but how do you get those coefficients? They all come from correlations, you see. And gases, maybe it's okay, you can still get something. Liquids and solids and everything, it is correlations only. So you see, we live in a world of correlations and mixing rules. This is the state of affairs. You see, as soon as we move away from gases, you see, any other kind of material that we see is correlation and mixing rules. You see, so it would be a good idea to understand what mixing rules are, and it would be a good idea to understand what correlations are, how do you develop those correlations, and what kind of mistakes can you make when you use those correlations. So the first thing is that you may make mistakes in putting in the values. So the units, see, there is no correlation, doesn't have to be dimensionally correct on both sides. You see, it should not. There is no necessity of it being dimensionally balanced. Okay. So there is a mistake, because things can be something is there in meter, and some other length is in feet. That can also happen. You see, something else is in, let's say, kilometers, all in part of one correlation. Okay. So between different kind of units. Okay. So it's not that there will be one for, let's say, SI correlation, or there will be this. Okay. It's not like this, but you change. यार ये तुमने किया होगा. Now I realize, ये जो कैलकुलेशंस करते हैं सबसे पहले कोर्स में, कौन सा कोर्स होता है? बेसिक इंजीनियरिंग कैलकुलेशंस, बेसिक केमिकल इंजीनियरिंग कैलकुलेशंस. नो न्यूमेरिकल मेथड तो बाद में है. एक बेसिक केमिकल इंजीनियरिंग मटेरियल एंड एनर्जी बैलेंस करते हैं.
ट्रिपल करना है.
कोरिलेशन नहीं पड़े उसमें मटेरियल एनर्जी बैलेंस में. उसमें correlations देते हैं with all kind of mixed. You see, one of the favorite thing is that we give you a correlation with all kind of mixed units and say that convert it to SI units. Convert that correlation to SI units. अबे किया था ये? वही correlation था. क्या सारा टाइम बेकार कर दिया. कोरिलेशन नहीं पढ़ा. मैं इतना स्टैटिस्टिक्स तुम्हारे ऊपर आ गई कि तुम जो रियल इंजीनियरिंग है कोरिलेशन की वो भूल गए. नाउ कोरिलेशन मीन समथिंग एल्स फॉर यू. वो कोरिलेशन है प्रॉपर्टी प्रोसेस. ओके, देखो पढ़ा, मुझे याद है ना. CeLeLe I remembered where I had done it. तो मुझे याद है, I had done it in my first year. तो मटेरियल एनर्जी बैलेंस टाइप ऑफ कोर्स, यूनिट डायमेंशन, ये सब आ गया. So the mistake is units. चलो, if you are careful, units की mistake नहीं करोगे. There is a mistake that even seasoned people make. Okay? वो हो जाती है. किसी से भी हो सकती है. Okay? Units वाली नहीं होगी, but somebody who is very, very kind of careful, they'll not make those kind of silly mistakes. It's a silly mistake. You see, units ये थे हमने enter किसी और किलोमीटर में डालना था, इसमें डाल दिया. It's a silly mistake. एक serious mistake हो जाती है. Went unnoticed होती है. और किसी से भी हो सकती है. Okay? Can anybody guess? एक जगा दो यार इसको भी जगा दो. इसको भी जगा दो. Yeah, wake up. I'm telling you about a mistake that anybody can make. थोड़ी serious बात है ना, because if we know that if we do this, we'll not make these kind of mistakes. Self improvement कर रहे हैं, अपना सुबह उठते हैं, सोचते हैं आज ये करेंगे, आज I improve this part of myself. But ये गलती तो किसी से भी हो सकती है. Doesn't matter how much you improve yourself, फिर भी हो जाएगी. ये गलती आ जाती है because of, बस हो जाती है because it's not very clear. See, so we use correlations that are not valid for those situations. You see, many times this happens, and it can happen with anyone. So you can use a correlation because the journey of a correlation, sometimes the applicability of the places where this correlation actually works, that is lost. Either it is lost or, people are not careful. Okay, so just say use this correlation, but this correlation is not valid for those values. Because this correlation has been developed by doing experiments or taking values in that phase space only. Not outside it. So it may work, it may not work. Okay, so using a correlation which is not applicable for that situation. You see, ये गलती किसी से भी हो जाती है. किसी भी means हमसे भी, किसी से भी मतलब. You see, the best version of you can also make that mistake. क्योंकि ये हो जाती है, you see, because of the way correlations develop. How many times do you see correlations being written, but उनकी range भी लिखी हो? Correlation तो copy हो गया. Somebody did that, range रह गई, applicability रह गई. Okay, वो आई ही नहीं तुम्हारे पास, तो तुमने use कर ली. Okay, so be very careful. Okay, but it's a very common mistake. Many people make it. Not applicable, but they're using it. Okay. अभी कोई टर्म पेपर करना है, कुछ करना है, we'll use this to estimate. We'll use this to estimate, but then that estimation is based on something वो applicable है ही नहीं. Okay, machine can also make these kind of mistakes. वो चैट जीपीटी से पूछोगे, वो घूम घाम के सब जगह से आएगा, कहीं उसको लिखा हुआ मिल जाएगा. Okay. इस पूरे लिटरेचर में कहीं ये नहीं लिखा होगा कि this correlation is not to be used outside this range. See, कहीं नहीं लिखा होगा, तो उसके लिटरेचर में ही नहीं है कहीं. Okay, so it will take time. Ultimately, ChatGPT will also kind of placeholder for all kind of LLMs. Will also do this, but अभी नहीं करता. कहीं पे किसी लेक्चर में लिखा नहीं है ना कि don't do this. So, but there are many references where they say use this. Use this. Okay, but it's not to be used. Okay, so ये mistake है और humans or machine and everybody है. That is major हो जाती है mistake. Now coming back to correlation समझ में आ गया? Two mistakes, how they are developed and how useful they are. You see that it is correlation and mixing rules. Most of the property estimation is like that. Okay, and it kind of allows you to develop your own correlations. Okay. So there will be empirical correlation, there will be semi-empirical correlation, there is some kind of physics also has gone in. Okay, in choosing x1, x2, some coefficients and all of that. And this helps, this kind of thing helps. ये पढ़ाई जाती है, advanced transport और इन सब में पढ़ाई जाती है, this kind of thing. Okay, but हम नहीं करेंगे, हम का तो करते हैं इसमें. So we look at ideal this and this. So now we start on this. How do we estimate? Okay. So we have defined Cp and Cv. At this point, we have defined Cp and Cv. So Cp, Cv, and if you look at, Cp, Cv came in because we wanted to know that if this much heat is given, what will be the temperature rise. So we said there will be some kind of coefficient that's kind of specific heat. Okay, you divide it by the amount of material that is there, so you get specific heat. Okay, for per mole, per kg, all that. So this is for temperature rise. Okay, pressure rise के लिए क्या करते हैं? Pressure rise इतना बड़ा issue नहीं है. But for ideal system it's not there, but for other systems, yes it is. Okay. So density कितनी change होती है, volume कितनी change होती है? You want to figure that out. You see, so compressibility क्या है? Because we are looking at how much does the volume change. Okay, because of several reasons. You see, first of all, it is 1 degree of freedom that is there. Okay, हम piston को ऊपर नीचे करके in a closed system, we can, if there is a gas, we can change the size of the enclosure and then that becomes a degree of freedom. You see, उसको ठंडा करना है, उसको गर्म करना है, expand कर दिया, compress कर दिया. You see, that's a degree of freedom that kind of results in a change in temperature also. For the same amount of gas, you see, same material. Compress किया, ऊपर किया, kind of we can change the temperature. Volume change, अगर temperature बढ़ाया, volume कैसे change होगा? Okay, pressure बढ़ाया, change किया, volume कैसे change होगा? So if it is ideal gas law, it is okay. But in general, what are the relations? So एक trait है, and it's an example in the book. हम लिखते हैं B is some function of T and P. ऐसे करके लिख सकते हैं, ये किसी को भी लिख सकते हैं. Okay, degree of freedom बस ये मैच करना चाहिए. Degree of freedom and independent variables. ये नहीं degree of freedom में फिर dependent variable डाल दो. That's not okay. You see? So and this is there in the book, but it's being done for this, can be done for anything, and this is the usual trick. Okay, so इसका derivative लिखते हैं. Okay, so इसका derivative लिखने में there is a small change that happens is ये हो गया. Okay, and dt से मल्टीप्लाई करेंगे, p से करेंगे. dt से. Good. प्लस ये करा. इसको इससे मल्टीप्लाई कर देंगे. थोड़ा सा इसमें
अपने टाइम का स्टूडेंट डेरिवेटिव लिया उसका, तो नीचे टेम्परेचर आना चाहिए.
भूल जाते हैं यार. हाथ चल जाता है. इसी with age, ये उठता नहीं है. You know this? ये कहते हैं ना shoulders drooping. It's a reality. अभी पेस बॉलर को देखोगे ना, ये शोल्डर आने की जगह ये आने लगता है. कोई करता है बॉलिंग यहाँ पे? कोई यू बॉल, सो यहाँ की जगह इधर आने लगता है. अगर थक जाते हैं. ओके, जब इधर आने लगता है देन ऑल द लाइन लेंथ एवरीथिंग गोज अवे. कुछ लोगों का ऐसे ही चलता है. सम सेलिब्रेटेड बॉलर्स आर लाइक दिस, वो मतलब श्रीलंका से आते हैं, उनका हाथ ऐसे ही चलता है इधर से. वो इट्स अलाउड. इसी पहले वो था मलिंगा, नाउ पाथिराना, ये सब वेरी फास्ट, वेरी गुड. सो एनीवे, ये करेंगे. विल कंटिन्यू विद दिस, विल लुक एट दिस. बट एक चेंज है इसमें. थिंग दैट यू नीड टू वरी अबाउट इज व्हेनेवर यू यूज अ पार्शियल डेरिवेटिव इन थर्मोडायनामिक्स. Okay, partial derivative means that this is there. Okay, but this partial derivative, if used in this equation, this is very subtle and many people make mistake. Okay, whenever you choose a partial derivative, you say this is working, everything else is constant. This is changing, everything else is constant. This is what a partial derivative or a directional derivative is. Okay, so you don't qualify what is kept constant. You see, in general, in maths, in functional analysis, whenever you use a partial derivative, you do not qualify that partial derivative by what is held constant. You assume that everything else is held constant. But because in thermodynamics you are allowed to choose, the two variables there and no more. Okay, because then it will confuse, you see, the degree of freedom. So it is absolutely necessary that you specify what is kept constant. So in this equation, this is kept constant. In this equation, this is kept constant. Okay, so this equation, this value that you compute by making use of this equation, by simulation or whatever, and you want to get a correlation or whatever, and if you lose track of this, you'll make a mistake. Because you can get this many times. X can be constant, S can be constant, you see, something else can be constant. Okay, so a partial derivative in thermodynamics has to necessarily tell you what is that is the accompanying variable, you see, what are the other independent variables, you see, and this is a slight difference, but इससे पहले नहीं आएंगे, वो अटेंडेंस शीट का आज तुम बोलोगे, जल्दी बोलो, अटेंडेंस शीट का है, जल्दी लो यार, मुझे रुकना पड़ेगा सबको, इसको बाद में एंड करेंगे, हो गया, Navagya has done it many times. तुम्हारा ही turn.
Ayush Chaudhary.
Yes.
Anand Tiger.
Yes.
Hitesh Gautam.
Yes.
Akhil Mohammed.
Yes.
Nishant Kumar.
Nishant Kumar का है. Yes.
Lokesh. Lokesh.
Lokesh.
Lokesh.
Okay. कौन है लोकेश? Yes. Good.
Akshay Raj.
अक्षय.
Tehseen Ahmed.
अरे रुको, अक्षय नहीं लिखा. दो अक्षय. अक्षय राज. Okay. Good.
Tehseen Ahmed.
Tehseen.
Nilawat Pawan.
Robert. Yes.
Nilawat Ganesh.
Ganesh. Yes.
Ashmita Rathore.
Rathore. Yes.
Ankit Kumar.
अंकित कुमार का है? Yes. अंकित.
Hardik Kumar.
हार्दिक कुमार. Yes.
Anubhav Sahu.
अनुभव साहू. Good.
Khushbu Yadav.
खुशबू यादव का? Yes.
Lucky Buskute.
बुस्कटे. बुस्कटे का है? उसका नाम काटो.
Shubham Chawla.
काट दिया तुमने? काट दूंगा नहीं यार, काट भूल जाएंगे. जल्दी काटो, लोगों को जाना है यार, किसी को वोट डालना है, किसी को जाना तो नहीं है.
Abhishek Kumar.
हाँ आ गया.
Pratham Manchanda.
Yes.
Akriti Harit.
Harit. Yes.
Suman Maji.
Yes. Maji.
Paras Kansal.
Yes.
Surabhi.
Surabhi. Yes.
Shriyanshi.
Shriyanshi. Yes.
Jagra Shakalya.
Shakali. Yes.
Kshitij Kumar.
Kshitij. Yes.
Rahul Kumar.
राहुल कुमार क्या था आपके नाम?
Yash Modi.
यश मोदी. यश मोदी कहाँ है? Yes.
Prakhar Agarwal.
खैर.
Divya.
There is Divya. Yes.
Keshav.
केशव.
Arnav Ranjan.
अर्नब में से
Akshat Dhamija.
Divya.
Isha Kumari.
Yes.
Harshit Bhatt.
But yes.
Ayush Bhanderia.
Yes.
Ashwani. Hardik Kunwar.
Yes.
Ayush Kumar.
Yes.
Samarth Gupta.
समर्थ है. Good.
Garv Gupta.
Yes.
Aninder Roy.
Yes.
Drishti.
दृष्टि. Yes.
Utkarsh Gangwar.
दृष्टि बाहर गए थे, तो मुझे आते देखा तो फिर सोचा आ जाओ अपने साथ में.
Vikas.
दृष्टि, you were looking like this, and you saw me, and you turned like this. But दृष्टि, you are more than your face. See, I can recognize people. See, and if I go around like this, I'll see your face also.
Vikas Yadav.
I'll ask you. Yeah, don't feel bad. Yeah, it was not to make you feel bad.
Vikas Yadav.
विकास यादव का है दिख गया.
Stuti Upadhyay.
उपाध्याय से.
Shashank Kumar Singh.
Yes.
Nikita Jalwaria.
Yes.
Sarthak Maurya.
मौर्य.
Vedansh Agarwal.
वेदांश है.
Abhishek Soni.
सोनी है,
मान्या अग्रवाल,
yes,
अमोल गुप्ता,
गुप्ता,
दिव्यांशु शर्मा,
शर्मा,
आलोक यादव,
yes,
पूर्वी जैन,
yes,
हार्दिक बगौड़ा,
yes,
निशान विश्वास,
yes. विश्वाल का है, निशान विश्वाल, निशान विश्वाल, विश्वास,
केशव राज,
केशव राज है,
दीप्ति भारद्वाज,
yes,
सचिन चंदवाड़ा,
सचिन, 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 क्रिकेट खेलते,
विशाल भगत,
विशाल है,
तुषार शर्मा, मयांक कलाल, अंकित सुरेश भाई पढ़ाया,
क्रिकेट टेंडर,
ऋषभ जोशी,
ऋषभ भी है,
सारंग मेंढे, रोहित कुमार मीना, अनिरुद्ध गोयल,
गोयल भी है,
ईशिता सैनी,
सैनी भी है,
श्वेता चंद्रा,
चंद्रा भी है,
मनोज्ञ,
अमित्या है,
शशि कुमार,
शशि भी है,
पुलकित गर्ग,
ये भी है,
अनहद सिंह,
सिंह भी है,
निष्ठा मुराद।
मुराद का भी है, गुड, थैंक यू। ये किसने गलती करी आज? दोस्त कुटे, बहुत से लगी। Quiet, please. Yeah, Samarth, you can come here and sit on D7. Shomil, do I see Shomil here somewhere? Yeah, come. And also get into this habit of, or rather, do not pick up this habit of asking a question to somebody who is senior to you and then saying yes, good. You asked a question, I answer, and you say good. That's not your prerogative, and that's not your position to say good to somebody's answer. Listen. You ask me a question, I answer. You're not allowed to say good after that. That's really, really very rude. You understand? You're not even allowed to say cool. Okay? Good to bahut dur ki baat. You understand this? Loud and clear? Okay, good. D7 is here. Shomil, has he come? You make a round like this and then go there. Since you asked, come. Make a round like this. Since you asked, come. Come. No, from there, outside, the outer ring. Come. Because you asked, come. That's okay. I'm not asking you to jump in a well. I'm just asking you to make a round. Come. Just make a round. Come, go like this. It was not because you didn't want to disturb him. I understand that, you see. listen to this. Don't get into this habit of, just, getting it in. I truly understand why you were stopping there. See, I keep a special track of people, not just these two wheelchairs, but in general also. Okay? So I clearly understood why you were waiting there. This is because you asked me what to do. Could have come there like this. Learn to live with people, other people, all kind of people, smarter than you, larger than you, superior to you. Okay? Learn this. Okay? Shomil, do I still see him? Is he not here? Nanukya, once we caught that proxy with Shomil, twice or once, at least once. Should we pursue that and figure out who has made that proxy? What does the class say? Should we pursue? If you don't say, it's a yes. We should pursue? Okay. So we will pursue. Okay. Now coming back to this, heat and work. Okay. So and listen to this carefully now. You see, most of the things we are just discussing here. So if you're not paying attention, I don't have a set of slides here. If that moment is lost, it's lost. You see? And get into this habit of, just in one class out of many that you do to just focus. Is it difficult to not chat? For half an hour, for an hour? We get a break, every 10-15 minutes we get a break, chat then. Why? You always have to chat. And repeatedly, when I tell you not to do this, you're still chatting. So it's a habit, see. It's not a reflection of your character, it's a habit. You see, and unless you're forced to follow a certain training, that habit doesn't go away. So all of us have to learn to live with other people, you see, and to be mindful of what the other person strength and benefits and positions are. You just can't be just yourself all the time. You're not allowed to in a society. You see, in a professional setting you're not allowed to. In a society you're not allowed to be yourself all the time. We are clothes, this, that. So many things. In that conditioning. So we listen to this carefully because we'll kind of do things very fast. I mean, in terms of concepts, not really in terms of speaking. So there's heat, there's work, very clear measure of displacement. Okay, and that is why work is a handle to so many things. You see, and we said work defined as displacement, this, that, from here to there, very sensible, very straightforward method of finding out. Okay, this much from here to here. And we try to understand what force is. Okay, some confusion with respect to force, but displacement is not doubted. Okay, most of the time. Okay. Now in the first law, because we look at the heat and energy balance, and now we have the heat also, and now things start becoming tricky, very tricky in fact. Okay, because heat. In the first law, you see, work is very well defined, but heat then gets related to the internal energy. And the internal energy is not known. You see, that's the whole issue. You see, whatever is hidden inside the system, you see, as in thermodynamics, we don't intend to know it anyway. You see, whatever is inside. Okay, and otherwise also, there's so many things where, it just changes. You see, heat is flowing, something is getting from here to here, but you can't measure it, you don't see it, you see, unlike work, okay. So the kind of heat that is easily understood, appreciated is the heat that results in temperature rise, only, you see, because you can measure the temperature. And how can you measure the temperature? Because you have all these temperature scales and everything, and you are related to these, boiling point, freezing point, and different, universal scale, absolute scale. Fahrenheit, centigrade, all other so many kinds of heat. So the only situation where heat is understood and you have control over, how much is being used, whatever is here, there, and everywhere, where it is solely related to temperature change. But temperature change is the complete measure of the heat that has been transferred. You see, like work, then it's like work, clearly, very clearly understood, appreciated, and is called the sensible heat. Now, what? So there is a work component in the first law. There is a heat, Q, work, and U. Okay. And now we say, what happens? Heat is moving around, here and there. Energy is being transferred, and we call it heat. What happens? If it's not related to temperature change, where else is it going? What else is it doing? You see. So it is not the problem of the heat, but the problem of the internal energy that is not understood. You see. So we try to sense the H part. If I can just write them here. You see, Q, W, and delta U. So this part is clearly understood. This part, if it is related to delta T, is understood because you know specific heats, mass, material, and then the delta T. Then this is work. It is the complication in delta U. You see, that kinds of get transferred to heat, because delta U, we may say this is U1, this is U2, everything is fine, we are okay. But then what happens to heat? What happens to Q? You see? So all the problems related to the internal energy, get transferred to heat. Heat by itself is not a big issue, you see. Something goes from here to here, some energy is being transferred. That's heat. Okay. So we need to look at how delta U creates an issue. You see? So what different kinds of issues can come because of delta U. Okay. And delta U, you have to ask this question, what can happen because of delta U? Okay. How will you track it? How will you track this problem? Okay. What happens to delta U in the process? There are many ways to do it. You can choose one of the ways that is, for an engineer, will almost always help. Okay. Suppose you have to find out some change, delta U, because you have to work with heat, and you have to find out delta U. Okay. Now this delta U, if you don't know how to begin, okay, you say, okay, let me see, what is my Rambar, go-to thing, you see. So if I'm stuck, who do I call? You see. So I call something which will help you all your life. Okay. And that is, you say, I'll look at, any guesses?
Specifically, CPC.
तो हीट है ना, हीट से तो बहुत दूर है, तो हीट से बहुत दूर है. Okay, अभी तो डेल्टा U में, and we have to figure out what happens to the delta U. You see. If we don't know what happens, then how do we begin? You see, if you know how to begin, you'll then all the maths and algebra science is available to you. You see? LLM में, Chat GPT में, you just know which prompt to type. फिर तो सब शुरू हो जाएगी कहानी ना. एक हैंडल ही चाहिए होता है ना. उसके बाद तो पूरी कहानी हो जाती है. So how do you begin? If ever you are stuck.
By small change. By small change.
That can be one of the ways that you know this and you say, if I disturb it a little, what happens? That's also one of the ways, and a very powerful method. But you look at chemical change, physical change. You see. What happens? What happens to delta U in different situations? I'll say, okay, I'll break it into two parts. I'll see what happens to delta U when there is a chemical change. Okay. I'll see what happens to delta U when there is a physical change. Okay. This is how we have kind of divided our understanding of changes. Okay. And this is a very powerful concept. If you ever have to, carry out something, you can ask the question, what is a chemical change? What is a physical change? You see, a physical change was asking someone to come from there and sit here. A simple physical change, you see. Nothing happens to him. The sawmill is not here. The other fellow is also, quite far away. तुम्हारा क्या नाम है? Hardik is there. So थोड़ा दूर है, chatting is difficult. Okay. So I said, okay, what is the physical change? Physical change में मजा नहीं है. It's not enough. Once that stimuli is taken away, things go back to where they are. You see, physical change, reversible. So I have to use a chemical change also. Chemical change क्या करेंगे? Chemical change में कुछ करेंगे, थोड़ा सा हैमरिंग करेंगे, कुछ करेंगे, उसको याद दिलाएंगे. और ऐसा नहीं है, बहुत दिन से चल रहा है ये. समर्थ के साथ में ये गेम बहुत दिन से चल रहा है. ओके. लेकिन वो कहते हैं ना, यू एग्जॉस्ट अ पॉसिबिलिटी देन यू यूज अनदर वन. देखो अब नाउ इज काइंड ऑफ, अरे मैं टीचर हूँ, तुम आधे से भी आधे हो मेरे, मैं तुमको बुली करूँगा. इज दैट द ओनली थिंग अवेलेबल टू मी टू फाइंड हैप्पीनेस? लेकिन तुम गलत रास्ते पे जा रहे हो. यू डोंट, that idea of respect for a fellow person is not there. You see, you may have hundreds of problems. You know where it all began. You didn't come and tell me कि सर ये problem है. वहाँ से होता गया. And now it has reached a state where you're not even listening to me when I'm talking to you, and keep on doing something. तो वो जरूरी था. Okay. Assuming कि अंदर कोर में सब ठीक है. Okay. And no more, nuclear changes are required. Chemical तक तो हो गया. Nuclear changes would be a lot more catastrophic. Okay. So we do this chemical change. Okay. And it can help you. You can just say कि physical change क्या, and then a picture of physical change जिसमें कि reversibility है, let's say. And there is a semblance of where you start from. Okay. Chemical change, reversibility is probably not there, and the character also changes. So the original is not here. That is one way to look at physical and chemical change. You see, there are many other ways also. The energy barriers, you see, so the valence bond coordination, all these electronic bonds, tens of kTs, hundreds of kTs, that's the bond energy. Physical bonds are 1 or 2 kTs. Okay. And 1 or 2 kT, if kT is already available to me, if billions and billions of billions are here, and some of them would have energy more than what is required. So any energy barrier that is 1 or 2 or 3 kBTs, is not a very high energy barrier. Okay, 10 kT, 100 kT, these are very high barriers. 1000 kTs, very difficult to break that. You have to increase the temperature so much. So something like pyrolysis is required. To break that. Okay. KT is in terms of, standard temperature inflation. Room temperature, let's say 293 K. Not temperature बढ़ा है, KT भी बढ़ा है, ऐसा नहीं. KT at some temperature. It will come. It's a part of the lecture today. Okay, that's why I was discussing KT also. So we say, if I'm stuck, I say, okay, if I have to figure out what is happening in the process, I'll say chemical and physical. That is one way to break it into two parts. Okay, and manageable parts. And also, why are we doing it? For industrial process, changes, all of that. And we already have a template that things can be seen in compartments of physical and chemical change. See, chemical engineering, unit operations, unit processes. Have you done that? So physically, so we look at the physical change. So we say, this is a species. So some reaction takes place and some phase change takes place. So you're looking at systems where no reaction, no phase change. no reaction, no phase change, there is a good chance that sensible heat is all that you need to worry about. Which means that if you have good control over the temperatures and you can measure them, place the temperature sensors properly and make the measurements properly, okay? And then you will be able to understand what Q is, okay? And if you understand what Q is, then work is anyway something else, already measured separately, and you have the first law, you see, in that sense, okay? And there are many, ideal systems, situations where this happens, okay? Where there is no phase change, where there is no species change, no reaction, okay? If a phase change comes in, some kind of complications in heat effects. If reaction comes in, some kind of complications, okay? And we have spent quite a bit of time in understanding phase changes. You see, so this class, I would assume we have discussed phase change so many times, okay? So this is, let's say, one half of your engineering, chemical engineering, and one half of all the processes that you will do. This is again maybe more than one half. I'm just saying there are two, so I say this is half, but maybe this is much more. Okay. So 3 different cases. Okay. In the reaction, so many things happen. Okay. So we say, okay, what kind of reactions? Okay. And typically reactions where you can see it in many ways, organic reactions, inorganic reactions. That is one way. It is like you may recognize, we say, okay, if I need to understand reactions, and we say, okay, we apply this framework. Does anyone recognize this? Yes. Okay. So we say organic, inorganic. Okay. Other kind of reactions in terms of oxidation reduction. Okay. In terms of, let's say, there are many more, these kind of things. Oxidation reduction is one, organic, inorganic is one. Okay. And typically those. Okay. And one of them that is really important is a combustion. You see? It's not coming from the MESI framework, but it is coming from the utility. Use over. You see? Something like work by user. You see? यूज कर रहे हैं, मतलब और कोई रीजन नहीं है उसका, यूज कर रहे हैं. कंबशन इतना इंपॉर्टेंट है कि यार who is going to bother about whether there is a counterpart and whether combustion takes care of everything or not. It is like because of usage it has become so important. You see, so all the credibility of choosing combustion separately than others is because it's so useful. You see? And lot of power is being generated by this and that. So there is an analogy in that, you see. There are so many other ways of looking at any system, you see. But ये एक quality है. Okay, why combustion is used. But you can see, you can create a framework for energy or let's say reduction, and kind of oxygenation. Okay, hydrogenation. In catalysis, you look at hydrogenation a lot. Your hydrogen को कैसे घुमाएं इधर उधर, de-alkylation a lot, कि ये कैसे तोड़ें उसको हटाएं, किसी रिंग में से alkali, alkyl groups कैसे हटाएं, those kind of things. So they become very important. Okay. But otherwise, combustion is important. Another thing that is quite important is ब्रह्मा विष्णु महेश इधर बनाया इधर फूंक दिया, समझ रहे? I'm kind of religion neutral. I use whichever religion comes to me. मैं तो इधर ही बड़ा हुआ हूँ, सभी कुछ देखते देखते. So इधर बनाना भी important है, इधर जला दिया, फूंक दिया, इधर क्या मिला. In between, all kind of processes are there. Okay, so कम से कम 2 end को तो पकड़ लिया. You see, अगर सोचो तो बनने लगता है कुछ मेसी फ्रेमवर्क बनने लगता है धीरे-धीरे. Can you see that? How is it being formed? Okay. अब बहुत इतना ज़्यादा टेंशन है लाइफ में कि you need to kind of just bear it and say यार बस तेरी मर्जी ये होना ही है. Okay, all kind of trouble, I can tell you. This is you're kind of safe from so many other bad things that are happening. But ठीक है, चलेगा देखा जाएगा. So we look at combustion, we look at formation. Okay, so we need to figure out a way of how to handle what happens in formation, what happens in combustion, okay, and what happens in phase change, okay, and of course what happens in sensible heat, wherever the heat is directly, completely, resulting in temperature change. Okay, so there the issue is more about where to put the temperature probes. See, you'll do all these experiments, and you're doing a heat transfer course also. And if you do these experiments, when you go for heat transfer lab, you'll get these thermocouples. कोई गया ही नहीं अंदर तक, कोई इधर है, कोई उधर है, कोई function नहीं कर रहा. All this is fine. We'll write equations T2 minus T1, but T2 है कहाँ? T2 ढूंढ रहे हैं, है ही नहीं. Okay, T1 पता नहीं T1 कहाँ है, in this whole idea. You see कैसे? So the problem more then becomes of instrumentation, sensors, how to sense those temperatures. You see, far away stars तक को हम sense कर लेते हैं, red shift, this shift, that shift, क्या temperature होगा, cool है, is it cooling, is it getting hotter, is it moving closer, is it moving faster. Just imagine temperature measurements कितना ज़्यादा advanced होता है. See, हम तो the kind of things we discuss in the curriculum is actually nothing compared to the challenges that we face as a race. You see, हम तो एक बस काम चल रहा है. Okay, and then hopefully, some of you will do PhDs, do some research, and maybe solve some more difficult, more relevant problems also. That's an undergraduate course, first course. Okay, so we can look at phase change first. Okay, because the reaction would require chemical and physical effects होंगे, because physical effect is kind of underlining, वो तो reference है, it is always there. Chemical नहीं होगा, you see. The physical is always there. You see, अगर unit process करोगे उसमें भी तो unit operations कुछ ना कुछ होंगे. Otherwise, how will you carry out the process? You see, so even in a chemical change, physical changes are implicit. You see, they may be there. Okay. So we look at physical changes. Let's get a hang on physical changes. So what are the kind of physical changes with a view of, let's say, having control over Q? Ultimately, we need to have control over Q. So what kind of physical changes? And we said physical and chemical. एक में तो कोई change हो ही नहीं रहा. Directly temperature measurement वो कर लिया. Temperature measurement is not there. So many huge problems with temperature measurement. Okay, and some of them you will yourself see when you do those experiments की thermocouple में क्या हो रहा है नहीं हो रहा है, temperature आ रहा है नहीं आ रहा है. You see, all very एक कोर्स ही पढ़ा रहे हैं, sensors. You see, and then how do you sense कि क्या temperature है, कहाँ पे करना है, एक liquid दिया उसका temperature measure करना है. So there is something called a cup mixing temperature. तो liquid लिया उसको mix किया फिर उसका temperature लिया. Otherwise ऊपर से लेते रहोगे then you'll not know what is happening. You see, so इतना mixing होगी नहीं. You see, natural convection may or may not be there. Okay, so forcibly mix करके you get a uniform temperature, then you get the in a way real temperature. Okay, otherwise सिर्फ surface पे ऐसे करते रहे तो you may not be sensing the representative temperature. Okay, so ये सब कर लिया phase change. Okay, so what phase changes do you remember? क्योंकि जो the phase changes that you will remember now as a response to this question are the phase changes that you are likely to remember 10 years from now. जो अभी याद नहीं हो 10 साल बाद तो बिल्कुल भी याद नहीं होगा. And this whole idea that we'll find it whenever required, that's not how the human mind works. That's not how the solution works. Method of solution works. You see, there's a lot more information that is already available to you before you design something, before you solve a problem. So this brain kind of carries so many things, and you use all that, you see, to solve things. Okay. So what phase changes? लिख के बात होती है. क्या है? पेरेंट्स हैं, प्राइमरी स्कूल है, स्कूल प्रिंसिपल है, मैं भी कहूँ 70 साल से यही हो रहा था, मैं क्या करूँ? देश का क्या विकास करूँ? अरे कुछ सुनो, कम से कम जो सुना रहे हैं. फेस चेंज पता नहीं, या तो आंसर आ गया होता, आंसर भी नहीं आया. सिंपल चीजें, ये फेस चेंज हो रहा है. द अदर काइंड ऑफ फेस चेंजेस आल्सो, द स्टेट ऑफ एप्लीकेशन इन अदर सिस्टम जो है कि ये फेस चेंज हो रहा है, फेस सेपरेशन हो रहा है, फेस चेंज हो रहा है, फेस ट्रांसफॉर्मेशन हो रहा है, एंड यू हैव टू रिकॉग्नाइज दोस फेजेस, ओके, एंड यू हैव टू सी if these kind of phase changes are happening, how to stop them. Okay, and this is one of the critical problems, that you will face. Not because the ice is melting. I mean, that also is a very big problem because the ice is melting. Okay, but how people are, or how opinions kind of phase change happens. When people, in opinions, in the way they think, how this segregation happens, and what are signs of those. Okay, and how do you measure that? How do you sense that? Okay, so ये सब methods लगाते हैं. Okay, all this social media etc. can tell you कि क्या हो रहा है. Okay, and so many ways, we'll not waste time on that. But it's a critical problem. So pay more attention to what the phase is and to how to identify your phase. Okay, so melting कर दिया, इसमें evaporation कर दिया, sublimation कर दिया, यही सब solid liquid gas, जो सालों से चला आ रहा है, अभी भी चल रहा है. इतने करिकुलम रिव्यू हो गए, इतनी इंजीनियरिंग बन गई, सब कुछ हो गया, वो सॉलिड लिक्विड गैस अभी भी चल रहा है. ओके, चल ही रहा है. अब थोड़ा बहुत कॉम्प्लेक्स फ्लूइड हो रहा है, अदरवाइज तो सॉलिड लिक्विड गैस ही चलता है. एंड सॉलिड मटेरियल्स आल्सो, सो लुकिंग एट डिफरेंट फेजेस इन सॉलिड मटेरियल्स आल्सो. डिपार्टमेंट बना रहा नया, बीटेक. See, all this research was already being done, but at an undergraduate level, special focus to different kind of phases in solid materials. That is new. Metallurgy में पढ़ाते थे पहले. Metallurgy कोई पढ़ता नहीं है वही, BHU में है, ISM में है, some places कारकुल में है, minerals metallurgy कोई पढ़ता नहीं है. Okay, और पूरा टैरिफ वॉर जो है वो रेयर अर्थ पे रुका हुआ है, रेयर अर्थ एंड मिनरल्स पे रुका है. just imagine the kind of choices we make. You see, critical चीज़ें फैशनेबल नहीं है. You see, पूरा कोविड हुआ है, फिल्टर्स कहाँ से आए? टेक्सटाइल से, जो कोई लेना नहीं चाहता, कोई पढ़ना नहीं चाहता. कहाँ से? वो उसका ओरिजिन, वैक्सीन, उसका मेजरमेंट कहाँ से बना? DBEP से. कोई जाना नहीं चाहता वहाँ, क्योंकि ये ट्रेजेडी है. ओके, और इतना सब होने के बाद भी उसका एंट्री रैंक, एग्जिट रैंक चेंज नहीं हुआ. एक कंप्यूटेशन लग गया मैकेनिकल में, उसमें अप्लाइड मैकेनिक्स वाले में उसका रैंक ऊपर चला गया. ये दिस इज व्हाट you, your parents, us, हम सब ने मिलकर ये सिस्टम बनाया हुआ है. There's so much exciting things happening in biology, so much exciting things happening in materials. हम पढ़ना ही नहीं चाहते, हमको पता भी नहीं. There is no role model, there is no way, there is no pathway that is being defined. Okay. So, but it's my job to tell you कि ये भी एक बहुत profitable चीज है. Okay. So all kind of materials ये सब करके तो how do we track this latent heat? So phase change में the heat that accompanies a phase change is the latent heat. It's called a latent heat. Okay, latent heat of vaporization and all those, heat of sublimation. ऐसे करके, but it's a latent heat because it doesn't show up in the temperature change. इसलिए latent ही हो गई वो. Okay. By that token, वो heat of reaction वगैरह में भी the temperature is not changing. Chemical change में भी latent heat ही है वो एक तरह से, but this is latent heat of phase separation. Okay. or phase transformation. जैसे भी कहते हैं, it's phase separating or transforming as a whole. So the way to handle all this is, and it's a very, very interesting exercise, you see. And there are books where you can find that exercise, and physical chemistry, typically done in physical chemistry. उसमें So one of the ways we look at condensed material, so there is something called a condensed material physics, condensed matter, condensed material physics, which is solids and liquids. It's like a condensed thing. Okay. Isme the issue is what kind of packing is there, and all this is being taught to you. All different kinds of packings are being taught to you. So what kind of packing is there? What kind of separation distances are there? Okay. So what kind of lattice is there, and what kind of lattice parameter is there? See, that is important when you look at a condensed material. But only in solids, only in crystalline solids. Amorphous में वो भी नहीं है, powders में वो भी नहीं है. You see, liquids में क्या है? It's because it changes shape, volume is constant, so relatively, compressibility very high. Very low incompressible almost. But some idea. You see, not a lot. But at least there is a short range order in liquids also. That if you look at a liquid molecule, you pretty much know उसके around क्या है. At least the limits. इससे ज़्यादा नहीं है, इससे कम नहीं है. You see? So we talk about. So whenever we talk about phase change and we talk about heat in phase change, it is called latent. There will be a sensible part also. There can be a sensible component. It's not that there will not be a sensible component. And we say that it will never happen. There can be a sensible component also. Okay. But normally, let's say, if the sensible component is not there, you are only looking at the latent component. Okay. So in a phase change, sensible component can be there. It's not that it will not be there. It can be. Depends on the degree of freedom. The two phases have to coexist. And if two phases have to coexist, number of components, degrees of freedom, you see, number of species, you see, number of phases, and you get a degree of freedom. You see, in some cases it can be high also, C minus P plus 2, number of phases 2, but many more components. You see, so if there are more components, then you have degree of freedom is higher. You see. It is only pure. Here you say, okay, pure, one component, minus P, plus 2, 3, 2 phases, 1 degree of freedom, and that degree of freedom is, let's say, temperature, pressure, volume ले लिया. You see, because why volume? Because volume is the one that necessarily changes in a phase change. क्योंकि the state of aggregation changes. हम define कैसे कर रहे हैं phase को? You see, it is like a cyclic argument. The phase is defined by the state of aggregation, how they are arranged. Okay, तो volume तो necessarily change होनी ही है. So if the volume has to be necessarily changed in a phase change between solid liquid and liquid solid and liquid vapor, you see, and there is only one place, so volume change हो गई. The other two things then cannot change. ये गेम है. अगर component ज़्यादा हो गए तो more degrees of freedom. तो उसमें भी बदमाशी करते हैं. उसमें कहते हैं कि नहीं, components में composition change हो गया. You see, so volatility आ गई. You see, vapor में ये reach हो गई, liquid में ये reach हो गया. All kind of separation processes are based on this. If somehow you try to create two coexisting phases, and then you'll get a different composition here and a different composition here, and you can separate things, or progressively, you can in stages enrich any component in any of the phase. You see, so ये composition change हो गया, but it doesn't say, at least very clearly कि other things cannot change. You see, temperature can change. Okay, azeotropes आ गए, कुछ भी नहीं, same ही composition. Azeotrope, have you heard about azeotrope? मास्टर आंसर पढ़ा होगा कुछ, या दो phases में there is the same composition. So two components, two phases, okay, and same composition, okay, फिर degree of freedom कहाँ है? You see, so उन cases में do you say कि just the volume, fixing the volume is enough? You see, just the volume change is enough. There can be other changes. We don't know. Okay. What happens when things are in critical? So the idea is we look at the condensed material. We have an image. This is how we get the latent heat of any phase separation. We look at this phase transfer. We look at packing. Packing ये पढ़ाई जा रही है तुम्हें. In liquid there is an issue, but liquid में क्या करते हैं कि liquid में we say कि it will have, let's say अगर 2D है, you see अगर 1D है, then it will have only two neighbors. There can be a liquid stream, very thin stream, like a jet stream, very thin liquid thread, and 1D, nano में करते हैं, उसमें करते हैं polymer melt में when you have electrospray, इतना पतला thread आता है. So if you are looking at that, then it's like a string. So string में this molecule would have only two neighbors, one here, okay. उससे काम हो गया एक string में. एक sheet है. Then what happens in a sheet? How many neighbors are there? Okay. This is slightly tricky. Okay. तो एक सर्किल रखा, उधर एक और सर्किल रखा, एक और सर्किल रखा, एक और सर्किल रखा, एक और सर्किल, एक और सर्किल, एक और सर्किल, और एक सर्किल के चारों तरफ कितने सर्किल्स हो सकते हैं? Assuming the same kind of circle, because you are looking at pure system, so all circles are the same. तो a circle कितनों से surround हो सकता है 2D में? इतना पढ़ाया गया, जेई में भी सवाल पूछा होगा तुमसे. एक ऐसे सर्किल रखा, उस पर एक सर्किल ऐसे घूमता हुआ जा रहा है, घूमता हुआ जा रहा है. ऐसे कुछ सवाल आते ही नहीं आते? अरे कभी तो पढ़े होंगे, नहीं पढ़े? एक सर्किल ये है, कितने सर्किल रख सकते हैं? कैसे निकालोगे? अगर एमसीक्यू होगा तो सारे रख के देख लोगे, बनेगा नहीं बनेगा. निकालना हो तो कैसे निकालोगे? Okay, so you know the maximum in a 2D space. What is the maximum number? Okay, and minimum is like a gas. कुछ तो होंगे तभी तो liquid कहलाएगा. So let's say at least 4 होंगे. Okay, Cartesian coordinates में चलते हैं, sheet में 4 होंगे. Okay, so you have all these in liquids. You have a, अगर जब कभी पढ़ोगे आगे, तुमने पढ़ा हो शायद, all these Boltzmann वाली equations जो आती हैं, simulation methods, Boltzmann methods आते हैं, कौन से methods? Lattice Boltzmann methods. LB methods आएंगे. They are kind of simulation method which all of you will read about. Okay, lattice Boltzmann simulation, LB simulation. ये तुम्हारे seniors कर भी रहोगे बहुत से projects. Okay, so lattice Boltzmann में 4 neighbors वाले कुछ methods होंगे, पर 4 से ज़्यादा भी हो सकते हैं, इधर वाला भी count कर सकते हैं. Okay, so there can be 9 neighbors, 6 neighbors, 8 neighbors. So limits पता है. ये मिनिमम 4 है, मैक्सिमम 12 है, 16 है, जितने भी 9 है. ओके, क्योंकि ऐसा भी हो सकता है ना. इन सॉलिड्स लैटिस यू फिगर आउट कि ये इंपैक्ट कर सकता है. इन ऑल सो लिक्विड्स में यू डोंट नो इट प्रॉपरली, बट ज्योमेट्रिकली यू कैन फिगर आउट कि सेम इफ इट इज अ 2D, इफ इट्स अ स्फीयर, then you can find out कि कितने spheres उसके आसपास हो सकते हैं. Maximum 21, 12, 14, 16 जो भी हो सकते हैं. depending on the kind of liquid or kind of solid. Okay, solids so has been taught to you, liquids नहीं पता है, but liquids में you just look at the extreme cases. Okay, कि vapor type behavior में क्या होगा, zero neighbor. Solid type में ये होगा, liquid कहीं बीच में होगा, halfway between. Okay, तो ये करके bond energy दे देते हैं इसमें. Okay, so if it is a liquid, the bond energy is about क्योंकि एक स्टेट में कितने बॉन्ड्स हैं, कितनी है पोटेंशियल एनर्जी है, सब कुछ काउंट करेंगे, दूसरी स्टेट में काउंट करेंगे, दूसरे फेज में, एंड विल लुक एट द डिफरेंस. ओके, दिस इज हाउ विल गेट द लेटेंट हीट. ओके, ये स्टेट क्या है, ये स्टेट क्या है, एंड इनके बीच में क्या डिफरेंस है. बिकॉज वी आर नॉट लुकिंग एट द हीट, वी आर लुकिंग एट द डेल्टा यू व्हिच इज अ स्टेट फंक्शन, स्टेट ऑफ हीट. वी आर नॉट लुकिंग एट एच और क्यू और ये सब, वो सब तो क्यू तो है ही नहीं स्टेट में. ओके, तो स्टेट से कोई मतलब ही नहीं है क्यू का, तो प्रोसेस में अलाइव होती है. It's alive only when there is a process. State से लेना देना नहीं है कुछ उसका, क्यों का. Okay, जैसे W जब डिस्प्लेसमेंट होता है तभी आता है, उससे पहले कहाँ. Okay, so delta U में this is stage, this is stage, this is the configuration, this is the configuration. These many neighbors are there, and these many neighbors, the bond energy is this much. Okay, so we say these many neighbors and this much bond energy in this phase, this many neighbors and this much bond energy in this stage. In terms of solids, it's straightforward because you know the lattice, crystalline lattice, you know the lattice parameter also, you need the distances, sizes also, and all of this can be calculated. Okay. In liquids, there is it's a little tricky. Okay. But liquids में कहते हैं कि if it is a non-polar liquid, then it is like KBT. Polar liquid will have a different issue. So liquids में the way is polar के लिए कुछ है, non-polar के लिए कुछ है. Okay. So polar KBT ले लेते हैं. इधर KBT ले लिया, उधर जीरो है. Easy. मानिए एयर से this liquid going to vapor और vapor condensing to liquid. इधर तो लिए कितने, 12 मॉलिक्यूल लिए. ओके, सेपरेट है, नो एनर्जी, जीरो. इधर ये 12 मिलके एक हो गए. ओके, एक ग्रुप बन गया. सो वी से आर बेसिस इज, पहले हमने देखा कैसे लिक्विड में अरेंज है, जिसमें ज्यादा अरेंज है उतनी मिनिमम बेसिस लेना पड़ेगा ना. यू कैन नॉट से आई एम लुकिंग एट दिस ग्रुप विद 12 मॉलिक्यूल्स, पर उधर एक ही लिया, ऐसा नहीं ना, इधर 12 से बना. तो यू टेक एज मेनी एज आर रिक्वायर्ड टू डिफाइन अ यूनिट ऑफ द कंडेंस मटेरियल, एंड देन टेक एज मेनी सेपरेट वंस देयर. तो इतने 12 उधर लिए, 12 लिक्विड स्टेट में लिए, 12 वेपर स्टेट में लिए, बिकॉज यू आर वर्किंग ऑन दोज 12 पर यूनिट मटेरियल आइडेंटिफाई कर लिया ना. सो वी आर लुकिंग एट दोज 12. ओके, इधर जीरो है बिकॉज देयर इज नो इंटरेक्शन. इधर एक बॉन्ड एनर्जी है एंड देन सो मेनी नेबर्स. तो द अरिथमेटिक इज ओके. ओके, ये कर लेते हैं. इसमें द मिस्टेक दैट, डू यू ऑल एग्री दैट दिस इज वन वे. ओके, एंड if the bond energy is not known, we say it's about KBT. Okay, you'll not make a mistake. Non-polar liquids, you can say KBT. In polar liquids, you can add a little bit more. Okay, अगर बहुत ज़्यादा हो जाएगा तो solid ही बन जाएगा. If the neighbors, it has to decay also, because the neighbors can help you, stop you, help you, but jam तो नहीं कर देंगे completely ना, like in a solid. Okay. तो फ्लो तो होता रहेगा ना, अगर ये शेयर लगाओगे तो इट विल फ्लो, सॉलिड तो नहीं फ्लो करेगा. तो ये हो गया, एक सब कुछ कर लिया एनर्जी बैलेंस. देयर इज अ कैविटी एनर्जी दैट वी मिस, एंड मेनी पीपल मिस दैट. ओके, और it's a very interesting calculation, and I'll maybe if I give it as an assignment, people will do it. I have to give assignments also, I've forgotten. Okay, I'll do that tonight. Okay, so it's a very intelligent calculation. Okay, and I can challenge all of you that only few of you will get it right in the first instance. Only few of you. You see, maybe none. Okay, you'll have to really think very hard to understand what is actually happening. Okay. Here. So what we miss out on is that these are 12 separate. इनको condense किया, okay, और इधर बना दिया, so many neighbors, and delta U is this, okay. The cavity energy is that these 12 will go and sit somewhere. जब ये 12 यहाँ जाएंगे तो वो जगह कहाँ से बनेगी? So there will be energy required to make that cavity. You see? So n number of bonds have to be broken inside the condensed material to make space for these 12 to come in. And when they come in, n2 number of bonds will be made. You see? So ये जो n1 break करने पड़ते हैं for the cavity to make space for those 12 to come in are missed by most people. I can guarantee you that if I have not discussed about cavity and I would have just given you a simple answer, simple question based on this, most of you would have done this. For two reasons. One is, it's not really intuitive. Second is, we are towards the fag end of this. There's so many courses, this and that. जो answer मिल गया कर दिया. So there is no time to reflect on the question. If you spend time on the question, पूरा दिन है तुम्हारे पास, ये luxury है, then it may occur to you कि यार ये सही नहीं है, ये जाएगा कहाँ? Somebody may think that, you see. But अगर straightforward in the run of the mill kind of thing, assignment है ये हुआ, most of you will give that answer. Okay. So ये cavity energy is very poorly understood. कि वो cavity कहाँ से बनेगी? Okay. और अगर cavity बनेगी तो intuitively क्या लगता है कि अबे इतने तोड़े थे और इतना ही बना लिए तो मिला क्या? किसी ये क्वेश्चन आ रहा है माइंड में किसी के मनोज जी आ रहा है? इतने तोड़े इसको लाने के लिए, अभी जो इसको लिया इतने ही बना लिए तो मिला क्या? यही कैलकुलेशन करना है, मिलेगा. ओके. तो जब नए को लाओगे, नए को लाए और हम सोचते हैं कि इसको लाए और टूटता है, ऐसा नहीं है. जितने टूटते हैं उससे ज़्यादा बनते हैं. इट्स वेरी इंटरेस्टिंग. ओके. मतलब देयर इज अ मिसमैच एंड दिस कैन प्ले आउट इन मेनी सिचुएशंस. मतलब एक ग्रुप है, एक बार घूम रहे हैं लोग, उनको ग्रुप में लेना है, हम ले ना लें, हम लेंगे तो हम बिगड़ जाएंगे. ऐसा होता नहीं है. हम सब स्ट्रांग हो जाते हैं. ये साइंस कहती है, हम नहीं कह रहे. ये सोशियोलॉजी में नहीं कहा जाता है, साइकोलॉजी में नहीं कह रहे, पॉलिटिक्स में नहीं कह रहे. ये साइंस कहती है बिकॉज देयर इज समथिंग कॉल्ड अ कैविटी एनर्जी. वो कैविटी बनानी पड़ती है. ओके. सो एंड देन वी लुक एट इनसे क्या आता है. व्हाट रूल डू यू गेट व्हेन यू लुक एट लेट्स से हीट, लेटेंट हीट ऑफ वेपराइजेशन. लेटेंट हीट ऑफ वेपराइजेशन होती है, एक रूल आता है. ओके. एंड वेरी इंटरेस्टिंग रूल यू सी. और अभी तक चलता है वो ऐसा नहीं है कि नॉट मेनी एक्सेप्शन टू दैट रूल हैज बीन फाउंड. ओके. सो देयर इज अ रूल कॉल्ड क्रोटन्स रूल. तो बॉइलिंग पॉइंट से लेटेंट हीट को रिलेट करता है. इट रिलेट्स योर बॉइलिंग पॉइंट या जो भी वेपराइजेशन, जो फेज चेंज का जो टाइम है, टू योर लेटेंट हीट. So boiling point and latent heat of vaporizations are related by Croton's rule. Okay, and you get it because of this. Because number of neighbors इतने होंगे, यहाँ free हैं, यहाँ condense हो गए. There is some cavity that was formed. क्योंकि इनको ले जाके कहीं रखना होता है ना, liquid तो बढ़ नहीं रहा है. So you get a Croton's rule, and it kind of works well. And Croton's rule for polar liquid and Croton's rule for apolar liquid will be different. Okay. Will the coefficient that you get about 10 or 13, जो भी था 13.1 या 11.3, I don't know, something like that, 11.3 maybe. Okay. Will it be more than 11.3 or will it be less than 11.3 for polar or liquid? This you have to figure out. In किस direction में जाएगा. Okay. So we'll continue with this heat effects. We'll look at chemical changes also, but physical changes have you understood? ये शॉमिलिया आया नहीं आया अभी तक? नहीं आया? कोई बात नहीं. अटेंडेंस शीट क्या है? हो सकता है अटेंडेंस शीट में हो. तुम्हारे बाल फिर बदल गए. क्या यार तुम भी थोड़ा सा दुनिया ने तुम्हें ऐसे धक्का दिया और तुम पढ़ गए तो इसलिए that was not a haircut. Scientific theories हैं कि hair style कैसे होते हैं, okay? And there is a very big gap in you know जिसे कहते हैं coiffure, okay? Head style, इसको और अपना you know बहुत पैसा है इसमें, बहुत ज़्यादा. You know if you can figure out a way to style it and tell people कि ये होगा तुम्हारे साथ. Okay, and ये सब तुम्हें पढ़ाया जाता है. You know, if you use all those methods, you can find out. एक सबसे interesting paper which I found out was, and I don't see anybody here, otherwise हम कहते हैं कि you sample the hairs and they can tell you कि whether a ponytail can be made out of these hairs or not. अबे science में paper है. Because they look at the rugosity, they look at everything, they look at the structure, and then they figure out कि इतना उसमें tenacity होनी चाहिए, rugosity होनी चाहिए. Only then a ponytail can be formed. You know, ये science में study करते हैं methods. Okay, and there are softwares also to do all that. So hair styling is a very, you know, मतलब there can be startups इस तरह का. तो करें बताओ तुम्हें क्या लग रहा है मोटा मोटी. इसे शॉमिल को देख ले, बाकी छोड़ दे. अरे इधर तो नहीं है, इधर है. कर सकते हैं, चलो जल्दी करो. मैम आ गई, चल आ गई, अभी नहीं है, जल्दी करो. शॉमिल कहाँ रहता है? अरे मजा नहीं है यार, वो इधर है नहीं. फायदा क्या यार, वो अपना पक्ष भी नहीं रख सकता. फायदा क्या, और इस केमिकल ट्रीटमेंट का फायदा क्या? आर्यन क्या है? प्रेजेंट आर्यन है. छोड़ो चलो. इतने लोग हैं, क्या लग रहा है? कुछ ठीक लग रहा है ना? थैंक यू. Because so that you age, but you don't age greatly and in your spirit. You keep accepting this. Suddenly. So you'll be fine, you'll get a little bit tired. Suddenly, my body is like oxygen नहीं रहती. भूल गया ना शीट लाना. I mean not भूल गया, there was not enough time to print. I print 3 sheets on Monday. So Monday को मैं print.
तेरे बच्चे भी तो बैठ सकता हूँ, ऐसे क्या है? ठीक है.
Okay, quiet please. Anyway, so today I don't have that normal attendance sheet that I print 3 sheets every Monday, and this Monday I was not there, so I couldn't print. So you'll have to write your name, entry number, and signature. Okay. Because you see, I promised Manogya that I'll not make him call again if he does it well. And he's done it well last time, so I'll not make him call again. But I'll rely on other things. One is, of course, you write down the name, entry number, signature. So a lot more data for the machine to check for the handwriting and everything. Then I'll take pictures, and I'll have other supplementary data coming from communication towers and your logins. Okay. You understand? You log in and then it tells you where you are, which router you are connected to. You understand? You have done it in the past, and we have records of everything. You know, your phone number, which tower it's connected to, and your login ID, which device, and where it has been logged in. That data is available to us. And of course, the photographs will be available to us, and the pictures, signatures, and everything. So, we will not bother. Come in quickly. Okay. And we are likely to have quizzes every day, because if people have to get A's, you see, I need to hurry up. It shouldn't happen that somebody misses just one class and then the A is gone. It's too harsh. Okay. So, and for that to happen, you'll have to take quiz every day, because you'll have to do well then, more than 90% attendance in the quizzes. Okay. So we'll probably have quizzes every day. Okay. So when I give a quiz, it's not that I'm harsh, it's that I'm very generous when I give a quiz. Okay. You understand this logic? Okay. Are you ready to call today also? You know, structures, everything. Okay. So we close this concept of heat capacity by saying that it is how much heat is given and what is the temperature rise. Okay. And that remains the definition for heat capacity. And you need to write down the first law, and you have to figure out what the heat is, okay, and what the temperature rise is. Of course, one of the things. And then see, there will be a component of internal energy in this. Okay, so you have internal energy, heat, work. Okay, that is how the first law is related. So internal energy, you try to figure out what is the change in internal energy, and you try to figure out what the work is, and the work would be PdV, or force into displacement. Okay, F dot D. And there is a special kind of work that is PdV. There are other kinds of work also. There is a charge, you move it, some work is done. Okay. So, but we are looking at work of expansion, contraction, okay, compression, and PdV. And we also discussed that ISO, constant volume, does not necessarily mean no work. Not even the work of a special kind, which is expansion and compression.
Yes.
You see, constant volume, but you're moving charges around is a lot of work.
Yes.
You understand? But even when you're looking at expansion and compression because of pressure, even that is not all the time important. Okay. You see, you integrate dl over some cycle, okay, over something, you see, and you get 0. So integration of dA displacement can be equal to 0, okay, but F dot dl
May not.
even for a small to small volume also. Of course, for a path it is always true, but even for a very small volume it's not true. So heat capacity is heat by temperature, and every time it has to be estimated. Okay, 2 very special kinds of heat capacities that are known, you know, Cp and Cv. Okay, and then those Cp and Cv, one is at constant pressure, another is at constant volume. Okay, it kind of just helps. And of course, when you look at molecular theory and you try to look at Cp minus Cp 3 by 2 R, R 7 by 2 R, depends on what the gas law is. Okay, so that we'll not go into that. We just say there is a heat capacity. You put in, you try to estimate how much heat goes in and what is the temperature rise. Okay, and then depending on what units, that's your choice. You can choose whatever unit, per unit mass, per unit mole, Just 1 minute. But here, क्योंकि I didn't find time, I didn't catch you, and उधर से आ गया तो फिर आप आ गया क्या कर सकते हैं? You know, they become very rude. You know, if I now pick somebody up and throw them out. You know, I can't pick people up. It's difficult. So, any questions about this? Heat capacity, CP, CB, and S also. Sometimes, you know, when you are looking at solids, it is S. You remember? MS delta T. CP, CV for gases, all that. But don't put too much faith on CP and CV. All the time you need to look at how much heat goes in, what is the temperature rise, okay, and then you try to take the ratio, divide both of them, and then use the appropriate units. That is that. And of course, we looked at U also. We discussed, and maybe we'll reinforce it, that U is a state function for simple material, okay, and the way we define the state. See, so a state function is, you know, is implied by what the state, how the state is defined. See, if you take care to define the state with, if you have not identified the degrees of freedom properly, then you will not be able to specify the state properly. So something that may actually be a state function will not be a state function because you have made an error in the degree of freedom calculation, you have not defined the state properly, you have not taken enough parameters there in the state, in the definition of state, and then you say it's not a state function. Okay, so that's not correct, but it is like accounting. So once you have decided that this is the degree of freedom, this is the state, and this is how the state has been defined, then with respect to what your definition of the state is, it will be a state function or not a state function. So you typically, you know, for gases, liquids, simple, it will be a state function. It will never be a state function for a complex system. Okay, and why it is not be because see, you will deal with lot of complex systems as with material, complex material, and also lot of components in a system. So it is absolutely essential that you get this idea or this way to look at complex system correctly at this point. Otherwise, if you try to, let's say in your 4th year, in your 3rd year, or later on, if you try to read books about this, that this has become very important, I want to do research in this, I want to use these theories, you see, then it would be very confusing. Okay, so there's one of my jobs is to tell you how simple things are, and to give you that confidence that if you take them, if you treat them with these things, it will do the job. You see, so you don't have to unnecessarily complicate. And complex material, complex systems, theory of complexity, depth and complexity, all these things you will revisit, you see, in your life, because these things will become important, okay, in your life, you know, in not so distant future, and then you should not get confused. It is just lot of components. If lot of components are there, and that can lead to just being lot of components being there and interacting with each other can give rise to lot of very emergent behavior. So emergent behavior means the behavior of individuals. You cannot relate it to the behavior of the group. It is such a simple concept. You see, but if you pick up a book on complex fluid, you know, they'll make such a complicated structure out of this that, you know, emergent behavior is something that cannot be completely, you know, completely out of bounds, not understood, anything can happen. No, it's not like this. You see? So one thing is this, and everything comes from lot of components interacting with each other. And then it kinds of, and then there are many other things that can come in, but a good definition is this. Like specific heat is, you just figure out how much heat goes in and how much comes out. So you have a black box, you heat, and you have a way to figure out how much heat goes in, and there are many ways to do it. You see, you heat it to a current, and you figure out how much current goes in, and you say, okay, if this much current has gone in, maybe 10% of it goes outside, there's a leakage here, there, and all that. This is the amount of heat that is given in, and this is the temperature rise. And that can give you the specific heat. You see, you don't necessarily have to figure out, you know, what kind of system it is. Okay, so at all stages, you'll be true to what the spirit of thermodynamics is. Finding a way to comment upon the system and the system performance, comment on its future, figure out without going into the detail. That is the key. And curiously, if you don't go into that and you try to make sense of it, you use all the maths that you know to do it. See, otherwise you would work with physics. See, so okay, that's how it is. So इधर से कान नहीं पकड़ा, इधर से पकड़ लिया. All kind of things. So either you do experiments and you don't worry too much about this, or you use very complex methods. So first break it into small parts, look at all the deviations, this, that, use a lot of calculus, you see, all kind of things, okay, and then you find out about the system, okay, or you go inside the system, look at the physics of the system, use whatever math is required, and figure out for the system. इस तरह की चीजें होती रहती हैं. Can you be a magic है? होता है. Physics में नहीं करना, math में करना. और experiment में that is even worse. करके देखो. All kind of destruction can happen करके देखने में. अगर सोच के कर लिया, thought experiment maybe only it's very safe in that sense. Okay, or numerically it's very safe, theoretically it's very safe. करके देखना is so much difficult. कुछ भी हो सकता है. So we do that. Now we come to the pure material. So when we say pure materials, okay, we look at the properties of pure materials, because we look at materials and we say, okay, of these materials, we'll look at some kind of material that can be simplified. So how can material be simplified? Pure material. Okay, because when we look at different chemical species, you say, okay, it's a mixture of these species. This is the chemical composition. So we say pure. So with respect to chemical and with respect to physical. Do you see the pattern here? Everything that we do is physical or chemical. There is a physical change, there is a chemical change. There is a physical, chemical. You understand this? So when we say pure, we think only in terms of chemical. But pure as a definition, for a lot of things we say just being chemical is enough. Looking at chemical purity is enough. But for thermodynamics, at an operational level, you see, that's not enough. Because the system may be chemically the same, but physically may be very different. So our job of simplifying certain types of material, certain states of material to be a simplified system, so that we can comment on this is not good enough. You see, that simplification is not enough unless we have chemical. A simplification with respect to the chemical composition and a simplification with respect to the physical state. Do you understand all of this? Because the objective was to look at a material, this material, in a simplified way. Okay, so of course chemically same has a role, but all of us with our experience already understands that water, ice, vapor is a good example. Chemically same, very different. So we say we need to look at chemical and physical. So chemical, we all understand, there's molecules, atoms, ions, all kind of things, ways to radicals, free radicals, ions, molecules. Some other, how do we define the chemical nature? You see, NaCl here, but NaCl in solution are two different things. You see, Na plus here, Cl there, so it's not the same chemical composition. They act differently. See, sodium ion and chloride ion, they act differently than NaCl. It's a good example, you see, simple example. So we say, okay, are we looking at molecules to be the same? Are we looking at atoms to be the same? Are we looking at ions to be the same? Or are we looking at radicals to be the same? And that will then define the chemical homogeneity. See? So just by, otherwise, at an atomic level, they'll be the same. You see? And then you say, okay, sir, this is not enough. We look at isotopes, we look at isomers also. This should have come from the class, but it didn't. Give a little pause for you to do this, okay? And people sitting in the back, not really being able to hear me, but they're just sitting there, okay? If I speak the way I speak, and I sit there, I can't hear myself. And then if the exams are going to be based on what I'm discussing in the class, all of this should be full. Well, it did for 2 lectures. People were cramming here and there, just trying to be able to listen to me. Not anymore. Habits die hard. Otherwise, so I expected, all of this to be full. Because sir तो अब बोलेंगे नहीं, and who will tell sir to use the mic? तो हम ही यहीं आ जाते हैं, but no. Okay. So ये सब होता रहता है, side story. Okay. वो पीछे बैठे. Ash, today you don't have anything to copy, to finish, some assignment, homework, nothing? You've been writing in every class, yes? I have pictures, I can show you. You've been writing in every class.
Sure.
Okay. You have some work to finish. Today there is no work to finish. Is it okay? If you don't feel bad, सभी का नंबर आएगा. अब आप आज नहीं लिख रहे हैं इसलिए आपका नंबर है. लिख रहे होते तो you would have been busy there. नंबर आता था लेकिन आपको पता नहीं चलता था because you are busy writing in copying and assignments खत्म कर रहे हैं. Okay. So come back to this. First of all, when we say pure substances, do you understand? It is chemical and physical. It could be only chemical also, it could be only physical also, but typically the way we have studied and we have grown up, chemical is what we think of, but just by being chemical is not enough to maybe look at a simplified system. Okay? So we need to look at physical one. Even the chemical one, when we think, we say, okay, same chemical species. This is what your knowledge, I expect your knowledge to be at this point. So when I say chemically pure substance or just pure substances, you will say chemically pure. So you'll add all that. You see, I'll say pure substance, you say chemically pure, and then you'll also look at the molecular formula and you say, okay, molecules will be the same. Okay? But that's not true. You can decide pure with respect to what? Okay. And all of us know what isotopes can do. Isomers, isotopes, radicals, then ions and atoms and molecules. Okay, so very, very different way of looking at what the chemical nature is. You see, isotopes, fissile है, नहीं fissile है, हमें available है, नहीं है, is a matter of life and death for a nation. You understand? Can you relate this? If I say, isotopes क्या है? Carbon dating, figuring out reaction mechanism, figuring out processes. कि ये tree grow कर रहा है, is this tree growing because of whatever is in the soil or whatever is in the air? You see, and you'll be surprised to know most of the trees, the mass comes from air. Could you have guessed it? And most of the carbon, most of the bulk of the tree is actually what it has captured from the air. मिट्टी से नहीं आता. You see, only because nutrients and all of that, and then the base has to be there, it has to be kind of, stand at one place, rooted. Okay, and then all minerals and transpiration, and then there is a pressure difference, and then everything comes in. And while everything is coming in, a lot of other things also coming in, important things also come in. And then there's a huge filtration process. So even though the water and everything may not be so good, but the tree itself, most of the time, unless, it is beyond a level. The bad things, they come in, and it's beyond some certain level, then only they start appearing in the fruit. Otherwise, the tree would filter, simple things, disturbances, it would filter. Okay? So if you find some fruit or something, contaminated because of the groundwater or the soil, it's very heavy pollution. You see, if it starts appearing in the leaves and in the fruits, because it has gone through that filtration process and still appearing. I'm not talking about something very special that has come in and the tree has itself, not evolved around it, and then something, kind of does not break up at all, kind of gets conveyed. convection, because convection just goes and also finds a way in the growth process. You see, it is so difficult. All this filtration, and then there is a growth process for the fruit and the flower and everything. And it finds a way inside. You know, just see. If it is finding a way inside, how much damage has already been done. Before we say that it's appearing there, it's not like a living being. You see, it's not like fish, which consumes and then it kind of becomes a part of the body and then it stays in the tissue. May not be doing anything, see, but it's still there, just stuck. Okay, like these microplastics, things, a lot of things. So if your flora is getting affected by the ground quality, I mean, it may be with a very good, aroma, with shape, size, good quality, bad quality, within one range it's okay, but if it just gets damaged, then it's an indication. But this indication will come only when the pollution is very, very high. You see, how will this information help you? We have discussed, for 5 minutes, something, probably, 10% of it was already known to you. 90% was new information. And how is it going to help you? Of course, it may come in the exam. But beyond that, you see, if you want to have sensors for, let's say, ground quality, water quality, all of that, if you want to have sensors, are you going to rely on trees and plants to give you that? No. You would probably rely on fish, something, animals. They'll get affected much, much faster. Then somebody may say, they are more intelligent, they are more complex. You see, an animal can do a lot of things, but typically, that's a better indicator, faster indicator. Even at a low level, you can sense it. Okay? So if you're relying on your plants to give you a sense of what the groundwater quality and everything else is, you're already late. Other ways, it's already beyond that. And of course, there's so many other things also. The possibility of growing everything without soil. Soil kari gaya. It's just rooting it, support, and a way to give all that. Or maybe all that is through convection mostly. But diffusion कहाँ होगा? मिट्टी है, पानी है, pores हैं, कितने भी hairs हो, water का movement easy है, and the water ऊपर सब evaporate कर दिया, then the pressure comes in, and when water comes in, सब मिलके आ गया. Okay. So all this is also new knowledge. I suppose knowledge was already there, but it's related to this. Okay. And then physically, इसको कैसे break करेंगे? How do we take care of this part? Yeah. Anybody else from the? Shape is of course you can, because it can be a spherical, dendritic, all kind of crystal structures. That shape is also one of the. So a state of aggregation of molecules, how these different molecules or the constituents are arranged. Okay. And now this aggregation, was taught to you. State of aggregation, one states of matter was taught to you. और वो aggregation से तो unicorns ही बनते चले गए. Aggregate करते गए unicorns बना दिए. That's how most of the unicorns have come. Aggregate करके. हम भी एक सब चीज है. आप कुछ नहीं कर पा रहे. जरा सोचो. 130, 42 hours, 3 exams, 1 lecture. यंत्रा को साफ कर सकते हैं. पता है कौन है? बच्चा है. इतने लोग. That is the power, you see, of aggregation. But वो phase सही नहीं है. Chemically तो सही है. This group is chemically very, very good. Radicals भी हैं, isomers भी हैं, isogroup भी हैं, all kind of things are there. ना purpose है. और ना state of aggregation is okay. state of aggregation and micro for for some group, for some activity, for some classes, for maybe watching movies, for some activity based test. But for this big activity based but इतना important है state of aggregation. Okay. So state of aggregation में क्या बना? Liquid, solid, gas, plasma, Bose-Einstein, and complex. So this is, let's say, last 20 years or maybe last 15 years we have agreed to saying that this is a separate state of matter. It is, because as we have already discussed, it depends on how you define the state. You see, so it is a different state of matter. A colloid is different from a liquid. A gel is different from a polymer. So but technologically it's very important. Scientifically and technologically also it is and last 15 years technologically it has become very important. You see, so all the gels that you use today, okay, maybe if you care to remember since you were growing up, how much change has come in the products. Okay, the colors that you would be using. Okay, even the simple colors, very primitive things. You see? The crayons, the colors, that has changed. The tubes for pain relieving, the toothpaste, that has changed. The packing has changed. The way all these other things that come out of a tube, you see, that has changed. All that has changed because we have now looked at complex fluid. And technology is based on complex fluid. You see, everything has changed completely. You see. And it is changing even more. Okay. So mostly scientifically it was already understood that they are different, but technologically there was no push. But now there is so much push that you have to understand this separately. So there will be a complex fluid thermodynamics, there will be a heat transferring complex fluid, there will be a mass transferring complex fluid, momentum transferring complex fluid technology. You see, so all of that has to be taught separately. Very, very different from what the normal gas, liquid, solid, vapor would behave. So do you mind if I drink this a little? Solid, whether mic use करें तो सही है. क्या कहते हैं? So every time I go to Shivnadar, they give me one of this. Different colors, 3-4 colors are there. So I go there to help them. And they keep giving me some steel, some brown, but very convenient. The size and everything is convenient. It's so nice. So liquid, you understand, solids, gas, plasma, there's this. So while we have, I suppose you have some good understanding of this. Okay, talk about isotopes. And isotopes that are fissile and isotopes that are not fissile, and then for nuclear energy and then relating it to life and death. Okay, so nuclear energy gives you life also. You understand this. Okay? There is a nuclear deterrence. You see, forget about the energy that it will give you and there. But it's a deterrent also, so it gives you life, it preserves your life. And of course it can kill. It has killed in the past. So either by design or by accident, both. So too much power. So when you look at isotopes, you don't worry too much about this, ki ye hai kya, except for dating and tracking purposes. Okay. So most of the uses of isotopes are in dating and tracking. And do you know that the department has a unit where we could track what is going inside a reactor by putting in isotopes? Does anyone of you know that? We have worked on this, you see, with BARC, Baba Atomic Research, and we developed a lot of technologies, okay, where these isotopes, they go inside the reactor and we track what the emission is, what the radiation is. And with that radiation, I mean, of course, it will be a composite sense, but with that, we kind of deconvolute and figure out how the liquid is flowing. So in a packed bed, if you want to figure out how the liquid is flowing, how do you image it? So it may not be optically possible to, but ultrasonically maybe you can, with other kind of imaging you can do, with other kind of radiations, but one thing would be that you put in an isotope and you kind of track the radiation at different heights. So you know where the radiation is, and from there you kind of create the liquid flow and texture and everything, and you figure out that there is a stagnant zone there, okay, or this is moving well, or this much wetting has happened on the solid surface, to figure out what is happening inside a packed bed. You see, so we had one, and if you can find out actually, and maybe you can have a look at that process also. So that is one, and of course archaeologically, how old things are. They are carbon dating, okay. And so many other things. Medically, medically also, where things go in. So they put in in your. They do MRI or lots of things, you see, and they put some isotope and they track it, okay, and it's very, very interesting to figure out. I mean, to know that in some of the cases, you see, because isotopes would have a half-life. Let's say if they are radiating also, because if they are radiating, they are losing something, you see, and they are radiating only within a band, you see, so they not keep on radiating till the very end. You see, they become something which is stable and not radiate after a while, you see. So you are radiating, you are losing, and you are also moving out of the band or in a state where you not radiate anymore, so you're not useful at all. So if those tests have to be done, who will provide the isotope? Just think about this business. You see, so at times, if Apollo, Max, all these hospitals, if they have to do this, you see, to figure out, where the blood is, inside of the body, and they do the imaging, with a contrast and with a dye and with a radioactive dye, you see, not just a color, but a radioactive dye, so that they kind of enhance the image and get a better picture. So read about all of that. Many, many times, and I have had some experience of this. They will raise a requisition for an isotope, okay. And that isotope will be shipped from Finland, from Norway, and within 42 hours or 24 hours, because they'll make it there and then it has to come, it will keep on degrading all the time. And how do you stop it? It's not like cool it and then it will stop. It doesn't work like that. See? अंदर ही अंदर कीड़ा लग चुका है. बाहर से पेंट करो क्या होगा? कुछ नहीं होना. It will keep on degrading. Other cases, you'll have a storage. So you'll cool it, this, that, everything, conditions, and you ship, and the shelf life and everything increases. But this half-life is kind of, that's the nature inherent. So it's spontaneously degrading. Doesn't matter what you put in. Okay, so it's not degrading because you do something. So it is spontaneously happening. So all efforts to control that will not work. External efforts to control that will not work. You see? So nucleated versus spontaneous processes. You see? So if it is spontaneous and you put in too much effort on controlling it by saying that, okay, this is not there, this is not there, this is not there, it doesn't help. It's degrading. Okay. So they ship a larger quantity, and then this logistics had to work. You see, so this has to be prepared there by some bombardment, by something, you see, made there, then shipped to the hospital, to the patient. Okay. So logistics is extremely important there. And there are specialized people for this. You see, there are specialized agencies for this kind of logistics. Okay. And they have all the clearances and everything, and then from the source to this. Okay. Very, very interesting journey of that isotope. So when we look at isotope, these are the things that I know. But with isotope related to life and death, national security, sovereignty, isotope. Separate nuclear material, raw material, cancer, all that. Of course, radicals you understand. Ions also we discussed in one of the class. Atom, molecules. Liquid, solid. We need to have a picture for these. Okay. And we also need to look at what a phase is. Okay. Like what a material is here, and we have all of this. What a phase is, and we have all of these. Okay. So we look at the chemical composition of the material, and we look at the phase of the material. And phase, as I said, cannot be very clearly defined. You see, it is like a loose definition where looking at a group of or looking at a material, you should be able to tell whether it belongs to this phase or not. It's not a very strict definition. And it is not just this. The concept of the phase is being used for lots of other kind of groups also, to identify different kind of systems also, not necessarily physical systems here. So if you look at those, there is something called a, and this you will study later. Have you heard of this term? Order parameter. So order parameter is what defines the phase. So you look at the evolution of a phase. Okay, so you have phase 1, you have phase 2, phase 1. So order parameter value this is this phase. Order parameter value 1 is this phase. And you track that order parameter. And you say, okay, half crystalline, half not crystalline. So order parameter, if being crystal is 1, it will be half. Okay. So the way phases are understood in terms of order parameter. And you have the freedom to choose order. And some of the order parameters would be a good choice, a better choice, then other choices for order parameter. Okay. So fortunately, many systems have been used. Many order parameters are already known. You see, like density is an order parameter. So density higher than this, there's a good chance that it is a gas. So lower than this, there's a good chance it's a gas. Higher than this, a good chance it's a liquid. Very, very high, good chance it's a solid. Okay. Sometimes mercury add not solid, एक दो exception चलता है. Okay. वैसे भी mercury किसको मिल रहा है. Okay. So otherwise, typically this is the thickness, density range for the solids. This is the density range for the liquids. This is the density range for the gases. Gases are easily understood. Solid, liquid में थोड़ा सा confusion है. Okay. Plasma, of course, gases and ions, very high temperature. Lot of technologies are dependent on this. All kind of depositions, all kind of structures that are made. Chip industry, all these semiconductor fabrication. You want to make something, and do you want to make it by picking up this and putting it here, or you want to maybe have lots of it in the atmosphere and a pattern, and you say, okay, the pattern decides how it collects. You see, so that is also one way. It's like spraying through a mask. So you spray through a mask, and you have all this gravity you can make. Okay, or lots of patterns that you can make. These stencils and other things, mask, and you spray through it, and you make something. So that's much easier than actually putting material in a brush and applying it. So many technologies, and plasma is an integral component of it because it can allow things to be in abundance, and the receptor decides what to pick. Okay, so it kind of allows you. So even this is very important. So क्या important होने जा रहा है? Solid, liquid तो हो गई, solid भी हो गई, but these are the new things. Probably they are not so important in my times, but in your time they'll be more important. This is absolutely is more important for lots of products that are being made. Okay, so you need to study a lot of these. Bose-Einstein, condensate may be your grandchildren. It will become important. हमारे समय में तो only if you are doing theoretical physics. ठीक है. Otherwise इतना अभी important है. In lots of technologies that we make. Not directly. Before somebody says, sir, यहाँ से, and ultimately it's just because of this. Not that kind of relation. But if you don't study it, it's okay. You can still do a lot of things. But you need to study these. All you need to study these. Okay. It's a phases हो गया, order parameter हो गया. So you'll have to see what people have chosen as order parameter. Okay. So gases, liquid, solid, we have some understanding of what a liquid is, what a gas is, what a solid is, okay, and plasma, this and complex fluid, this we all understand. There is another distinction that has to be made when we talk about material. So a material can be pure, the material can be in the same phase, but the material in terms of what the neighbors are, okay, and that is also going to become very, very important, but it has the new distinction that I am going to talk about pure systems, okay. It has been important for the last 100 years, okay. It's going to be even more important. It has been important for the last 100 years because of other reasons, okay. Now it will be more important of course, for the reasons that were already there and some more new reasons, okay. And that is, we have already discussed, we look at bulk and we look at interface. Okay, so we say it is a pure material, it is liquid, but this liquid is in the bulk, this liquid is at the interface. You see, that thermodynamics will be very different. Okay, and we as scientists, engineers, we have accepted this. Okay, so there will be a different thermodynamics for surfaces. Maybe you have done that course in the first year. Some chemistry course about surfaces. Have you done that? Some course. So did it bother you that why should we be teaching you surfaces of all the things? It didn't bother. The reason is because it has been identified that that is different. Okay? That surface and interfaces are different. This surface means that it is an interface with air, atmosphere here. Interface is, this is something need not necessarily be atmosphere. Then it's an interface. Otherwise, a surface kind of implies that you are exposed to the environment or the atmosphere. Okay, so bulk and interface. This liquid, chemically same, everything same, still a liquid. This liquid is different from this liquid. So for the last 100 years, it has been important because of detergency. So the importance was, this is bulk, this is I. So all kind of cleaning systems, and also liquid gas, bubbles, drops, jets, all kind of operations. So a lot of unit operations would happen in liquid phase. Okay, liquid gas, there's a liquid and gas is bubbled through it. Okay, then who decides what the size of the bubbles would be, how bubbles would grow, and depending on the size of the bubble, so much material would have so much surface area per unit material. Okay, and that surface area would mean that if the driving force is the same, the flux being the same, the amount transferred would be very different. Okay, because then you have more surface area. Okay, so all those concepts are there, and it was important because of all of this. Okay, now there is a question. The hood has to be removed. Hood हटा लो और जगा लो जो लोग सो रहे हैं. You're allowed to slap them. Just a little, not a tight slap, but हल्के. Okay, जगा लो जिसको भी जो सो रहे हैं. I say it has been important for the last 100 years because early 1900s, people have started making soap, detergent, this, that, bubbles, drops, all of that. This got a new added dimension now. Bulk and interface has got an added dimension now. Can anybody tell me what that is? Anybody? सो रहे आपके इधर जाग जाइए, जागो जागो जागो, क्लास जागो, क्या कर रहे हो? Anybody? वो तो वही है, मिसल फॉर्मेशन इज दैट डिटर्जेंसी में है, मिसल्स बन के बाहर निकलना. But you're right, slightly more advanced than just the bubble drop. Okay. Anybody else? But it's in the same class. It's not very different. There's a whole new technology that has come in. यार ध्यान से इसलिए सुन लो, हिंदी में बोल रहे हैं, इंग्लिश में भी बोल सकते हैं, और हिंदी में बोल रहे हैं, ध्यान से सुन लो। इंफॉर्मेशन टेक्नोलॉजी में जॉब नहीं मिलेगा तुम्हारे मन का, एटलीस्ट पहला जॉब। ध्यान से सुन लो सब लोग, जग के सुन लो, ओके। मैनेजमेंट में जॉब मिलेगा नहीं मिलेगा किसी को नहीं पता। मैनेजमेंट स्कूल में जाना बहुत मुश्किल है और तुरंत जाने में कोई फायदा भी नहीं है, अनलेस यू हैव वर्क एक्सपीरियंस, तब कुछ उसका बेनिफिट होता है, ओके। सो इंफॉर्मेशन टेक्नोलॉजी चली गई, मैनेजमेंट चला गया, एंटरप्रेन्योरशिप इतना आसान नहीं है, ओके। तीसरी चीज फाइनेंस का, जब पैसा ही नहीं है तो कौन खाएगा कौन खिलाएगा, ओके। एंड एनीवे इट इज़ अ वेरी टफ लाइफ, यू नो। ट्रेडिंग करोगे, ये करोगे, रिस्क मैनेजमेंट करोगे, हाई डिग्री ऑफ मैथ्स चाहिए, कंप्यूटर चाहिए, एआई चाहिए, इट्स अ वेरी टफ जर्नी। करोगे बट इट इज़ अ टफ जर्नी, ओके। ये बचा क्या तुम्हारे पास, technology. So whenever I talk about a new technology, that is where your jobs would be, and you can, and that jobs will not come as a production manager only, you see, or somebody who would work in the plant. There will be lot of other things that will enable it, okay. So उसके लिए सोचो, so you have to figure out on the new technologies की new technology कौन सी आ रही है, उसके अराउंड स्टॉक मार्केट भी होगा, उसके अराउंड मैनेजमेंट भी होगा, उसके अराउंड और टेक्नोलॉजी भी होगी, इंफॉर्मेशन टेक्नोलॉजी भी होगी, उसका फाइनेंस भी होगा, बट अराउंड द टेक्नोलॉजी, वैक्यूम में नहीं होगा, see. So your mind should always be looking at how things are functioning, how they used to function, how they are functioning now, and what in future is, you know, things are going to come. ये फ्यूचर है तुम्हारे लिए, तुमको नहीं दिख रहा है किसी को, आर यू नॉट अवेयर ऑफ दिस कि ये होगा। मैजिकली आईटी में जॉब थोड़ी ना आ जाएंगे, मैजिकली डेटा के जॉब थोड़ी ना आ जाएंगे यार तुम्हारे 2 साल में, ओके। एंड दिस इज द टाइम टू लर्न न्यू टेक्नोलॉजीज, इज वन ऑफ द वेज। एंड वो तो करना वैसे भी करना है ना, बिकॉज यू स्टडिंग टू बी अ केमिकल इंजीनियर। इस क्लास में यही सब हो रहा है, इस जगह यही सब हो रहा है। इट्स इजियर टू लर्न अबाउट टेक्नोलॉजी while being here than to go out and learn it. This पूरा ecosystem is based on technology. So many times I use the word technology in this class, but कोई रिस्पॉन्स नहीं, कुछ नहीं, आगे नहीं बढ़ रहा। देखो क्या हो रहा है दुनिया में, कौन सी टेक्नोलॉजी आ रही है, ओके। वो आईसी इंजन पे बना रहे थे, फिर वो ईवी आने लगा, फिर अब कोई कहता है नहीं आईसी ही चलेगा बट विद सम अदर फ्यूल। सो अभी you need to look at those technologies, हो क्या, कौन सी टेक्नोलॉजी आ रही, कंस्ट्रक्शन टेक्नोलॉजी, कौन सी टेक्नोलॉजी, ओके। यू नो, तो यू लुक एट ऑल द टेक्नोलॉजी। डेटा को कैसे हैंडल कर रहे हैं, जैसे एआई हैंडल करेगी, आप हैंडल करेंगे, आप तो कुछ नहीं करेंगे, आप दिल्ली में तो कम से कम नहीं करेंगे, अच्छी जगह पर। सो व्हाट इज द न्यू टेक्नोलॉजी व्हिच हैज मेड इट very very important for you to understand this, whereas bulk and surface, so surface thermodynamics or thermodynamics of interfaces is already accepted as a separate thing, you see, and all kind of changes, modifications and add-ons are added to it when we talk about that thermodynamics, you see, thermodynamics of surfaces, okay. And a course was taught to you about interfaces and surfaces, okay. So what is, and in the beginning it was, you know, as Sony also says, missiles, bubbles, jets, liquid, you know, basically with contact area, you see, and also cooling things, you see, you spray them, you cool them, like all these chilling towels and everything, you can know how the milk is cooled, okay, ऐसे करके देखा नहीं, ठंडा करता है, फिर ऐसे करता है, all the time attracting other people also, ये क्या हो रहा है, तो जाकर बोलोगे एक मीटर दूध दे दीजिए, ऐसा जोक सुना है? नहीं सुना?
1 मीटर दूध दे दीजिए,
हाँ
1 मीटर।
अबे जोक है ये। अगर किसी को नहीं पता कैसे दूध मिलता है और तुम जाओगे, एंड द वे वी आर बिकमिंग लैक्टोज इंटॉलरेंट, दूध कौन पिएगा, और ऐसे करके दूध दे रहा है, देखा है किसी ने?
डोली चाय वाला, डोली चाय वाला
ऐसे दूध दे रहा है, और जगह लीटर में नहीं मिलता, पाव में नहीं मिलता, ये तो मीटर में मिलता है, ओके। तो ये टेक्नोलॉजी, दिस इज, ये टर्म सुना है किसी ने? माइक्रोफ्लूइडिक्स, हैव यू हर्ड ऑफ दिस? Miniaturization, making small things. So if you're trying to make smaller things, and so the amount of material that is at the interface versus the amount of material that can be considered to be in the bulk, that ratio changes. ये तो सबको पढ़ाया गया है। यार जे में भी सवाल पूछते हैं ना, इतना लिक्विड है उसकी 1000 ड्रॉप बनाई, कितनी सरफेस एनर्जी बनी हुई, ये हुई, कितना ठंडा हुआ, ये सब क्यों पूछते हैं? तो व्हाट यू डू विद दिस, ये तुम्हारी टेक्नोलॉजी है, छोटी छोटी डिवाइसेस। ये तुम्हारे चिप मेकर्स आर इन्वेस्टिंग इन फ्लूइड मैकेनिक्स, यू नो दिस। वो सर्किट तो ठीक है, ट्रांजिस्टर तो ठीक है, आईसी तो ठीक है, दैट वीएलएसआई डिजाइन इज ओके, हीट ट्रांसफर कैसे होगा? ओके, they're investing in fluid mechanics programs. अब उसको कूल कैसे करें मशीन को? Okay, so microfluidics है, nanofluidics है, nanomaterials है, all of that means that the interfaces have to be understood. So when I say pure material is not just वो जो PVT बना है तुम्हारी किताब में, और जो ट्यूटोरियल में तुमने सम्स किए कि इधर टेम्परेचर बढ़ाया, इधर ये किया, क्रिटिकल पॉइंट ये है, इधर से ऐसे घूम के आया, लिक्विड बना और सब्लिमेशन हुआ, इवेपोरेशन हुआ, ओके, कंडेंसेशन हुआ, ये सब पढ़ाया क्या होगा? कहीं तो फेज डायग्राम पढ़ा होगा। And this is state of matter, this is state of matter, and you change the temperature, you change the pressure, and then SV कर्व भी बना दिया, SU कर्व भी बना दिया, TLP भी बना दिया, TD भी बना दिया, VP भी बना दिया, कंफ्यूज कर दिया जी। 6 महीने बाद you will not remember anything. Okay, इसमें there is a hope कि कुछ रहेगा। So when I say pure, it is this. The palette is this. ये black and white नहीं है खाली, ये pure है, ये mixed है। ये pure के इतने shades हैं। Okay, pure है interface पे, pure है bulk में, okay, pure है ions हैं, नहीं है, all kind of things. Okay, so what I do is I take some pictures before you leave, क्योंकि ये AI में use करेंगे।
क्या?
I take 2 pictures, एक इस तरफ की, स्माइल करो सब लोग, और इधर बीच वाला रह गया, एक बीच में भी ले लेते हैं, स्माइल। और ये शीट्स का है, अटेंडेंस शीट्स का है, 2 शीट्स हैं। One last chance, ये हर कोर्ट केस में होता है। Has anybody signed for somebody else? कोई प्रॉक्सी है इसमें?
सर अटेंडेंस नहीं हुई है सर, मेरी अटेंडेंस नहीं हुई है।
अरे यार प्रॉक्सी है कि नहीं पूछ रहे हैं, जिसकी नहीं है।
सर मेरी अटेंडेंस।
चलो गुड, थैंक यू। 36 बहुत प्रॉक्सी, बहुत प्रॉक्सी। इस बार टांग देंगे। हमें कुछ नहीं करना है, माइनर की सेट है हमारे पास, उसकी इमेजेस लेनी है जी, उसकी इमेजेस लेनी है और इसकी इमेज लेनी है,
खेल दिए जाएंगे,
सिस्टम बता देगा मुझे। और फिर फोटोग्राफ्स भी हैं, और फिर तुम्हारा नेटवर्क कनेक्शन भी है, फिर तुम्हारा फ़ोन का डेटा भी है, फ़ोन किस टावर से कनेक्टेड था। दिखा जाओ, ये पहने डालो, गिर जाएगा। आज में तुम्हारे रीयूनियन में आई सेल दीज पिक्चर्स व्हेन यू कम हियर आफ्टर 25 years. तुम्हारे रीयूनियन में आई मेक अ स्टॉल फॉर यू एंड आई सेल दीज पिक्चर्स, नॉट सेल, आई जस्ट गिव इट टू यू। अभी इनकी वैल्यू नहीं है, 25 साल बाद बहुत होगी।
I mean, when you mean pehle, do you mean before the spawning of this entire event?
About the one night.
I did. Yeah, I played in that night. मैं खुद के साथ खेल रहा हूँ. अबे इसलिए जो मेरा करंट बॉट है algorithm जो मिनी that is a max algorithm. Full fly.
हेलो सर.
खांसी तो इसलिए आ रही थी क्योंकि सर्दी हो रही थी। सुट्टा यार भाई 10 दिन में जा लो ऑन एन एवरेज समझ लो 6,000 कम करना। अब मेरा कम ही था जब से फिर कैंपस में गया जो सीनियर्स है भाई जो सीनियर्स है ना मेरे पे PhD वाले जो है वो बहन जो बहुत ज़्यादा सुट्टा फूकते हैं उनके साथ बैठे बैठे
बाद में अच्छे से बात करते हैं। अच्छा डिसीजन, राइट डिसीजन।
Quickly. Okay, right. So looking at how to get the compressibility factor, because we use a problem to finding the compressibility factor, and the compressibility factor, as I said, one of the ways is to get it from experimental data, and in experiments you need to be careful that you actually achieve the effect. And in physical experiments achieving the equilibrium is very difficult. In a 3-hour lab, it can't be done. It's not easy, okay, because it kind of progressively, the approach is slower. In contrast, in numerical methods, if you are closer to the equilibrium, you actually speed up. Okay, so major difference with approach to equilibrium. Okay, and especially in this case where we are looking at deviations of z from 1. Okay, so a little bit here and there can also make a difference. Okay, so one is looking for those small variations. One of the things is that if you don't know the answer, if you want to express something, okay, then the best way, not the best way, but a kind of rigorous way to represent anything that is unknown and is a function is in terms of basis functions. Okay, and you will not be wrong because it's rigorous, it's true. Okay, and then come in quickly. Quick. Continue. And find a movie that you like. I'm just waiting for all this disturbance to die down and तभी बात करते जा रहे हो। Where is this murmur coming from? तुम मेरे सामने ही बात कर रहे हो। I can hear you speak. इधर पूरा जोर कर रहा है। फोन में भी कोई इधर कर सकते हो कोई भी। Get into this habit of paying attention for at least an hour, 50 minutes or whatever. अभी भी बात हो रही है, वो देखो अनंत के सामने वाले जो 3 चश्मे वाले उनके बीच का चश्मे वाला हिल रहा है इधर उधर। मतलब कैसे पढ़ाई हो सकती है सोचो। Is there a way to even get anything done here? Okay. फिर क्या तो people like Trump are bad, I mean you have to see why they are there. They got elected. They are popular presidents. See why they are like that, If instructors lose faith, it's because of this. This is a training into listening and communicating, discussion for an hour. You see, you can do that. Not taking notes, this, that. Just listening, discussing. It's a different kind of course. You have to cooperate. You kind of that background noise is there. You have to use the mic. ये तो वैसा माइक भी नहीं है जो फेंक के मार सकूं मैं। All my politicians teach me. अब माइक से चिल्ला के क्या होगा? माइक फेंकने से काम बनेगा। That is what the house is like. तो ध्यान से सुनो, ये सब सीरियस चीजें होनी है। We are on an accelerated pace अपने हिसाब से to get the course done. तो हम पढ़ना नहीं चाहते हो। So I'm saying if you don't know about anything कि ये क्या होगा, then you say okay, it is like some infinite expansion in terms of basis function. Till this point, you are absolutely correct. There is nothing wrong in it. It's the basis functions are chosen correctly. Okay, linearly independent set and a complete set. This is okay. But now you have a choice to get all the coefficients properly. Okay, and there is a way to get them because you can have infinite number of coefficients all given by a rule. Okay, so in that sense it's kind of not really that unassailable infinity kind of thing. You can actually find that the coefficient n is this. Okay, and one way to evaluate is that most of the time they'll come and Maji is trying to move mountains. They go Maji and Maji is not even listening. She has even forgotten that her name is Maji. Maji, what is your name? Suman Maji. Maji is also your name. Don't forget that. Okay, आप बात करते जा रहे हैं. See, you cannot remain disciplined. Look at the kind of CEOs we are getting in the world. I mean, बस सोचो बस कैसे लोग हैं. These are the kind of CEOs you are going to get in your life. Okay, these are the people who are going to come up and maybe the world needs them. That's why they are coming up. हमारे जैसे नहीं मिलेंगे तुम्हें कि डांटेंगे फिर मुस्कुराएंगे फिर डांटेंगे फिर संभालेंगे फिर समझाएंगे. You will not get people like that. People will punish you. Kind of just out of sight, out of mind, and thrown out of the story. You see, nobody will even bother to give a second look. कुछ नहीं है. You see, there's nothing in any person that kind of bothers a second look. Okay. वो traits अब नहीं है दुनिया में. People are not operating like that. You see, एक humanity है ये hurt नहीं करेंगे ये नहीं करेंगे. It's all gone. My next 10 years are going to be very very rough with very rough people with a very rough world. Time मिला एक वो करने दो. चलो, let's listen to this. So fx को लिख देंगे. And how can you use this? Because in your whatever you'll do, you'll have to find out some function, something unknown. How does this value, that value, and there you say, okay, this is like a infinite series. In that infinite series, all the coefficients, so you can make some assumptions in how do you find the coefficients. So they may not be rigorously found, exactly found. Okay, and there are ways to find those infinite coefficients. There will be a rule that will define that. Okay, and the way they are calculated is through a recurrence relation most of the time. If you remember, there was a set of differential equations that you have to solve. Bernoulli's equation, this equation, that equation, and you'll get all kind of polynomials. Remember, Legendre polynomial, this polynomial, that polynomial, all solutions of special kind of differential equations. Okay, so there may be 50 of those, and all 50 of them would give rise to many different kind of polynomials. Okay, and with very special, coefficients and everything, special properties also. Okay, and all of those, if you remember, there was something that says, okay, coefficient n plus 1 is related to coefficient n in some way. So that if you have 1, you can get 2, if you have 2, you get 3, you get 4. So this is typically the kind of things that you will do. Okay, but even then you will not solve till infinity, so you will then kind of curtail it, truncate it, and you say, okay, these many terms only, but within these terms the coefficients are exact. Or within these terms, but the coefficients are also estimated to some approximation. You see, so all those kinds of things would come, which would mean that your function that you are going to evaluate or the solution that you want to evaluate will not be exact, but closer to that. Okay, an approximation, even in an analytical method. You see, when you compute something, then you anyway make some mistakes, because real numbers you will not be able to represent all of them in a real way. Okay, but there are ways, you see, interesting ways, where you can do a different kind of maths. Okay, but it's okay. So this is one way. Okay, and then you have to choose that basis function properly. And some of the basis functions that are routinely used are, let's say, the power series x square, x cube, or 1 by x square, 1 by x cube. Okay, and you will see both of them. When you look at the virial equation of state, there is a p, there is a power series in p for z, and there is a power series in 1 by b, okay, for z. And the coefficients are there. Okay, so that's okay. Now these coefficients, as I said, the Fourier series, that is one of the ways, and this is so important. You see, what we discussed about the Fourier series, why it has survived. One of the, it is a good approximation, and it kind of, if things are wavy, if things are not flat, Fourier series is typically a very good approximation. You see, it is a good approximation because the number of terms that you would require to represent any wavy kind of function with combination of sine and cos, like in a Fourier series, the number of terms is very little. Okay, so with very few terms you can approximate, okay, the function very well. So the number of terms are less, and then because whatever you do, you will have to necessarily do it at least for some test cases for some number of terms, and then you will maybe increase the number of terms, and then you look at the difference and you say, okay, you know, the number of terms that I have taken are good enough. I don't have to take extra terms, because that is the question. You see, you cannot be calculating number of terms, you know, till infinity. You see, and then a special case of that would be that you need only 1 or 2 terms, or maybe 3 terms, okay, at most. So this is what the landscape of, you know, functions and how to find solutions and to represent. You see, this is the key. You see, and if you do whatever future courses you will do, or whatever, you know, problems that you will solve, if you keep your mind open to this, things will be much more easier for you. Okay, and they'll make a lot more sense to you if you just keep this in mind. You see, otherwise it's very easy to get lost in so much, you know, all kind of summations, this, that, you know, exponentials, complex number. You know, maths is presented in a very difficult way. It's not easy to understand, or very easy to kind of forget also. So we do all of that, and in Fourier series I said, if you get the first 10 terms, and if you want to now approximate and let's say, okay, 10 more terms, 20 terms, then the first 10 terms don't change. You see, so the incremental number of extra terms only have to be calculated, and this is a very big plus. Okay. So representing, so you have a choice, you say, okay, my z is this, but my z is not only, you know, just this, maybe the Fourier expansion for z. Who is stopping you? You get a chamber where you can put in known amount of material, and you can vary the pressure and temperature and you know, just kind of measure. You see, we have those kind of things in our UG lab. Okay, you do all those PVT measurements, you get a equation of state. You say, okay, I increase the pressure, so high pressure, low temperature, you know, Z is different from 1, so how is it Z? How is Z different from 1? You do all those experiments, okay, and then try to fit Z is some, not in a virial equation, I mean a virial but Fourier series, okay, not as a power series but as a Fourier series. Who stops you? Just do this, see what kind of results you get, okay. This whole number of terms, you see, it is so critical that, you know, 20 years ago maybe, or maybe even 10 years ago, when I was solving these molecular dynamic, doing some simulations, I have to write my own code for evaluating an exponential, for evaluating a sine, for evaluating a cos, because, you know, sine and cos, because you look at the force measurement, then you'll have to look at the components. So sine and cos have to be evaluated. Okay, I have to write my own subroutine for it. You see, that if sine has to be calculated rather than the inbuilt, it calculates it from mine. Okay, so I use that, you know, 1 minus x or x plus x by cube, those kind of expressions. Okay, this is one. Even exponential, because many times you are looking at the decay and the exponential comes in. So exponential, sine, cos, these two are very common, you know, in molecular dynamic simulations. And I have to write my own codes for them. Why? Because the inbuilt ones would take more time. You see? Say sine, and then we do all kind of, you know, time analysis also, look at, you know, function evaluations, do it 1,000 times this, 1,000 times inbuilt, and you say, okay, you have saved this much. Okay, so you do those kind of exercises, which is something that is unthinkable for you. Maybe you will not even realize it was special at that time also. You know why I'm writing this? I said I'm writing this because it kind of speeds up my code. Okay, so this truncation is a very serious business. Okay, otherwise, you know, you can't even work. Okay, so you get an analytical solution, but to evaluate that analytical solution, you see, you need to truncate. Okay. Then we said there is a completely different way of looking at functions also. So what you say is that you know function somewhere, and then you say, okay, if I know this, then I'll look at all the deviations. And the deviations would be a sum total of all different order of derivatives. You see, that is what a tailored series is. You see, that I know the value here, and if I want to know the value here, then of course I'm looking at the derivatives, but I'm not looking only at the first derivative, I'm looking at the second derivative also, third derivative also, fourth derivative also, because in principle all derivatives would kind of impact, you see. So this is how a Taylor series expansion is done, and this also allows you to a way to let's say communicate between different functions. Okay, so function 1 written in terms of Taylor series, function 2 written in terms of Taylor series, and then they can communicate. Function 1 expanded in terms of a power series, function 2 expanded in terms of power series. Okay, and then you do all kind of algebra, whatever is required, and you say, okay, coefficient on this side, coefficient on this side, and these coefficients are related to the coefficients here. You see, a very, very common exercise that you do. Okay, so which is unknown functions all brought to basis functions, and the coefficients are measured. You have done this kind of thing. If you remember, in some maths course you must have done it. Okay, that the coefficients are like this. Physics also you do it sometimes, depends on the level of physics you are doing. Okay, so Taylor series, then of course one of them could be 0. So you say 0 as a special place, you see, nothing happens, here, direction changes, the sign changes, so many things. You see? So we say, okay, a special case of Taylor series. Okay, and then what kind of mistakes can you make in Taylor series? You see, Fourier series, I told you that is very, interesting mistakes can be made. Okay, and we will still make them. You see, very, very interesting mistakes. Okay, which happen. Even now, yesterday I was discussing this because I just kind of finalized my student thesis and I was looking at phase separation, and we are looking at, the critical quenches, which means that that you are exactly in the middle. So there is no minority or a majority phase in phase separation. Okay, so if there is no majority or a minority phase in phase separation, you don't know which phase will appear first, which phase will appear as a continuous phase, which phase will appear as a dispersed phase. Okay, so it's a big problem. You see, which droplets will you get? In a solution when a phase separation happens. So if one is minority, the other is majority, you already know which one will appear first. Okay, but if it is, let's say, exactly the critical quench, that's a term that is being used, then you don't know. You see, it's not easy because it can be this way, it can be this way. Depends on the fluctuations, and you cannot say that my equation will not have fluctuations, because if everything else, nothing else is there, at least the temperature is there. You see, so KBT, everything will be moving here a little bit here and there, so that has to be accounted for if you are worried about what kind of quench. Okay, so when you do simulations, numerical simulations, you are worried about these fluctuations. When you do experiments, then of course there are so many errors that can come in. So, and depending on which side of the quench you are, one of them will become a majority phase, the other will become a minority phase. Okay, the one that will become a minority phase will appear as droplets. ऐसा होता है, हाँ, okay. But the whole thing is analyzed through a Fourier series. Okay, and Fourier series by definition would have oscillations. You see, and when you simulate it and when you write answers to this, you will say that at some places this becomes a minority phase, at some places this becomes a majority phase. You see, the current understanding of critical quenches is this, that in some part of the solution or in some part of the system you will find droplets of these, in some part of the system you will find droplets of these. Okay, and everybody accepts that. ये quench है, ऐसा होगा, mix होगा, ये होगा. Can you see some kind of check that was missed in all of this? Anybody? I'm talking about something that is very important. It is the state of art. This is how the best people in the world see it. This is how the experiments have happened. This is how the numerical simulations have happened. And it is a critical quench. And I've given you just some idea about what is the minority phase, what is the majority phase, and then phase separation, which droplet will appear. So you know the picture. And the whole analysis is done through Fourier analysis. You see? What do you think needs to be checked? And what is something that people have missed out on? And I'm talking about the whole, ये जितने PhDs and institutes, वो जो रैंकिंग आती है ना फ्रॉम 1 to 500, everyone is this one. People have not even bothered about this. First of all, maybe they didn't find it important, otherwise they would have solved it. But people were happy doing it. But when I went back after the class and I was discussing this and I realized कि यार ये हम Fourier से करते हैं हमेशा, maybe it is spurious. Maybe it is happening because everybody is using Fourier and the Fourier by itself would be oscillating between this and this. जब इधर है तो ये majority है, जब ये इधर है तो ये. You see? So even though the understanding would still be correct, it can still be a mix. Okay, because intuitively it looks like a mix, कुछ fluctuation होने कहीं ज़्यादा होगा कहीं कम होगा. But method is not right. The thing is that even if there are no fluctuation and there is one directed majority phase and a one definite minority phase, okay, the Fourier analysis would still give you a mix. So if you are, let's say, delta this side of the quench, then one is a definite minority phase. You should get that. And in phase separation, you know, if one is winning, then it just keeps on winning. That's magnified. ऐसा होता है non-linear processes में, if one wins, then one keeps on winning, you see, in non-linear processes, which is, it's a non-linear process. So, if you're doing simulations on just on this side, why should I get a mix then? But Fourier analysis will give us a mix. You see, so it's a spurious result, which means that the result may be correct, but the method to get that is already imposing a mix on it, on the solution. You see, which is not proven by this. You see, it may be the answer may be correct, but the proof is not correct. You see, now you see the impact of a little thing. You know, just as an example, you see, talk to anyone who is an authority in phase separation. You know, the world's best scientist, like the lady that came here. You know, about the molecular simulations, quantum mechanics. She has a lecture here. You know, she came from England. You know, I gave a mail also that you go and listen to her. Okay. Talk to anyone, you'll see this, you see. So a little thing of understanding about Fourier analysis that is taught in maybe whenever the Fourier analysis is taught, it's there, you can see that, it's very intuitive. Okay. And people make those mistakes. Why do they make mistakes? Because it's very easy to look at sine, cosine, do all kind of analysis on that, you know, all kind of transforms are easy. Sine को करो cos होता है, cos को करो sine होता है. You know, जितना इंटीग्रेट कर लो एक्सपोनेंशियल में इट्स इवन ईजियर. You see? तो ये सब हमारे चोजन फंक्शंस हैं. ओके, वेरी वेल बिहेव्ड. यू नो, पावर सीरीज में क्या है, जितना डिफरेंशिएट करोगे वन पावर इज लेस. ओके, सो दैट इज द बेनिफिट दैट यू गेट. If you're not differentiating, it moves towards linear. Okay, but then, so this is how you enjoy maths. You see? Otherwise, you know, the world kind of just pushes you away from maths, which is a pity, you see. So Taylor series, Maclaurin's में, the kind of mistakes you can make, of course, delta x वाली कर ही सकते हैं. You can make those mistakes, which is very common because you have discussed that, and maybe intuitively also you understand, and maybe in most of the situation you already know in the neighborhood. The function value is known in the neighborhood. So you say, okay, the function value is known in the neighborhood, only slightly away from it. ज़्यादातर हम ऐसे केसेस लेते हैं. We are not saying कि पता यहाँ है, निकालना होता है. ये कभी नहीं करते. Astronomy में करना पड़ता है. Because it's so far removed from us. So rocket science में ये difference सबसे पहले कि यहाँ पता यहाँ है, करना होता है. तो वो रोबोट यहाँ तो चलाना आसान है, यहाँ सब स्कूल के लोग भी चला लेते हैं. छोटे-छोटे. I mean, nothing with kids, you know, kids can be very creative. उनको पढ़ाया नहीं गया ना. But difficult है. तो हम कहते नहीं x ये x थोड़ा सा चेंज कर दिया, यहाँ देख लिया. Okay, जरूरी नहीं है. Okay. So that kind of delta x greater than 1 kind of problem doesn't come. And otherwise also all the established equations हम non-dimensionalize कर देते हैं, हम scale कर देते हैं. So all that kind of in a roundabout way takes care of the delta x problem, or delta x being greater than 1, which is the biggest problem, you see. लेकिन ये अपने आप ही हो जाती है. You don't realize, you don't actively do it. It already happens. You know, हम नॉन डायमेंशनलाइज कर देंगे, स्केल कर देंगे, पास ही में रहेंगे फंक्शन के. You see. और भी रीजन है पास में रहने के, बिकॉज वी एज्यूम कि बिहेवियर ज़्यादा बदलेगा नहीं. ओके, so delta x वाली प्रॉब्लम, what can be the other problem? I have already given you an example of Fourier series where I just told you that a little bit of problem can magnify to this kind of global addition, not only in this class, a global addition. So इसमें क्या हो सकता है? What kind of mistakes can happen? Very interesting mistakes. Very, very interesting mistakes. तौकीर, एक सवाल पूछते हैं. And you know, just look at the perspective. You know, don't see beyond that. Okay, beyond this question. जो बच्चे खाला की ज़्यादा सुनते हैं और अम्मी की कम सुनते हैं. अरे यार, तौकीर को समझना है, तुम्हें समझने की जरूरत. खाला इज लाइक योर आंट, योर मासी, योर मदर सिस्टर. अरे यार, योर मदर इज देयर एंड द मदर सिस्टर इज खाला. ओके, अम्मी की बहन. टिपिकली द आइडिया इज कि जो माँ नहीं देती है वो खाला दे देती है. यू नो, ये ऐसे सोचा जाता है कि अगर माँ से नहीं मिल रहा है देन यू मे बी गो एंड से खाला उधर मक्खन लगाओ, शायद मिल जाए. ओके, एंड दिस हैपेंस, यू नो, अक्रॉस कल्चर्स. ओके, तो वो देखो सो रहा है, ना अम्मी ना खाला, क्या करेगा बेचारा. उठ जाओ यार, इसको उठाओ. ये सब लगा के रखा है, सो रूड. तुम ये सब लगा के घूमते हो, कॉन्फिस्केट हो जाएंगे सब. सो जो बच्चे अम्मी से ज़्यादा खाला की सुनते हैं वो बच्चे ज़्यादातर बिगड़ ही जाते हैं. बिगड़ ही जाते हैं ना, सही कह रहा हूँ ना. एंड खाला का एक मोटिव होता है थोड़ा सा, कि मोटिव नहीं होता है बट बिकॉज शी इज टू जनरस, तो वो उतना डिसिप्लिन नहीं कर पाती है. वो शी डजंट लुक एट द मेरिट ऑफ द रिक्वेस्ट, वो रिक्वेस्ट मान जाती है. ओके, तुम क्या मीनिंग ढूंढ रहे हो या खाला का पता ढूंढ रहे हो कि फ़ोन नहीं किया था खाला को कर लूँ, फिर से यू नो रिलेशन बना लूँ खाला से, पहले ध्यान नहीं दिया था. ये that is in a way related to this Taylor series expansion में जो problems होती हैं. Okay. और and this is a very real problem. In my thesis I did some numerical methods and I was running into a problem. Okay, and many people still, you know, make this mistake. If you pick up 100 theses in India or from anywhere, you know, 100 theses about numerical simulations, okay, at least 10 of them would have made this mistake. Okay, and a mistake just happens because of this, you know, because they have not understood this. मतलब बड़ी चीज़ कह रहा हूँ. 100 thesis उठाओगे, जो thesis करता है वो भी कुछ पढ़ लिख के ही करता है. You know, it's a very biased set. उसका एग्जामिनर भी पढ़ता है, उसका गाइड भी पढ़ता है, वो पेपर भी लिखता है, and they still make this mistake. तो इशू ये है, see, the issue is कि we have talked about delta x. What is the other component? The other component is the derivative. You know, first order, second order, third order, fourth order. That's how a Taylor series is built up, and that is how the function behavior is found. Okay. So, in a physical situation, the way you have formalized the problem, you understand that you can formalize the problem. You can choose what the function is. You can choose what x is. Thermodynamics का तो पूरा गेम ही यही है. You can choose what x is. You see? Choose कर सकते हो function. V is function of this, H is function of this. You can choose. That's the strength of thermodynamics. So it should not happen that in your formalism, you know, the second derivative has less effect, has more effect. Third derivative has even more effect than the second one. You see, so as the order of derivative goes up, the impact of those terms should go down. See, if you have formulated your problem or your system is such that the impact of the higher derivatives is more than that of the lesser order derivatives, तब problem है life में. Unseen problems हैं, unknown problems हैं. मतलब अपनी सुनते हैं, which is fx is f नॉट हो गया, ये तो सिर्फ अपनी सुनते हैं. ओके, पहला डेरिवेटिव ले लिया, माँ बाप की सुन ली. ओके, सेकेंड डेरिवेटिव ले लिया, मामू खाला, फूफा फूफी, इन सब की सुन ली. क्यों तो कि जहाँ ये हो गया वहाँ सब गड़बड़ है. इसी तो ये सिचुएशन नहीं होनी चाहिए. और इधर ये जमाने की सुनने लगा, सबकी सुनने लगा, जिसका तो बुरा हाल है. ओके, so this is how I mean, you may laugh, you may think it's a joke, but this is how I remember the Taylor series. You see, in the best way is that if you have all, you see, with varying degree of weight. Okay, and this is so important whenever you are looking at even machine learning, fitting data. You know, क्या weight है? That is the question. Again, यही सवाल है कि कोई और सवाल है? मेजर तो weight है. हम लोगों के पास ज़्यादा है, हमारे पास तो बहुत ज़्यादा हो जाएगा. See, I was very thin when I was your age. हमारे पास तो बहुत ज़्यादा और बढ़ता रहेगा. So you need to get all kind of checks done. कुछ चेक कराने पड़ेंगे और कुछ चेक रखने पड़ेंगे, तब तुम्हारा काम बनेगा. Okay? Check मतलब all kind of hormone level, this, that, you know, thyroid, this, that, sugar, those kind of things, you know. अबे तुम हंस रहे हो, तुम अभी लगती है. ये body है, you don't know how it turns out. Ultimately, kind of wins. So, बहुत complex है. Major frontier ही है ये, समझना इसको. Okay? So all kind of hormones, ये वो शुगर नहीं हो रही है, बढ़ रही है, कुछ खा रहे हैं, वो भी उतना ही खा रहा है, वो दुबला है, हम मोटे हो रहे हैं. All kind of things, you see. So क्या weight easy बड़ा issue है. चलता है. भी झेल रहे हैं, बहुत ज़्यादा झेल. एक प्राइड होता था, मैं कल दौड़ते हुए चलता था स्पीड, 6th floor in IIT Kanpur, and we would race when going to the class. कौन पहले पहुंचता है, दौड़ चलते. आज जो है वो एक चढ़ते हैं, फिर रुकते हैं, फिर चढ़ते हैं, फिर रुकते हैं, धीमे धीमे. तो ये होता है एज के साथ. पर तुम्हारे केस में अगर ध्यान नहीं रखोगे जल्दी आ जाएगा, बिकॉज यही वैल्यू और डिफरेंट है. ओके, सो ये हो गए तुम्हारे स्विचेस. So ये मिस्टेक होती इन फॉर्मलिज्म. So it should not happen that the second derivatives, third derivatives, fourth derivatives have more impact than the first derivative. वो नहीं होना चाहिए. And it plays out in various ways. It plays out in the formalism of the problem, and it plays out in the numerical schemes also. Okay. So ये सब तुम लोगों का काम है. Whenever you come across this, you देखोगे, इसको check करोगे derivatives को. Okay. क्योंकि in the end you're truncating. See, you're truncating means you're not looking at some part. Okay. So कितने उस part significant है कि नहीं? You see, ये question भी बड़ा है. So what to consider and what not to consider. Now, so Z. ऐसे एक्सप्रेस कर देंगे, एक्सपेरिमेंट्स करेंगे. एक्सपेरिमेंट्स आई हैव ऑलरेडी टोल्ड यू, टाइम इज अ प्रॉब्लम फिजिकल एक्सपेरिमेंट्स में. ओके, द सेकंड अप्रोच इज ऑफ कोर्स द फ्रॉम द फंडामेंटल्स दैट यू हैव द पेयर पोटेंशियल. सम पेयर पोटेंशियल क्या है? समथिंग लाइक q1 q2 by r². दैट्स द पेयर पोटेंशियल. यू सी, so pair potential say you have done that exercise where you look at kinetic theory of gases and you develop the EV is equal to RT from there. तो कहते हैं ये कैसे वॉल लगा के इधर रखा, इधर मारते रहते हो, क्लोजन फ्रीक्वेंसी निकालते हो, फिर रेट ऑफ चेंज ऑफ मोमेंटम ट्रांसफर निकालते हो, फिर लाइट फोर्स निकालते हो, फिर प्रेशर करते हो, ऐसे करके किया होंगे सवाल डेरिवेशन का। इधर ऐसे एक शीट ले लेते हो इमेजिनरी एंड देन काइंड ऑफ कीप हिटिंग दिस, ओके। फिर देखो कितनी स्पीड से आया, कितनी स्पीड से वापस गया, इलास्टिक कोलिजन, दिस दैट, नंबर ऑफ कोलिजन्स, ये सब करके देन यू गेट द इक्वेशंस, ओके, और एन एक्सप्रेशन फॉर द प्रेशर, ओके। कोलिजन फ्रीक्वेंसी वुड ब्रिंग इन द वॉल्यूम, कि कितने हैं इस सो दैट्स हाउ द वॉल्यूम कम्स इन, ओके। एंड वो स्पीड जो है वो दैट कम्स फ्रॉम द मोस्ट प्रोबेबल स्पीड और एवरेज स्पीड 3/2 RT जैसे होती है ना, जैसे इट्स ऑल अ काइंड ऑफ सर्कुलर काइंड ऑफ थिंग, नॉट रियली फंडामेंटल, okay, but kind of works, okay. So from pair potential to macroscopic, that is another method and many people work on it, okay. And इसमें एक mean field theories लगाते हैं, because how do you sum? If you are worried about each and every component, then the integration and the summation would be huge, and it would be summing up many different things, okay. So mean field is a way of superimposition, उसका formalism है, easy formalism, okay. So one of the words would be कि pair potential पता है, something like Newton's gravitation वाला m1 m2 by r square, q1 q2 by r square, okay. And then you look at how do you sum it up, okay, superposition और ये सब लगा के, so this is one way, and then you try to get the equation of state, and once you get the equation of state, so ideal gas, real gas, liquids, dense liquids, mixtures, ideal mixtures, ideal mixtures of real systems and real mixtures of ideal systems. You see, all kind of combinations would be there. So you use a lot of mixing rules, you use lot of virial equations, you use lot of equation of states, and equation of states would be, let's say the best one for gases would be the cubic equation of states, okay, and they all start from van der Waals equation of state. So cubic equation of state होते हैं, there is a whole lot of them, okay. So Redlich-Kwong, SK equation of state, RK equation of state, RKS equation of state, so many equation of states, cubic, all kind of cubic equation of states. And cubic equation of states, there's two interesting things that are there. First of all, how many of you realize that you can get, actually for a cubic, you can analytically get the solutions? Have you done that? Quadratic, we get the solutions. Biquadratic, we can get the solutions. Cubic, you can get solutions analytically.
Yes.
There is a method, लेकिन कर लेते हैं.
Formula.
ठीक है, वो किसी ने बना दिया फॉर्मूला उसका, but there is a method. Analytically मिल जाता है. Okay, so you don't have to numerically solve it. So ये है cubic. और कहाँ से cubic आया? Why this cubic kind of works well? और वो सो गए. Cubic के नाम पे सो गए. नहीं, सो पहले गए थे. Cubic को बेकारी बदनाम किया. So, okay, now we are. So cubic equation of state, why does it work, and what is the problem in that? Major problem जो होती है. And whenever you use thermodynamic issues and use equation of state, you have to be careful about that. Okay. And that care is, एक तो तीन रूट्स हैं, solid, liquid, gas. These are the three things that you are worried about. तो तीन रूट्स हैं. The liquid volumes are very different from. Let's say we get solution for a cubic, we'll get three solutions. Fundamental theorem बताई थी ना, algebra की. Polynomial है, उतनी roots होंगी. Okay, it is very, very critical. Okay, Otherwise, all numerical analysis will be on very shaky legs. You see. So ultimately, you know that these many roots are there, and you search for those roots. Okay, and this theorem puts a bound on that number of roots. Okay, so in many cases, when you are trying to find roots, knowing the number of roots is a major thing. कितनी हैं? So cubic will give you 3, and 3 कौन है? एक solid की होगी, एक liquid की होगी, एक vapor की होगी, hopefully. Okay, at triple point 3 आ जाएंगी, या 2 spurious होगी, एक काम की है. Okay, so कैसे how do you kind of figure out कि कौन सी liquid की the route that you have calculated is the right one? You see, because cubic है. Even if you use the analytical expression or you use the numerical method, you still get roots, 3 roots. In general, whenever you solve a non-linear equation, you'll get many roots. In many cases, it depends on which root you use, what is the initial guess. You see? So you'll converge to the root that is closest to that initial guess. ऐसे करके बहुत सारी चीजें हैं. So any kind, so see, most of the things would be non-linear. Will be solved through a non-linear analysis, at least in your age. ये वाला काम तो कर चुके लोग. My age में you have to look at more difficult problems. So non-linear है, non-linear solve करेंगे. You don't know which root, okay, or whether whatever you have solved is correct or not. So वो तो in general रहता ही है non-linear के साथ में. The issue is there. So roots पता करते हैं. So the major issue is कि whatever you have gotten out of the simulation package or your solution is the right answer. You see, and the roots for gases, roots for liquids, and roots for solids are very different. You see, वो density change कर दोगे तो एकदम ही impact बदल जाएगा ना. We have discussed that. You see, the reason gases तो flow कर जाते हैं, but there are very few molecules. Material ही नहीं है. उड़ तो रहे हैं सब जगह. Accessible है, सब जगह पहुंच जाते हैं, but material ही नहीं है. You see, तो वो density दे दी उसमें calculation में solid किया, फिर कहा कि नहीं efficiency is this much. अब पेपर लिख दिया तो अगेन पेपर ना लिखा लेकिन एक एमटेक थीसिस तो हो ही जाएगी. गलत रूट डाल के इम्प्रूवमेंट दिखा के एंड एवरीबडी इज हैप्पी. और जब प्रेजेंट करें तो थोड़ा पैशन और ले आते हैं उसमें, ये बबलिंग एंड सॉल्ट हो गया एमटेक. तो अभी ऐसे भी सॉल्ट हो जाता है ना, एमटेक हो जाता है ना. इसी हम ऐसे देखते रहते हैं. जाने दो यार, वी टेक अ डिसीजन कि इसको 1 साल रोकना अच्छा है कि इसको जाने देना अच्छा है. एंड यू नो वी कलेक्टिवली डिसाइड कि यार इसको छोड़ दो, ये औरों को भी खराब करेगा, इसको जाने दो. So it's not that you get away with it. You get away without the strategic decision. Not to spend any more resources on it. ऐसा नहीं. We try to teach. Try जैसा भी हो. So all of this is done. Any question on whatever maths we have done? But do you actually feel more comfortable with maths now, or ये देखो वो 3 चश्मे वाले समर दिस एंड दैट जुटे हुए हैं, वो तुम लोग की आदत ही नहीं सुधरती है. And I'm saying just for an hour the Trump का डर दिलाया, CEO का डर दिलाया, कुछ हो ही नहीं रहा है. देखो ये ऐसा नहीं है कि मेरा बाप यहाँ था, मेरा ये यहाँ था, मेरा वो यहाँ था, वो सब नहीं है. I can be the worst teacher that you will find in your life. You even have that idea, you see. If I am very comfortable discussing all those things, means कि I can execute them myself. Okay, joke चलता जा रहा है. I'm just trying to do it in a very simple way. फिर भी बात होती जा रही है, लेकिन बाद में पकड़े जा रहे हो, then there is no guilt. You're just smiling कि अब ये फिर करेंगे. यार अभी छोटे बच्चे नहीं हो तुम, जो बदमाशी करता है एंड माँ से कि ठीक है यार फिर कर ले, अभी तुझे समझ नहीं है, अभी तुम पढ़ ही नहीं रहे हो, सुन ही नहीं रहे हो. मैं इधर सब निचोड़ के डिस्टिल करके पढ़ा रहा हूँ तुम्हें. For the last 6-7 lectures I tried to make life easy for you, क्योंकि इतनी मैथ्स तुम्हें समझ में आ जाए, so that you are comfortable with whatever level of maths you find in your life. Okay, and I can guarantee you that if you had listened to all these lectures, your numerical methods, this, that, function analysis, you will get them easily. You see, you'll be more comfortable with them rather than struggling. You will find answers. Later on also, if any problem comes, you will find answers. But if you had listened to all this, it would have been easier. You see, you could have solved bigger problems easily, or you could have looked at some problems जो नहीं है. I give you so many examples. The state of art in phase separation, the major problem is all based on inconclusive proof. मतलब if that does not excite you, हम कर ही क्या रहे हैं यहाँ पे? Anyway, so the idea is not to collectively bring in a mahal of animosity here. Enjoy karo, you are in a good time, life hai, enjoy karo, class mein padho. I'm just asking कि 30, 40, 50 minutes चुपचाप रहो, सुनो, अब बात करते ही जा रहे हो, and with direct reference also तुम नहीं सुन रहे हो, मतलब कैसे होगा ये? Just imagine, बाहर अगर कर रहे हो क्या होगा? With the position of authority, yeah, maybe in a meeting where everybody is contributing, in a communal setting also, community setting, communal is a very bad word. In a community setting, तुम ऐसे disturb कर रहे हो system को, क्या है? पढ़ो यार इसको. So I'm asking you this question, do you feel कुछ समझ में आया? नहीं समझ में आया? कोई बात नहीं. We'll try again some other time. But this was not, the maths that is at the core of, all the difficult maths that you will see in thermodynamics. सिर्फ एक concept बाकी है, वो that also we'll find out. But most of the concepts about, the maths in thermodynamics have been covered here, whatever we did here, and also the kind of pitfalls that you will make, okay, and errors that you can make. Okay. Now we come to all kind of calculations. The calculations that there is an equation of state, and that equation of state can be converted to then work done is one of the things. So we can calculate that, okay? क्योंकि P dV से निकाल सकते हैं. And how is P varying with D? With V? PV gamma is constant. If you don't know anything, then PV gamma is constant. Something that will work. Okay? You should be able to figure out why PV gamma kind of has worked. Okay? कुछ और भी हो सकता है. Okay? Why PV gamma has worked? If I ask you that question, and why gamma has, for most of the processes, the gamma is this way. Okay, so you can look at all the processes that are simple ones, adiabatic, this, that, everything, and you can find out what the work done is. Okay, so yeah, it's sorted, it's not difficult. Okay. And we can compute all the compressibilities, Cp, Cv, Cr, all that we can compute. Okay, so if you move to, let's say the heat. So we'll introduce it here and we'll continue in the next class. Okay. If you have ever bothered about why do we just put H whenever we are looking at heat effects, बड़ा interesting है. You see, we are looking at heat effects and we are looking at what heat is and this and enthalpy है. E भी लिख सकते थे, कहीं नहीं लिखते भी. So finally H चले गए. H is equal to U plus PV, and I had a question also in one of them in the midterm. Okay. So most of the things would be done in terms of, let's say, the enthalpy. Okay, so some stream is coming in an open system. क्या लेके आ रही है? H लेके आ रही है. Okay. कुछ काम कर सकते हैं. इस मास में क्या रखा है? कितनी हीट है? H है. Can anybody answer कैसे हो सकता है ये? Because of in a closed system, U हो गया. You see, U को zero कर दिया, सब कुछ ले लिया. Okay, और PV D को भी zero कर दिया, सब कुछ ले लिया. So enthalpy is what is there with the system. You see, all of that can be converted to heat. You see, वो पूरी transfer हो सकती है ना as a heat. Okay. Okay. So if we use enthalpy so many times, you see, whenever we are looking at heat effects, then it makes sense. You see, okay, and we are doing a balance on what is possible. We are not doing a balance on what actually happens. So we are looking at what is the maximum possible that can happen. You see, and then of course we'll see what happens, and we'll look at all kind of coefficient of performance, efficiency, and all of that. Okay. बोल तो लिख के तुम कर रहे हो, मतलब सुधरोगे नहीं. When I speak to you, you should be looking at me. You see, तुम बार बार उधर उधर घूम के देख रहे हो, उसकी क्या देख रहे हो उसके वहाँ? ये नॉर्मल है गर्दन कैसे घूमना, ये करना, दूसरे की शीट में देखना? इज इट नॉर्मल? ऐसे बनी है तुम्हारी नेक? इज इट सपोज टू डू दैट? कुछ उल्लू की नेक है 360 डिग्री पे नॉर्मली घूमती रहती है, इंसान की गर्दन है. दो आंखें दी हैं सामने देखने के लिए, आंख दी है, फेस दिया है, कुछ सोच के दिया होगा ना. पीछे भी तो आंखें हो सकती थी, साइड में भी तो हो सकती थी, सामने क्यों है? कुछ ज़्यादा डिफिकल्ट सवाल है इवोल्यूशन में पूछना तुमसे ये. ये इंटरेक्शन के लिए. तो कहोगे नहीं गर्दन तो सर घूम सकती है, थोड़े मसल्स हैं सर, घूम जाती है. कुछ कह रहा हूँ सुनो तो कम से कम. व्हाई यू जस्ट कीप पुशिंग दिस? ओके, वेयर इज द अटेंडेंस शीट? वो मैम आ जाएंगे, कहेंगे यार केमिकल में यही होता है. अरे आइडिया ये नहीं है कि तुम्हें परेशान किया जाए, या ये कि तुम्हें मैसेज तुम्हारे तक पहुँचे. अरे अटेंडेंस शीट तो भी चेक करना है यार, यू हैव टू कैच समबडी. तुम बताओ ये सही है? ऐसे दिखा के वजन करके ऐसे देखो, ये देखो और देखो और देखो. दो है, दो गलत होंगे.
आयुष चौधरी, आर्यन त्यागी, हितेश गौतम, तौकीर मोहम्मद, निशांत कुमार, साक्षी पटेल, निशांत नंदन, गुलूकोज लोकेश, अक्षय राज, तहसीन अहमद,
अक्षय राज का है, सॉरी राज,
तहसीन अहमद, कुनावत पवन, विनावत गणेश, अंकित कुमार, हार्दिक कुमार, खुशबू यादव, लकी भूसकुते, शुभम चावला, अभिषेक कुमार, आकाश, प्रीतम कुमार, आकृति हरित, मनु कतियार, सुमन माझी, पारस कंसल, सुरभि, श्रेयांशी, जागरव, राहुल कुमार, प्रखर अग्रवाल, दिव्या, केशव, अर्णव रंजन,
केशव का एक केशव है, दूसरा केशव.
अर्णव रंजन, विकास कुमार,
अर्णव रंजन, विकास,
बसंता रॉय, अंश अरोरा, ईशा कुमारी, आर्यन, आयुष बंडेरिया, हार्दिक कोतवाल, समर गुप्ता, घर गुप्ता, दृष्टि, निखिल जहांगीर, स्तुति उपाध्याय, शशांक सिंह, निकिता जलवानिया, अभिषेक सोनी, दिव्यांशु शर्मा, आलोक यादव, नितिन यादव, हार्दिक भगोड़ा, उदय प्रताप सिंह, निशांत विश्वास, केशव राज, दीप्ति भारद्वाज, सचिन चंदवाड़ा, तुषार शर्मा, मयंक कलाल, अंकित पटाया, सरन मेहते, रोहित कुमार मीना
का,
अनिरुद्ध गोयल, विशाखा सिंह, इशिता सैनी, श्वेता चंद्रा, ऋषभ देवांगन, शशि कुमार, पुलकित गर्ग, अनन्या यादव, अनहद सिंह, आदित्य स्वामी.
क्लास क्या? क्लास मेरी तो है पर मैं अब करनी अरे बहुत ज़्यादा थक गया हूँ यार, सोया नहीं हूँ कल रात का, नींद आ रही है बहुत ज़्यादा। 6 बजे सोया था, सुबह 9 बजे उठ गया।
6 बजे सोए थे।
हाँ हाँ
ये भी ठीक है, 7:30
क्या
ये सुबह 6 बजे सोते हैं, 7:30 बजे
आज ही सोया था
मेरे पास
तो भाई ये तेरा तो लेवल ही अलग था।
क्या हुआ इसका?
सुधर गया है ये तो।
4 बजे उठना,
सोचा कितने बजे? वैसे एकदम ब्रह्मचारी।
ये तो नहीं, ये लॉजिक है। 4 बजे
क्या होता है?
4 बजे सारे नेगेटिव एवरेज लगभग हो जाते हैं, तो लगभग न्यूट्रल होता है। योग करने से सारे पॉजिटिव एवरेज इसी टाइम पर 4 बजे के बाद। तो 5 बजे के बाद सबका वापस नेगेटिव एवरेज होता है, फिर ये टाइम शाम को टाइम
4 बजे सोना नहीं उठना होता है।
मैं पहले क्यों नहीं बताया कि ये मुझे
25 साल वेस्ट हो गए। क्या कर रहा था उसको?
हमें तो अपना शेड्यूल सही लगता था, वही बात।